So hello and welcome to the second day of our Galileo teacher training program. So we go to the next topic. Yesterday we've talked mainly about Earth, our own planet, where we live, and everything that you can do with satellites and spacecrafts there. And today we go a little bit further out into the solar system, and I'm sure you have all seen some science fiction movies about Mars, and the interesting question is still, is there life, or at least was there life at some stage also on that planet? And to find more out about this, so there are also a lot of spacecrafts that were going there in the last decades. And today we have here our colleague Alejandro Cardesi. He is not only the science operations manager of the Mars Express mission. It's a mission that is now since more than 15 years investigating the red planet. He's also a scientist himself and studies a lot of different subjects there. And so he will tell us today a little bit about Mars and all the missions that went there in the past, a little bit about the history and what we know really about the planet so far. So I hand it over to Alex. I just think he has some problems with the background. So
hello, can you hear me?
Yes, perhaps you can raise the volume of the microphone a bit.
No, that means getting closer to the microphone, I guess you mean. Okay, so I guess you see my...
I suggest that you take off the background, Alejandro. It's like my computer, it's a shadow of you. So good morning, everyone. Hope everyone is awake, alive and kicking. So
yeah, better. Yes, okay.
Much better. Thank you, Alejandro.
Okay, there you are. Okay, so should I start? Let me share my screen. In the meantime, just may I ask how many people is online at the moment?
For the moment, 38, but I hope we're coming back to the same level as yesterday, which should be around 80.
Okay.
Hopefully.
Okay, let's move this somewhere here. Okay, so let me start. As Michel said, I'm Alejandro Cardesi Moinelo. I work with Michel and the colleagues at ISAC in Madrid, and I'm coordinating the science operations between Mars Express and ExoMars. And I'll be talking today about Mars science and exploration. Okay, because there are two things. What the purpose of this talk is to see how the technology has been driving the knowledge throughout history. So we will go from the origin of times, or the human times, how we understood Mars, to the space era, and the space exploration nowadays. Okay, because Mars is very, very interesting, not only as our neighbor planet, as all of the planets are very interesting, but actually Mars has another aspect that makes it very challenging, which is that we can actually go there now with robots, but we will very soon be able to go there with humans, probably in the next decades, and we are doing all that we can for that. Well, I apologize, this is the clock in the living room. That may be something. Let me wait for the 10th bell. Okay, now we can start. That means we're on time. Okay, what's going on? Okay. Okay, so first of all, a very brief introduction about Mars, just to get us all in context. And the first thing is that Mars, the name itself, was the name of the Roman god of war. And Mars is the fourth planet in the inner solar system. This is this one over here, and it is actually of the 4 terrestrial planets, rocky planets that we have, somehow similar to the Earth. This is the farthest one. And it is a bit red because of the ferric oxide in the surface. It is actually this red color that gave inspiration to the ancient Greeks and Romans to give the name of Mars as the god of war. Then very basic parameters here is that it has half of the diameter of Earth. We see here a comparison. It has a fourth of the surface and a tenth of the mass. So that means that if we stay on the surface of Mars, we would have a third of the weight. So I'm about 90 kilograms. I would be weighing 30 kilograms on there. The atmosphere on Mars is very small, very thin compared to that of the Earth. And the Martian day is very similar. It actually has more or less the same duration, about 1 hour more. Whereas the year is twice of that of the Earth. And has 2 little moons, Phobos and Deimos, that we will be seeing later. So now we start the story. This was just a brief context, but let's start the story from the beginning. What did the early humans see in the sky? So that's without technology, just by looking at the lights, the bright spots that they see on the sky. So the first thing they saw was that there are a lot of bright spots in there, mainly the stars, but there were many of them that did not follow the same movement. So they would moving from day to day, from season to season. And these were these 5, Mercury, Venus, Saturn, Mars, and Jupiter. These were what they called the traveling stars. That's the traveler stars or wanderers. These were called then the planets. This is what planets actually mean. And they gave name to these 7 anomalies, but I actually only mentioned 5, Mercury, Venus, Saturn, Mars, and Jupiter. The other 2 planets, although they had separate names, they were actually the moon and the sun. These were the other 2 objects that were traveling in the sky without following the rules of the rest. So they were special. There was something weird going on with them. But they didn't know much more than that. The only thing they could see was the movement. So these gave actually drove the mythology. These are actually the reason why we have 7 days of the week, and the reason actually of the names of the weekdays. In particular, in English, it's moon for Monday and Saturday for Saturn, Sunday for Sun. But in Latin Roman languages, it's even more evident. So basically, in this era, without any technology, no telescopes, of course, no satellites, there was very limited knowledge, and the only thing they could do at the time was actually speculate, and then these drove to mythology and not real science. The real science will come later on. They could have done. They did know some things about the movement of the planets, but not much more. So that's why the mythology was boosted. But then, thanks to the technological advancements, the next step was the invention of the telescopes around the 1500s or early 1600s. The first one to actually use it for science was Galileo, to take this telescope and start looking up at the moon, at Venus, at Mars, and everything that he could find up in the sky. It's very well known, the findings of the moon, actually the phases of Venus. On Mars, he also looked at it, although he did not see anything interesting. His telescope was still very basic. But only a few years later, once the telescopes improved a little bit, another astronomer, Huygens, observed a dark spot in Mars. It's very, very faint, but he actually did these drawings at the time. And just by seeing this dark spot, he could already calculate the rotation of this object of Mars. He didn't know what it was. It could be a ball of fire, but he actually saw that it had a dark spot in there that was rotating. It had a duration very similar to the Earth. It actually calculated also the diameter of this object, which he calculated to be 60% of the Earth, which is quite amazing how he did that. And also he saw this little spot in here near the pole, which he already identified as a polar cap. So we went from a time where these objects were traveling the sky and were basically gods, no one knew what they could be, to in 1659, we get to a point where we actually are thinking in a completely new world already at these times. It was still very speculative, but it is completely changing the mindset at the time. And this was, again, driven by technology, driven by the new telescopes that were bringing more and more knowledge. So we went on and developing better and better telescopes until the end of the 19th century. And here we get one of the best images at the time by Schiaparelli, but the problem is that the technology was reaching its limits. And we could see some more features on Mars. We could see even better the polar caps, but the quality of the telescopes was still very, very bad. So then this limitation in technology started then again driving the speculation. So they could not really interpret these images, and they started seeing or trying to interpret what they call the optical aberrations of the telescope, these limitations of the technology. So the astronomers here, they started to see things that were not really there, and they started to hypothesize, speculate on what these channels could be. So they actually did these maps of the planet. So some of them are real features, but all of these channels here, they were fake. They were not real objects on the surface of Mars. But this was again limited by technology. The technology had reached its limits, and then the floor was open to speculations on what these channels could be. And it is amazing how these continued actually until the 50s. If you see some of the documentaries of space of the 50s or even early 60s, you could see that this was the concept that they had of Mars. It was a flat land of channels with water, probably built by Martian civilization. And this was present in all sides of society. This was very well known. The War of the Worlds by Orson Welles, 1938, but also many other documentaries of those times. So then we get to the space era. This was in 1957, the start of the era. It was the start of the space race between Russia and the United States. Russia was the first one on the 4th of October of 1957. They launched this little satellite called Sputnik that many of you may know. And it is really amazing how you see the date here. It was 1957. At this time, still, they did not know anything about the surface of Mars, about what was Venus made of, all the objects out there. There was some insight thanks to the spectroscopy, but still it was very, very light. So it was a major breakthrough once they actually managed to get out of the atmosphere. In 1957, it took them really, really short time to start sending things farther away. And this was the next step. You see, in 1960 already, only 3 years after Sputnik, they were already sending missions to Mars. First was the Russians until 1964 with the Americans. We see here all this first region here on the left. This is the core of the space race until 1975. And here after 1975 with the Vikings, there was a stop. There was basically the end of the Cold War and the reduction of the missions. Only until the late 90s we see that the space race, or not the space race anymore, but the space missions were boosted again, not only United States and Russia, but now also with Japan. We also see here Europe coming up in the early 2000s. So there's a lot of information in this graph that was just showing how it works here on the left chronologically. But then on the right here, these circles mean, well, the first circle here was that the mission was a failure. So that the mission did not meet its objective, did not reach Mars, or did not leave the Earth, or something else. The next step is a flyby. A flyby meaning that it passed through Mars but did not stop there. This was actually the first successful mission to Mars. It was the Mariner 4. It took the first pictures of Mars. And then the next step, we had Mariner 6 and 7, also with flybys, taking picture. And the next step that happened in the early 70s was an orbiter to Mars. So actually managed to go to Mars and stay there for a while, taking images, taking data from the surface of the atmosphere. And this was again in 1971. But we see that the next step, which is a lander, is to actually touch the surface, has only been done 7 times. Well, we are missing a few in the late years. It has only been done 7 or 8 times now, and only by the Americans. So Europe has not yet been able to land on Mars. And Russia, well, did land on Mars, but it was not successful. It was only operative for a few minutes, so it was not really successful. And then also the rovers, it was only the Americans here. So a part of all the information that is given in this graph, the main point I want you to bring home is that it is very difficult to go to Mars. So about half of the missions that have been there actually failed. And while we are learning and we are getting more and more missions successful nowadays, it is still very, very challenging, especially to land in there. Only the Americans have been able to do it. So we get to our times nowadays. We saw before that in the early 2000s, we had a new armada of missions going to Mars, with Mars Express from ESA still operational, Odyssey, MRO, and the Opportunity and Spirit rovers from the Americans. Then another point to mention here is that the windows, what we call windows to get to Mars, actually happen every 2 years. So we are only able to launch spacecrafts or missions to Mars every 2 years. So we had here 2001, 2003, 5, 7, 2009, 11. Here it happened around December, January. So this is when MAVEN, the atmospheric mission by NASA, was launched. And we also have another partner there, the Indian mission, Mars Orbiter mission, and Curiosity. And then we got to the last ones in 2016. The last one by ESA was Trace Gas Orbiter, which we'll be mentioning later on. And the last one that landed there was in 2018, was InSight by NASA as well. And then we get to 2020, which is also a very crowded year, with missions going to Mars in this very moment. At the moment, they're traveling through space on the direction to Mars. And we have another very big and impressive rover by the Americans, Mars 2020. But we also have another two partners, which are China, which have an orbiter, a lander, and a rover, and the Arab Emirates, the HOPE mission that is also traveling to Mars. This is what we have at the moment in space, working and going to Mars. And then in 2022, we will have also the ExoMars 22 mission, which is a collaboration between ESA and Russia, we will mention later. And then we will be mentioning at the end a little bit about the Mars sample return and the other future missions or projects that may go to Mars. There's even some private initiatives that are still quite uncertain, but they may still make it in the next years, who knows? But we still have a long way before we can actually have astronauts in there, but we are working on that. But there's still a lot of technology we need to bring. The next step will be Mars sample return. Okay, so let's go back to the present, to Mars Express. Mars Express was and is still the first European mission to orbit another planet. It was actually the first mission of the called Rosetta family, which was Rosetta, Mars Express, and Venus Express, and it's still operational since 2003. And it has recently been extended until 2022. We're hoping to get it extended even further until 2025. Mars Express is in orbit around Mars since 2003, and it's looking at all of Mars system and as a whole. When we take a trip somewhere, we go to an island, visit some new place, we want to take pictures of everything and learn as much as possible of the place. And this is what we are doing with Mars Express. We're looking at Mars from the interior, measuring the gravity field and trying to understand how the composition, morphology of the interior, the subsurface, the surface, of course, geology, composition, mineralogy, the craters, volcanoes, mountains, everything. And then going up to the atmosphere and the ionosphere, trying to see how they interact and what is the composition and how the dynamics of the clouds and the dust works in the atmosphere. That we will see is very, very important. Not only that on the planet itself, but also the two moons, Phobos and Deimos. And so to go through this, I will let you this video. Okay, so I'll just go through some of the images here. We see these are real data, by the way. This is data taken from Mars Express itself. We can see valleys carved by rivers in the past. Where we can see the craters, and we can see some effects here of the dust falling from the craters. We see the water ice. Yes, there is water. We will see a lot about that. There is water on Mars, and it's a lot in the form of ice or glaciers, as we see here. There's also tectonic activity in there, and we see also the minerals in the surface. We will look at that. We have done many discoveries. One of them was the auroras on Mars. We are imaging the subsurface with a radar, so we can build 3D model of the ice of the polar caps. And we are looking at the atmosphere as a whole with radar. Also the Mars moons, those were Phobos in here. We can see also the craters and features in there, and Deimos which is the farthest smaller moon. Not only that, but we are also using the spacecraft to support NASA missions, and also in collaboration with TGO, with ExoMars. We're doing a lot of science together. Okay, so let's move on to the next one. This one. Okay, there you go. Okay, so this was a very brief video, just to check us. Can you still listen to me, Michael? Anyone?
Yes. Amazing.
Yes.
Yeah.
Okay, I'm just checking. Okay, so what I will do now, this was a very brief and quick video of highlights of the mission, but what I prefer to do is drive you through some of the discoveries of the mission that have been occurring in the past year. So I will be going through a few topics. The main one, of course, is liquid water and potentially life, but I will also mention the methane mystery and the atmosphere. So these are things that we have learned in the past years, thanks again to this new technology, to the space missions, in particular Mars Express, and then I will go to the next ones in ExoMars. So why is liquid water important? The idea is that we want to know if there's life, and we know that life is very related to water. So this is why we are chasing the water and trying to find out where water is outside of the Earth. So let's think a bit about this issue of life, which is quite amazing. If we look at us here on the Earth anywhere, if I ask you now to look at your hand, actually, if you would do this experiment here with in a lab, you could actually see with a microscope that there are millions of microbes, of organisms living on your hand at this very moment. Okay, so anywhere you look at the Earth, at your table, at your walls, everywhere, even your hand, there is millions of organisms. But when we look at Mars, at the moment, in one entire planet, there is not a single living organism. That is at the moment, it's amazing for me, at least. It is it's very impressive to think that there is more life in my hand that actually there's in one entire planet. Actually, at the moment, there's more life in there than anywhere in the solar system, or actually in the universe. And this, for me, this is very difficult to understand. There must be something out there, and we need to go and find it somehow. So if we look at the Earth, we have life everywhere, no matter where we go. We go to the deepest of the oceans, we go to the driest place, we go to the coldest place below the glaciers. We see microbes swimming there, even in the waters with very acidic, very salty, like this one. We find microbes everywhere. There's only one thing that is actually in common. The only thing that they need to live is water. Liquid water is the key. This is the famous water bear or tardigrade. This is this famous animal that is it's called the immortal animal, because they live in all kinds of conditions, and you can actually boil them or bring them to space or dry them or do whatever you want with them. The only thing they do is they just dry out, and as soon as you put a little bit of water on them, they will then start swimming again and leave. So it has actually been proven that these little bears can survive in space conditions, and actually they were brought to the moon recently by one of the recent missions. So, okay, this is just an example to understand that we see life everywhere. And everywhere we see it, it's connected to liquid water. And even in the dry places where there's no liquid water, the microorganisms will use either the salt or some other condensation process to find the liquid water and leave. So then we go to the concept of habitability zone in our solar system. basically, we look at the inner planets here, Mercury, Venus, Earth, and Mars. There is this definition of habitability zone, and this is the limits where we go from having a place like Mars, what we could describe as a global fridge at the moment, with almost no atmosphere, to on the right neighbor, on Venus, we have a greenhouse oven. So there's somewhere an equilibrium between, of course, the input of power from the sun and the distance, where we can find a balance so we can have actually liquid water on the surface and have a habitable place to be. And this is the limits we're trying to find out, because these are, we will see now in a moment that actually these limits, they depend also on the conditions of the planet itself. So Venus is a hell at the moment. It's a greenhouse oven, but not only because of the distance of the sun, of course, it is closer to the sun, but the main reason it's the atmosphere. It's an atmosphere that actually broke the equilibrium of the planet and drove the temperature to go to really, really high temperatures. And on the other side, on Mars, it is very cold, but it could have hosted liquid water, and we will see in a moment some of the liquid water in the surface. But the reason there is no liquid water at the moment on Mars is actually the atmosphere. So it is not only this habitability zone, is not only the distance to the sun, but the atmosphere is playing a key role. And this is why we have to study it. So I promise this is the only plot I will show in my presentation. I don't like showing plots in this kind of presentations, but this one is very important and to understand what is going on here. So the main scale I want you to look at is down here. This is temperature. Okay, the idea is that if we are on Earth, we can see that the water goes from solid state, that is from water ice, to liquid state. It just liquefies at 0 degrees. 0 degrees, of course, that is the definition of Celsius. So at 0 degrees goes from ice to liquid water, and at 100 degrees will go from liquid to vapor, water vapor. So this is what happens on Earth. The problem we have on Mars is that we are just below this limit here, about 600 pascals or 6 millibars. This limit below there, where the water goes directly from water ice to water vapor, and this is actually what we see on Mars. At the moment, we see ice in the polar caps, and we see vapor in the atmosphere, but we do not see water, liquid water running through the valleys, although there was in the past. So the reason we don't see it at the moment, it's because of the atmosphere. If we add more pressure to the planet at the moment, we could actually be slightly higher in this curve. We could then move up here and then see some liquid water running in there. So it is not the temperature that is driving this process, or not only the temperature, but it is the pressure of the atmosphere. Okay, so we will see some more examples now. Okay, so we have to, this is a recent map of how Mars looks today. I want to give you just some basic ideas here of what we see, and we're going to try to reconstruct the history of Mars backwards from here. Okay, so the idea is the very basic thing that we see. There's two very different regions, and the northern hemisphere is very flat and low. But here, blue does not mean water, not yet. It means altitude. Although we always on the maps of Mars, we tend to put the lower areas in blue because we do think that there was an ocean in this area here. So this is in the north, it was flat and low, and in the south it is high, and also it is very, very rough. There are actually a lot of craters in here. We see, well, of course, these two gigantic craters, Argyre and Hellas, but also a lot of rugosity in all the area. This rugosity, it means that there were a lot of craters. This means that this area is very, very old compared to the north. So we have an old south and a young north. And then here on the left, we see an area which is also young compared to the south, but has these features here. These are the Tarshish volcanoes. This is Olympus Mons, the highest volcano in the solar system. So this is an area with a lot of volcanic activity. It was actually cleaned up the surface compared to the south. Okay, so this is just the basic idea, and even already at this level, from the very first, let's say, images from far away of Mars, we can already see some areas like here, where we see some traces of what could be a river. Even if we look at this without knowing much about geology, you could recognize some features that you may think, okay, well, this looks like there was a lake in here and the water was going down through these lakes and up to an ocean in here. So this can already be seen at this scale. And this is actually possible. We're still trying to understand what happened, but we need to go back a little bit more. So we try to understand what happened, because we see Mars as it is today. It's just a gigantic desert at the moment. But we maybe, as you saw, maybe there was some water near the north, or actually maybe there was water in all this ocean in the north, and the craters and the valleys were filled up with water, or maybe the water was all covering the planet everywhere, not only there, but actually everywhere else, and different conditions. And the question was, when any of these scenarios happened, when there was liquid water, we know that to have liquid water, we also needed an atmosphere. So then the conditions would be very similar to what Earth is today, or was when the life emerged. So in these conditions, was there life at the time, or was it possible for life to live there? This is what we're trying to find out. Okay, so we're going to look at this history of Mars through various aspects, various topics. The first one is analysis of the geology. We do this with cameras typically. And as I showed you before, some of these areas, we see that there were rivers. This was clearly liquid water running on the surface. And this is the edge of the of the river, when we would reach some sort of lake or sea or ocean. And we also see glaciers. This is not liquid water, but actually ice. We see glaciers of ice flowing still today on Mars. But then, as I told you before, you could look at the craters and look at how old these regions are. And we see, we can actually measure the number of craters, and we can estimate the age of the area. And we see that the fluvial areas, all of them are very old. I can put here 100 million years old, but typically they're even much older, like 3,000 million years or 3 billion years ago. Whereas the glacial structures are actually much more recent. So we see already there an indication that the liquid water was there far away in the past, but not in the present again. We now look at the mineralogy. That means the chemistry of the rocks. We can look at this with the spectrometers. We can see basically the colors of this rock and find out which mineral it is. We see, for example, here, this is the ferric oxide. We see that the upper region is mainly dominated by dust, by ferric dust, basically. But if we look at some minerals, what are called the aqueous minerals, or the hydrated minerals, these are minerals that were found that are, formed in the presence of water. So it's not minerals that are wet just a few minutes or hours or decades. These are minerals formed under a lake or an ocean for thousands of years. So, and when we look at the rivers here, the images before, we see a channel of a river here going into a larger lake or ocean. But actually, we don't find the minerals in this region, which is odd. Well, probably because they are covered by sediments. But we actually find the minerals in the older region, in the region that was before that river. So actually, if we look at the map, we find we were speculating before that the rivers could go from these areas to the north, to the ocean north. Instead of that, we find the hydrated minerals in the older regions. So that would mean that the ocean was not in the north, but would maybe be in the whole of the planet before. So these are different theories, different ideas that we're still trying to find out if the ocean was again in the northern area or in the globally in the planet. Actually, this is more or less how it could look like now. If we look at the present, again, it's a giant desert. But then we see that there was some, sorry, let's go back. We see that there was a region where potentially there was an ocean in the north, but maybe it did not stay there for too long, not enough to make these minerals, but farther away in the past, there was a global ocean that covered the planet just after it was formed. And it is interesting to see that we compare Mars with Earth. This time, around 3.5 to 4 billion years, this is more or less the time where life was formed on Earth. So at the time life formed on Earth, we know that Mars had similar conditions to what we had on the Earth. So was life formed on Earth and not on Mars? Was it formed in both? This is a question that we have to answer. Okay, so we see that there was a lot of water in the past, liquid water, rivers, lakes, probably oceans as well. But where is the water now? At the moment, we just see this desert. We see here some images of the sand dunes. Where is the water? We don't see any water in the surface at the moment. But actually, we do see water in the polar caps. We are measuring it. We have this radar that we are able to build a 3D model of the polar cap. So we are actually able to see how much water is trapped in the polar caps at the moment. Not only that, but with this radar, we have been able to identify liquid water also. We know at the moment, there was a discovery in 2018 that in some regions in the South Pole, so down here, we did this radargram, it's called. You can imagine it as an echography, let's say, and a radar image going down. We could find 1.5 kilometers below the surface, there was this water lake. So not only water ice, all of these areas water ice, but also liquid water. This was the first time this was discovered. And this was even confirmed just a month ago, or actually 3 weeks ago, that we could see that not only this big lake, this is the lake that was found here in the South Pole, but actually there is a network of lakes around this area. So we know there's liquid water down there. The problem is, how can this liquid water be still there? The conditions that it has to have, probably it needs a lot of salt, and some of the models predict that there may be some heat coming from the core of the planet, so there might be some geological activity down there. Still, we still need to find out. But the interesting idea is that these liquid water lakes may still have some life in there, because we know that in some of the deep lakes on the Earth, below the Antarctica and the North Pole, we have living organisms even at this great depth. Without light, there's, as I mentioned before, life finds its way to survive. To first to stay there and then survive. So also water is in the atmosphere, and we can even see it. These are actually images by the cameras and the spectrums. So we see this is a water cloud that is forming regularly in one of the volcanoes. This is Arsia Mons. And we see this water cloud that forms and it extends more than 1,000 kilometers. But not only this is condensation in the clouds, but we actually have water vapor all around the atmosphere, and we see that with the spectrometers. Okay, this is just a summary, by the way, that I forgot to mention about the comparison of the atmospheres of Mars and Earth. We know that on Earth, most of the atmosphere, 80%, is nitrogen, and we have about 20% of oxygen in there. This is, and then we only have these small parts here, about 1%, which are all of the other gases, carbon, argon, carbon dioxide, and especially this one here, water vapor. There's very little quantity of water vapor on Earth, but still enough, of course, to keep us living and breathing. On the other side, on Mars, we have most of it, 96%, it's carbon dioxide, then 2% of nitrogen and argon. And the water vapor and even the oxygen are what we call trace gases. These are, there is water vapor, oxygen, ozone, a lot of other things. But we still don't know exactly how the atmosphere was formed, and how it works. We know on Earth that although carbon dioxide, for example, or water vapor or ozone are very, very small in quantity, we know that they are a key player in the climate of the Earth. The same happens with Mars. We need to understand not only how the carbon dioxide works, we know there's a lot of it, but we need to understand all of the rest of the gases to understand how the atmosphere works. Because as we said before, it was the atmosphere that probably drove the existence of water lakes and water rivers and liquid water in general in the surface. So there is some water in the atmosphere, but what happens then? We also look at the outside of Mars, the magnetosphere of the planet, and how the atmosphere interacts with the solar wind from the sun. And we actually see that the water is escaping from the ionosphere. So we see that these water vapor molecules, H2O, in the atmosphere transforms into atoms or ions of oxygen and hydrogen. And we can actually measure them with a plasma detector flying around here. We can see that these hydrogen and oxygen atoms are actually running away of the planet. So this is one of the theories, that the water that was there on Mars escaped. We know that there's still some in the atmosphere. We know that there's quite a lot still in the ice in the poles, but many of the molecules of water could have escaped in the history through the solar wind. And this process is, well, first because Mars does not have a magnetic field like the one of Earth, but not only that, but it's also because sometimes the water gets very, very high in the atmosphere of Mars, whereas in the Earth we have this cycle that water goes up in the atmosphere, and then at a certain point, which is a limit, condenses in clouds and then stays down. But sometimes on Mars, we have measured actually that, especially during the dust storms, the dust brings the water up in the atmosphere. So I will show also more later. So this is something we are investigating, and this is why it is very important to study the dust storm. This is another image that was taken in 2018, where we see the surface here on the left, and we see how the dust storm is raising, is getting very, very quickly here on the right side. And we are also measuring here other local dust storms. Here we can see also another cloud of dust flying very close to the polar cap. So in general, we need to monitor the climate variability, and for that we have models. We have a global climate model to understand how the atmosphere works. And this model is built using data from the planet. And in Mars Express, we have 17 years of atmospheric database of all different molecules, oxygen, water vapor, ozone, dust, temperatures, everything. This is what we're doing year after year, monitoring how the atmosphere works. And then we put that into a global climate model to understand how the atmosphere is working on Mars. Because again, it is the atmosphere that is driving the climate of Mars, that is probably driving the existence of liquid water. So we go then to the next topic, the atmosphere, which is methane. Methane was listed before as one of these trace gases. This is something that is very, very small at the moment in the atmosphere, but it's very, very weird. And there's a whole mystery and controversy about methane currently in the past years, because methane should not be there. Methane, well, is an atom of carbon and 4 hydrogens. And it's a molecule that if you put in the atmosphere of Mars, it should get destroyed within 300 years. So even if someone or something like a comet or an asteroid or whatever brought methane onto the atmosphere, it would disappear very, very quickly in a few hundred years by different processes. The problem, the controversy came in 2004 when 3 different groups around the world detected methane. One of them was the team by Vittorio Formisano on Mars Express, and found this little band over here, which was very controversial, because they claimed that get this thing out. Because they found an amount of methane that was completely unexpected. Again, the models predict that there should be 0 methane in there, and different proposed presence of methane in there at different levels. But why is all this mess about methane, all controversy? It's just a gas. The problem of methane is that the existence of methane has great geological or biological implications. In particular, if we look at methane on Earth, we have a lot of methane on Earth compared to Mars, but this is 80%, around 70 to 80% caused by living microbes, basically. So one of the famous ones, for example, is the microbes that live in the stomachs of the cows. So the cows, the meat industry on the Earth actually is a methane producer. So these microbes live decompose in the stomachs, decompose the grass, basically. The food, and then they emit here the methane to the atmosphere. So these microbes are a known source of methane. The other possible origin is geology. The other origin of methane on Earth is the geology. In some geological processes, can produce methane, although they're very complex to understand. But basically, some thermal subsurface processes can produce this methane if they have water next to it. So in any case, as we know it on Earth, we have methane produced by or geology with liquid water. But these three things, any of these three things would be a major discovery on Mars, because on Mars, at the moment, we don't know if there is life. We don't know if there is any geological activity, meaning active volcanoes or active subsurface geology, or liquid water. Liquid water, we now know there are these liquid lakes very deep in the surface, but we need to understand how these processes work. So, these are some of the theories that could explain the origin of methane. There was that maybe these deep lakes, there's some processes, or either volcanic or hydrothermal processes, or eventually some biological activity that would produce this gas and bring it up through the cracks in the atmosphere. Okay, the story was a shock in 2004, but then we continued investigating. There were a lot of measurements at the time by the Americans, by us in Europe, by our colleagues in Italy. But they were producing maps of methane, but they were very controlled because they were producing very different results. And again, the modelers, the people that know theory, how the atmosphere should work, they were still, are still very strong defending that it cannot be explained. So we had this very hot debate in this meeting in Rome in 2009. Then we had, we needed more data. So we brought new instruments to the surface, and there was curiosity in 2013. And the first measurement they did not find any methane. So, and we saw, okay, this is now this thing. Then they found no methane in 2013, so we thought it was more clear, but then again, more controversy the year after they saw that the methane was there, but actually is even more clear is that we see some peaks in there, and we also see a background level of methane that comes and goes seasonally. This was very weird, and it's not explained. So not only now we need a way to create the methane, so we need either bacteria or some hydrothermal activity, but now we need something to eat methane or to destruct the methane, because by photolysis or by absorption, it does not disappear so quickly. So we need a way to explain this, or to transport this methane around. This is not. This was controversial, but it was also confirmed again by Mars Express in 2019. So we actually observed one of these peaks seen by Curiosity. We saw it with Mars Express as well. We even identified the region where this could come from. This is where MSL is sitting, and we identified that this region is of potential interest because the wind could have transported this methane from these regions to there. So then we now need to see what is going on in these regions. Okay, this is just a model. Again, to illustrate that if we produced some methane in here on the surface, we would see that only after a few days, the methane would actually spread all around the atmosphere. So it is very difficult to explain how the methane would be seen after a few days. So it is very complicated to understand, and no one really understands it further. So the only thing we agreed was that we needed more data. So with the current instruments, even with not only Mars Express, but with MSL, we needed more data, we needed more instruments. Okay, and this is where we decided, okay, let's send another mission. And this is the next step, that is the ExoMars program. And the first mission of this program is the trace gas orbit. So we actually sent a satellite specifically to look at the methane, at the trace gases, and try to find where they are, if they actually are there, to try to prove it, and if they are, where are they coming from? And then the next step of the mission, still for the future, this is the rover and surface platform for 2022. One second. Okay, so ExoMars 2016, this was the first mission of the ExoMars program, and it had, well, a technological objective, which was to test the entry, descent, and landing concept. This was Schiaparelli. This was just a test to try and see if the systems were working properly. And well, we still didn't make it to the surface, but we learned a lot on how the thermal shield, the parachutes, and the attitude control, a lot of details, all the subsystems worked. So we gained a lot of useful information for the next test. Sorry, for the next landing. That's in 2020. And the science objectives, that's what matters for us at the moment, is this mission, the Trace Gas Orbiter. This satellite here that has 4 instruments with the main goal to look at the trace gases and the sources of these gases, if they are and where are they coming from, activity, volcanic activity, the links to life, and understand the chemistry of these gases. And then has 2 other instruments, a camera and a neutron spectrometer, trying to look at the surface and the ice content. By the way, it also serves as a communication platform for ESA and NASA rovers. Okay, so this is Trace Gas Orbiter. This is what I like to call the sunset hunter. So how do we look at the trace gases? The way of looking at these trace gases is looking at how these gases behave with the sun, or how they absorb the light of the sun. The way we do it is we actually observe the sun directly, and then we'll see how the sun goes behind the planet. And with that, like we are looking at the sunset on Earth, or the sunrise, they look at both sunset and sunrise, we can see how the color of the signal changes. Okay, I will wait for the bells 1 second.
Alex, this tells you that your time is up.
But how much time do I have?
The hour is over.
But we have one more, right?
Sorry?
I have 1 more hour, right?
No.
No. Okay, that is great. Okay, that is a very good surprise. Okay, so should I finish with the video then of ExoMars, and then that will conclude?
Please, yes.
Okay, let me just show the video at the end, and just so that we can. Okay, so let's just let you this video that shows all the program ExoMars. Do I have 1 minute to describe it, Michael?
Yes.
Okay. So this was the first launch in 2016. It was done in March 2016, and we see the spacecraft separating from the final stage of the rocket and traveling to Mars. It actually had, as I said before, the Schiaparelli lander that was released onto Mars, although it did not make it to the surface, but we used it to test the technology of the landing. And we have been observing the atmosphere. That is the release of the lander, by the way. And we have been observing the planet and the atmosphere since 2016 now. Then it goes the next step in 2022. It did say 2018 there was the original proposal, but because of various reasons we had to delay it. So we had the rover and surface platform that will be launched in 2022, arriving in 2023. So this is a very complex program because it is in a collaboration with Russia, and we have a Russian launcher and then a European carrier. And then that is the landing platform that is going down there. Of course, the spacecrafts, both Mars Express and ExoMars, will still be looking at that. Okay, that is again. Okay. So we will have two parachutes going down. Damn it. Sorry for that. Okay, here we see the Russian landing platform, which will then bring the rover down to the surface. And the surface platform will also do science and understand how the environment looks in the atmosphere. And this is the rover. Okay, I will go a bit faster now just to go there. This is how the rover will go down of the platform. And the main thing here I want to show is just the drill that will go and collect samples of the subsurface and measure them in the lab. Okay, I'll stop here. And I'm not sure if there's any questions.
Yes, can you see the chat, or should I read it into you?
If you can mention it to me, I need to see.
Yes, so there's a question. Water in Mars disappeared due to the lack of magnetic field, and the dust storms bring water vapor to the upper atmosphere, as I understood. Wasn't the dust generated after water disappeared?
Well, the water was, the dust was probably there also before. It's now that we see it more clearly. Of course, if it had been the water had been there, it would have probably trapped the water in this ocean. But I mean, in general, the answer is that we don't know, and this is why we still need to find out. We still don't know how the dust storms work nowadays. We have observed these features, for example, that they heat up the whole planet and they disturb the climate every 2 years or every Martian year. But we don't know how they worked in the past. We don't even know how they work in the present, so we need to build backwards again.
Yeah, then there was another question saying, so the Gladrats melt and spread the methane in summer.
That is one of the theories that actually could explain the creation and destruction of the methane. This is there is a group in Madrid in the Centro de Astrobiología that is working on this. They are experts in these topics. And this is indeed one of the possibilities that could explain the methane. But okay, I did not get to that. But with TGO, with the Trace Gas Orbiter, at the moment we have not yet observed any methane the past 2 years. After 2 or 3 years, 2 years observing Mars, they have not yet seen a single molecule of methane. So maybe again the controversy is still there, whether the methane actually exists or not.
Mm-hmm. And then we have several questions saying if we can get your presentation, which was really very much appreciated.
Yes, I will discuss offline and put it online with David. Yes.
Mm-hmm. Many thanks. And then there was another question saying, it's a little bit again about methane. Yeah, people are a little bit lost about it. So it says
it's okay. I think that is the right approach. We are lost with the methane,
yeah,
so it is.
We don't really know.
Yeah, we don't really know at the moment.
And the last question is, what about the high-res MRO mission?
Well, high-res is at the moment is probably the best camera at the moment on Mars. The NASA mission. On the ExoMars mission, we have Cassis, which is similar to high-res somehow, and we have on our side the color images produced by ExoMars are equally good. But yeah, the high-res images are very, very impressive. Really, really, really nice. I had some images here about Cassis, but don't really have time to show them now.
Okay, yeah, then really many thanks, Alex. Very interesting. Always for me, also the latest results and a good summary, really. Many thanks.
Okay, thank you.
And so we go to the next point in the agenda, which is now a hands-on session. So now, since we have learned a lot about Mars, I think we have Beatrice, who will go with you through an exercise that you can do with your students in the class. So I hope they have managed to solve problems with the computer.
I solved the computer, yes. This Smartphone is working.
So should we leave now? We have now a little bit less than 50 minutes for a...
Less than 15 minutes, okay.
Let me just check the program. When is the coffee break? The coffee break is...
Less than 15 minutes? No.
No, the coffee break is at 12. So yeah, so we have 50 minutes now for the hands-on.
15 minutes. 50. Okay. I try to take the minute as I swap. I'm going to take the nice background that we all have here. Excuse me. Is this one? Yeah. Okay. So I applied. Okay, super. I'm here. Okay, perfect. So it was super nice. Super interesting. The talk from Alex, and I'm going to start the activity today. Just checking whether you pay attention to his talk. So I'm going to share my screen, and we all together are going to refresh things about Mars that already Alex told us about. Screen 2. Okay. Okay. So do you see my screen? No, I suppose here the PDF.
Yes.
I don't see the chat, so if you can follow that, perfect. Thanks a lot. So as Michael was saying, this activity changed my microphone. Okay, sorry. This one, excuse me, everything. Okay, so as Michael was saying, I'm going to present the Mars season. It's an activity, a CSR scientific challenge created within the CSR team with a lot of help from Alex and Eleni, so experts in Mars Express, and also some checks from ExoMars team. This was also reshaped, let's say, for this Space Science Experience Online that we will present tomorrow with the support of our trainee Elisa. So I'm going to present it now.
Beatrice?
Yes.
But we don't see the full screen, just see the... Can you put on full screen, please?
No, because I want to come back later to
okay, sorry, okay.
Yes, I don't want to play as yesterday that I didn't find what was behind. So it's you don't see enough about it?
No, that's good.
Okay,
sorry,
okay, thank you.
Proceed.
No, it's just I want to easily go later to that. So we present the scientific challenge as a challenge itself. So for students, this would be the way what they have to solve. So the VMC camera that it was already mentioned by Alex, I wouldn't tell you where it is because it's one of the questions. I mean, it is here, located on Mars Express, so it's already mentioned, sorry. It's sending us image of the surface of Mars. ESA scientists and engineers want to program the Mars Express observation to obtain information needed for the preparation of future ExoMars 2022 mission. That, as you were told yesterday, was delayed for a couple of years. It was going to be launched in 2020, but it's going to be in 2022. So ExoMars is going to take observations with VMC data to support. So Mars Express with VMC camera is going to take images to support ExoMars planning. That is going to be launched in 2022. Okay, so could we count on you to help our scientists? This is a challenge for the students. So let's go to observe some VMC data camera. So this activity is also trying to develop the skills for the students that are considered key for 2020, that we were saying is problem solving, critical thinking, creativity, and also we use several phases as we were mentioned before, and it will be mentioned again tomorrow. Also, we follow the scientific method. This is a slide from Rosa, yesterday talk, when they observe and they arrive to their own conclusions and they check whether the initial hypotheses were correct or not. Okay, they work in teams, and here we tell them that they could decide one of the professions that are connected to space, so STEM careers. They decide which ones, they put their names here. And this activity is focused for 12-16, from 12 to 16, this is the target age. And you will see also tomorrow that depending on how many activities you want to run from this challenge, you will spend more or less time doing and preparing. So curriculum relevance is scientific method, rotation of planets, and solar system. And students should already know the seasons and identify features in images, but we will go through that together. They will learn basic properties of Mars, how to handle astronomical images, and the length of a Martian year, and process on space missions. And they will develop critical thinking, as we were saying, and some ICT skills. Okay. So first of all, let's get prepared for the challenge. What do we already know? So similar to yesterday that we were using a Kahoot, I would like that you were typing this Mentimeter, looking for this, and typing this code. And we are all together going to answer the questions. So I don't know whether I'm going to type here the Mentimeter.
The link for the code is not Mentimeter, is Menti.
Yeah, it's Menti. Yeah. Menti.
It's not the one that you're showing, it's menti.com.
Menti.com. Okay, I will put it in the chat.
Menti, if you enter menti.com and then the code.
It is in the chat, yes. Yes, you're right. This is the whole application itself, but yes, it's menti.com. So say yes when you are done, and in the sense of that you have put this link and inserted the code, and we will do all together. Can't see the code on the presentation. No, you can see it. Okay, so it is 7149. I will type it here as well. 7149901. 7149901. This is the code.
Bea, you can share your screen for text and image if you don't have videos to look it better, perhaps.
Okay, I will do that then. So I stop sharing. Okay, now I understand what was happening then. Why they didn't see. Okay, for text and images. Okay, share two. Okay, is it better? Sorry.
Yes.
Okay, thanks a lot.
Much
Thanks
better.
a lot. Thank you very much, David. So when you're ready, we will go through that. You may see something like this. Okay. 18. 23. 24. 24. Okay, so we can already start. How big is Mars in comparison to Earth? You already has both. And you are already voting of several things. Okay. How far is Mars from the Sun? Okay. Okay, the correct answer is this one. Mars is red because the iron oxide on its surface has a lot of saffron optical effect. Okay. 25 people voting. Okay. How much would I weigh on Mars if I am 50 kilos? So the answers. $15. Representation. Okay. The atmosphere of Mars in comparison to Earth is okay. Show correct. Press enter to show correct. Does Mars have magnetic fields? Yes, but weaker than those on Earth. No, but it had in the past. No, and never had. Yes, similar to Earth. No, and that may be reason to be losing its atmosphere. So Alex told us in the past that the atmosphere in Mars is around 100 times less dense than the one on Earth, and it does not have magnetic fields at the moment. It had in the past most probably, but not now, and maybe this is a reason for being losing the atmosphere. How many missions did fail to arrive to Mars? 21. More than half. You were replying. Which of these missions to Mars are led or have a strong collaboration with ESA European? Things that you cannot see. Yeah, press enter to show correct. Okay. The thing is that okay. Present. Okay. What are the reasons for the season of on Earth? Show results. So when is summer in Spain? So we're going to solve this together because it's not sharing properly the answers. And we're going to solve this together now. So you are voting at the moment, and we are seeing your answers here in the Mentimeter activity. And when it is summer in Spain, it is in the northern hemisphere of Mars.
Yeah.
Yeah.
We are listening to you very low. Can you raise the volume?
Okay, sorry.
No.
Now, okay, super. So, as I said, now with what you are doing is you are going through the different questions that were answered by Alex before. And then we want to see the results. Results are hidden and we want to see them. And how would you study variations on the season in Mars? So the questions that you have, if you are going through it yourself, is changing the difference in temperature, looking at the variation of the polar caps, and also you have the option. Okay. Well, for some reason. Okay. For some reason, this is not showing as I want it to be shown. Okay. So the different questions is, when is summer in Spain? It is in the northern hemisphere of Mars. So Spain is in the northern hemisphere. So it is a difference of one season between the Mars, when they are in the same quadrant, between Mars and the Earth. So it would be fall. So how would you study the variations of the seasons on Mars? And you have measuring the temperature, observing the variation in the polar caps, or measuring dust storms. It's the way that we will do it is measuring, in this case, measuring the variation of the polar caps. Also, if you are there, you can also measure the temperature. But for our activity, we're going to do it with the variation of the polar caps. And then the VMC camera is a web camera on board the mission Mars Express that we were saying before. And how long do you think that the Mars year lasts? So we're going to see here your answer. It was not displayed as I wanted, let's say. On board ExoMars. Okay. So, yeah. I didn't see your answers, so I will check it afterwards as I was showing you here on the backside. What did you reply? But with this, you can, I mean, it's configured usually as not presented. It's configured as the students can reply to it on their own. And that way they can see whether they are prepared or not for the activity. So I'm going to put this. Okay. So let's see in the chat, let's tell me whether you think that at least because I didn't see well, whether you think that there are seasons on Mars or not. So if you reply yes or no, it would be already a good answer. Nobody reply? Yes. Yes. Okay. And which of these three options that we were saying you would use to see whether they are the variation in the seasons with the dust storms, the change in temperature, or change in polar caps? Polar caps, ice cap, polar caps. Okay. Okay. And the last polar caps. Okay, this is the way we are going to do. We are going to use VMC data from ExoMars, and there we're going to see the variation during the seasons. I mean, during a whole year, checking the polar cap size. And the last question before going through that is, how long do you think it lasts a Martian year? Wow, this was from Google straight away, not 2 years. 2 years. 2 years. Most probably Alex already mentioned 600 years. Okay, so all these are your hypotheses. So we are going through the tool itself and we're going to calculate it. So the Mars seasons, so the seasons is due to the Earth is tilt respect to the sun and it's rotating around. And also for Mars is a similar situation with a different tilt, 25 degrees and 20 something degrees, 23 degrees. Okay, so let's start the challenge. For the challenge, as I said, we are going to use a web tool. And this web tool is here. I don't know whether you can click here or I will add it to you in the chat. I will add this to you in the chat. That's why I had it behind. Okay, this is the link. This is the link that we're going to do. Okay, so what are we going to do here? We have the season on Mars and we have several steps. It has been developed by the SalsaJ team. And we have here, if you click here, we have some images from the southern hemisphere of Mars collected by the VMC camera. And here you have some from the northern hemisphere and another ones from both hemispheres. There is a selection of them. And we are going to, first of all, what we have to do here is to identify the different seasons. So pick up one of the hemispheres yourself and try to let's pick up the northern one. And then you need to click to see whether this image corresponds to summer, spring, autumn, or winter. And the same for the other two. So for example, the first one, what do you think? It's we cannot differentiate it between spring and autumn in these images because we don't see from where it comes. So whether the polar cap was bigger or smaller before. So right here, which from what season do you think is the first image? From winter, winter. Winter. Okay, before you continue saying winter, I must tell you that winter is not very visible for us. So there's not much light. So here is quite some light in the images. So it's a bit shadow when we have winter. So if it's not winter, what other do you think it could be? This image about? I mean, what season may it be saying? May it be showing? Summer? Well, so we were here. Autumn, yeah, it's more about autumn, no? Because summer may be more here, no? More this smaller size. Autumn, okay. Spring or autumn, no? Any of the two. We cannot differentiate. Okay, so let's go spring, autumn. This second one, what do you think is showing? If this is summer, that we said is summer, this, what would it be? Summer or spring, autumn? The same. Summer? Okay, check. Wrong. So this is not correct. Most probably this is not the correct one. So if it's not summer and it's not winter, autumn. Okay, autumn or spring, as I said, we don't know because it doesn't have a number, so we don't know from where it's coming from. Okay, so let's check it. Okay, so this is correct. So now from the VMC images that we had stored in our database from the Mars Express mission, we can identify different seasons. Okay, so now what we have to do is we want to know how long a Mars year lasts. For that, we have also a selection. Here, what you see is 16 is the year, is 2016, and 60 is the day of the year. No, so if January has 30 days, 31 days is 31 plus 29th, so 1st of March, no? And here is the same. 17 is 2017, and 100 is the day of the year. So following this, he said, select a set of 6 images covering an entire Martian year. So we need to pick out 6 images covering what we think is a whole Martian year. We need to select all of them from the same hemisphere. These magnifiers are telling us that they are from the same hemisphere. So here is from the southern hemisphere, and this pink is from the northern hemisphere. Because a way to identify a Martian year could be, for example, to measure from what we consider summer to what we consider summer. Because spring and autumn is not distinguished in principle, and the winter doesn't have, is not much illuminated, so we haven't added many winter images here. So we need to pick at 6 images. Are you following this? Are you doing this yourself with the tool? I type again here the tool. Yes, okay, super. Okay, so as we were saying, you can come from any of the previous points, so northern hemisphere, southern hemisphere, and you come back here where you have a mix of the two. Okay, so if we want to select 6 images, let's look at it. This we don't see much, so these two we are not going to use them much. They may be winter, we don't see them well. So we have here the polar caps, a variation of the polar caps. And most probably we have more images that varies that we can measure from summer to summer here in the northern hemisphere. So I'm going to pick up this one, and I'm going to pick up these 2. So these 2 are my, let's say, external points in time. And I see some variation here. 1, 2, 3, 4. I can select 2 more. 5. But I already mentioned that for me, these are the 2 external points. And an extra one, this one. Okay. So select image from the same hemisphere. The size of the poles vary according to the season. Use the magnifier to check the images. Okay. So we go and we check it. So now what we should do here, we should type ourselves, which is what do we think is the length of a Martian year from the images that we have, because most probably it could be longer or shorter, but we have the selection of data that we have here. So if we go to this is the first that I selected and the second one, that's why they are at the extremes, let's say. So this is day 60 and this is day 288. So, but the year is different. So we can say that we have here 365 plus the 228. No? So let's do it quickly. Let's do a calculator, very easy. I know it's very easy. 365 plus 288, 653. This is what I get here, 653. And I'm going to check it. Okay. So it's well done. You have an error already of 5%, because what was done here is with the data that you have, and then the real number is 687, as someone wrote in the autumn should be smaller than the spring because the spring comes from the winter with a bigger polar cap. This is a question for Alex. If Alex is around, the autumn should be smaller than the spring because.
Hi, yeah, I was actually reading that, and it is an interesting point, but I don't know the direct answer. I would need to check. It does make sense, but I'm not sure.
Yeah. So from these images, we don't differentiate the 2 of them. But we saw, and we can come back. So we were saying the Martian years, the Martian year lasts 687 years on Earth. So now I would like that you write on the chat, how old are you in Martian years? As we don't see your face, we don't mind. What do you mean with the bigger polar cap? Okay, so let's come back. This is, he's trying to answer to you, Jorge. 25. So Jorge Hernandez will come back later, and he's also our expert in the VMC data, and is trying to answer the question whether the autumn should be smaller than spring. So you can do it later on your talk, or once that the teachers answer about the age in Martian years. And we can come back here and see whether we see any difference. This is for the expert. This is, yes, okay, we can speak later about it. Okay, so as I was saying, how old are you in Martian years? This is what we already have done. 70s, 12.7. Okay, 21. Okay. Okay, we have already done this. In the teacher guide and student guide, you are guided through this. And now we want to do a collaborative activity. And but for that, we want that you take into account that the some factors let's speaking about it in a rough way. Let's say in a I mean, not very precise, but these are the things that happened in summer, in the summer northern hemisphere. The climate, you have mild temperatures, you have winds, the atmospheric pressure is higher because of the temperature. However, in the winter, in the southern hemisphere, you have temperatures up to minus 130. The carbon dioxide is in the atmosphere is frozen, and I mean, and it's less temperature, so it's less pressure. In summer, you can detect dust storms, and also you can mainly when you have the summer in the southern hemisphere, because of the image that we saw before, the image on the Mentimeter, the image on the here, for example. You have here this is the northern summer and this is the southern summer. So the sun is closer, and so the most probably Jorge, that is an expert on Mars, will explain about it later on. But we have more dust storms, even if they are not very, they are comparable to some breeze on Earth, but they are stronger. So the question here is: imagine that you are living on a part on Earth, on the southern hemisphere or the northern hemisphere. So if you click here, and I'm going to put this also in the chat, it's going to be open here. The idea is, imagine that you are at the moment, or you are going to Mars. And ExoMars, we were saying that is going to, you are part of the crew. And ExoMars is going to land on 2022. We know it's not a crew on it, but imagine that you have to define what would you find when you arrive to Mars. So what do you need to do? If you live in the northern hemisphere, you would imagine that you are arriving to the northern hemisphere of Mars, and that you know that the trip will last 6 months, more or less what was mentioned before. So what would you find on Mars, on the same hemisphere that you're living now, but on Mars, when you arrive, if ExoMars is leaving the Earth on September 2022? So I'm going to put this in the chat so you can answer to this question. Because it's not loading this. Okay, so I will put the link in the chat for you to edit yourself. Okay. Okay, thank you, Lisa. You already put it there. Perfect. So if you open this is what we want you to answer. Is your name, where you live, whether it's the southern or northern hemisphere on Earth. This will be your reference for Mars. When you land on Mars on the same hemisphere. And if ExoMars would be launched in 2022, when you arrive to there, that we were saying before is 6 months difference, what would you find? Taking into account these factors. Taking into account this, that in summer, on the northern hemisphere, you have this climate and this dust and this variation in the polar caps. And in winter, you have these other ones. Okay, make this smaller because we don't see you all. I want you to see this. Okay, I'm going to close this one. So we were saying that the climate in summer on the northern hemisphere, you will have mild temperatures and dust storms and a reduced size of the polar cap. All of you are saying that storms. You arrive to the northern hemisphere. So they are stronger in the southern hemisphere, but there are some. Mm-hmm. So the polar cap in the southern hemisphere lasts during the whole year. Ice cap. Maybe Alex, you or Jorge could help them on this. If you arrive from summer to the northern hemisphere, what would they find? So the difference we were saying at the same quadrant between Mars and Earth is one season. So as you were saying, correct, that if we go in spring, we will arrive on summer. Okay, and that was all from me. This is the VMC, the calculation, identification of the seasons, the measuring of the Martian year. How old are you with the Martian, in Martian?
Hello, Bea, are you still there? Bea, we don't hear you. Hello, Bea?
I also don't hear her. She might have problems in her computer.
Yeah. So since anyway, I think she has finished. Also, you wanted to have some moments before the coffee break. No?
Yeah. That is very quick. I just would like you to go to the space where we are sharing all the materials with you, your grasp link. And you will see that we have turned on again a new folder called Image Processing with SalsaJ. And you have again there the link to download the SalsaJ software. And you also have the link to the instructions on how to install the software, which was already available to you. But now you also have a link to the images that we will be using during our session this afternoon. So it would be really very nice if you can go and download it all. And if you have any problem with the installation of SalsaJ in your computer, please stay when we go for lunchtime, and I will stay behind to help you with that, if that is the case. So again, there is a new space called D2 Image Processing in the campus, in the ESA GTTP 2020 campus on Grasp. You will find all the instructions you need and all the links that are necessary for this afternoon's image processing software session. Make sure that you go there and check, and I will be here waiting for you. Michael, I also see you don't see my image, do you?
No, I don't see
Yeah, so there's clearly a problem with the platform, maybe. Okay, well, I said it. You heard it, right?
Yes, we heard you.
Okay, good.
Okay, Bea is again back. Bea, but we don't hear you. No, Bea, we don't hear you. No sound. We cannot hear you. So we have to fix this over the coffee break. Okay, so I would say I thank you very much, Bea. I don't know if you can hear me. So let's go into the coffee break, and we are back at 12:15 Central European Summertime, please, for the activity with Sandra, creators in the classroom.
Michel?
Should I start?
I don't see Michel here, so maybe we should get started with the new part of the program. Let me just open it here because I don't remember by heart the name of Sandra's session, but we're going to have now a very interesting hands-on session that is related to creators in the classroom and DNA activity. So I hope you have the materials prepared. We know that Sandra was shopping to the preparation of today's session, so it certainly is going to be lots of fun. So Sandra, the floor is yours.
Okay, thank you very much, Rosa. It's a pleasure to be here with all of you, and I really hope this session will be useful but also fun for you and later for your students. So as you see here, I'm surrounded with a lot of stuff. And what I wanted to present to you in this session are two experiments that are very easy to carry out, with also easy to find materials that you can find at home or in the classroom or at your school maybe. And they serve as motivation to the students to engage them with science. So since we are talking today about Mars, we will relate these experiments also to the red planet. But first, before starting, let me just share my screen to see if everything is working. Okay. Can you see my presentation?
Yes.
Yes.
Okay. And you can hear me okay?
Yeah, perfect.
Okay,
Yes.
thank you very much. Okay, so we are going to do two experiments. One is called Craters in the Classroom, and the other is related to DNA extraction from tomato cells. So the idea here is that the students are going to learn about science by doing science themselves. So they will become astrophysicists or astrobiologists for one day, and they will discover some interesting aspects about our universe. Related to craters, they are actually something we observe around the solar system. They are very common, and they are a very interesting laboratory to understand some physics and also some other areas like chemistry or biology even. So the idea is that the students will follow the inquiry-based approach, the inquiry-based learning that Rosa already talked about yesterday a little bit. And of course, I'm not going to do the full inquiry-based activity because it will take a lot of time, 1 hour each of the two activities that I'm going to present, but you have all the details in the GRASP platform and also in the materials that I will later add to this platform. So impact craters, as I was saying, are very common actually. There are geological structures that we found on the terrestrial planets, on the rocky planets, and also in the moons of the outer planets, in the outer parts of the solar system, around the giant planets. We are talking about impact craters because actually there are other types of craters that maybe can form when we talk about volcano, for example, when the caldera is forming, but here we are referring to impact craters that are formed when an impactor, an asteroid, a meteorite, a comet strikes a rocky surface, like Earth, for example, or like Mars. And we can see them in different places. Here you have different pictures, for example, in Mercury, in Mars, in Venus, in some Saturn's moons, for example, like Mimas, and of course also here on Earth. On Earth, things are a bit different because here we have weather, we have erosion, we have atmospheric conditions that make that many of these craters are actually covered up after millions and millions of years, and they are hard to identify. Although we have some very beautiful examples like the Arizona crater that you can see in this image, That is a spectacular place that I actually had the chance to visit some years ago. It's really, it froze in the surface, right? You have the structure of the crater untouched, and it's really, really beautiful. But you can find craters in many places around the solar system. So they are really interesting structures to study for the geologists, but also for the astrophysicists. So how do they form? We were talking, we have an impactor that will strike a surface, and it will release a huge amount of energy. And a lot of the material that is in the impact area will actually come out, will be ejected from that place, sometimes to a very long distances. Here you see a very nice picture of the Tycho crater in the moon, and you see this huge rays, this ejecta rays, that is material that came out, was ejected, probably at very also high speeds from the impact site. So you can see sometimes really kilometers and kilometers of these ejecta that have been ejected from the place. You can see the structure a bit better in this diagram. When you have the impactor striking the surface, what is happening is that the first layer of the surface is actually melting, and there is a shock wave that propagates in the subsurface, in the other layers. But at some point, because these are dense materials, this shock wave is going to rebound and come back again towards the surface, and then it's going to produce, at the end of the excavation stage, what is called a central uplift. So you can see this structure in many craters, especially the larger ones, larger, maybe they're 30, 40 kilometers. You have different structures also within the crater. You can see the rim. The rim is basically this ring-shaped structure that forms around the impacting area. It's always a circle. And this rim can have very steep walls that are really, really high and really steep, or sometimes also form some, what we call some terraces, as this one here. So here you have the final crater, the final structure of the crater, and surrounding the rim, what you find is the ejecta layer. So all this material that was below the surface has now been deposited around the crater. And this is very interesting because it allows us to actually study the composition of the surface of the planet we are studying, or the moon that we are studying. So why it's important to study craters? Because we can understand better the composition of the place where the impact occurred, and we can also determine the ages of the different layers of the surface. Basically, because all their surface will be exposed to impacting meteorites for a longer period. So we may find that in this ejecta, there might be other impact craters as well. And then we can determine how craterized a surface is, and we can try to estimate the age of that particular part of the surface. And these are ideal places to look for traces of, for example, water, organic components, and maybe even life. So that is why, for example, in Mars, there are many rovers, and we heard yesterday all the missions that are actually in Mars, exploring the surroundings of Mars. And some of these rovers are actually located at some craters. They are looking for water, and they are looking for evidences of maybe life, maybe probably not current life, but maybe past life. So, for example, here you have a picture of the NASA's Curiosity rover, which is located actually at quite a small crater called the Gale crater, which is here close to the Martian equator, here where I have my finger. I hope you can see it. Here I have a topographic map of Mars, which is very cool because I can see the different heights in color in the Martian soil. And the Curiosity is just right here. Going around and inside the crater, taking samples of the soil. So what are we going to do now in our experiment? What we are going to do is try to recreate a particular surface, and then we are going to model and recreate the craters, how they form and the shape they have. And for that, we need all these materials, as you see, very basic materials that you can find everywhere. I have already prepared a little bit. Basically, I have a plastic container, a plastic bucket in a square shape, okay? That is transparent, that is important, so the students can actually see what is going on. And that is also large enough so you can actually drop objects on it. And I have used 3 kilograms of flour, okay? So if you like cooking, you probably have that at home. I don't like cooking so much, so I had to go shopping for that. And you are gonna need also some cocoa, okay? Because we're gonna put over floor, maybe 7-10 centimeters, depending on the size of your bucket. And then you're gonna add a little bit of cocoa. You're gonna spread a little bit of cocoa, basically because we want to see the effect of the ejecta once the impact happens. And if you have a contrast in the color of the different layers, of course, you will see it more easily. You will need a ruler, a scale, and a stopwatch, okay? So, and of course, sorry, I didn't mention, you need the impactors. You need marbles, balls of different sizes, okay? I have here another container with different impactors that they have different sizes, different densities, okay? They are made of different components. And with this, we are gonna try to understand what is the shape and what are the characteristics of the craters formed in our model surface. So here you have the step-by-step, all the steps of this experiment. It's important that you divide the students into groups of 3-5, more or less, so all of them can actually interact. And before starting anything, just when they have the surface here recreated, they first need to think a little bit about what is going to happen. So they make to do some predictions, what they think is going to happen when they start dropping the different objects in our surface. Because this is one of the principles of science, the methodologic method, right? The scientific method. So we need to first come with our own prediction of what is going to happen, and then we are going to test it. We're going to propose some hypotheses, and then we are going to test them. So let your students hypothesize what is going to happen, and then let's conduct the experiment. As I was saying, you need about 10 centimeters of flour, only a little bit of cocoa, less than 1 centimeter. And then we are going to use the ruler in order to be able to identify at which height we are actually dropping the different objects, okay? For example, here, it's a height of 40 centimeters, which is okay. You can try, if you have a bigger ruler, you can go up. Ideally, you will try different heights as well, okay? Okay, so you probably know what I'm going to do now. I'm gonna choose 3 impactors, more or less of the same size, with different weights, with different densities. For example, this is a heavy plastic marble. This is a very light ping pong ball. And then I also have an intermediate ball made out of wood, okay, which is not as heavy as this one and not as light as this one, okay? So it's important that when the students are working, one is taking also measurements of the time that the impactor is taking to actually fall this distance, this height, okay? So that's why we need the stopwatch. So one of the students will drop the projectile, the other one will actually measure the time. Maybe the third and the fourth one will actually take data of the crater itself. Okay, so let's go there. I'm gonna try to do it. Do you see me? Just 1 second. I'm gonna stop sharing my screen so you can actually see me better. Just 1 sec. Because probably now you are seeing me very small.
WebEx has the possibility that you can also have the slides and the speak at the same time if you can make the window bigger.
Okay.
But it's better if you don't need the slide. It's better if you stop sharing the slide.
Yes, I think I will stop better. Then I will come back again. So now you see me a full screen, right?
No, but the people we have to select instead of the view where you see everybody, that you see just the speaker.
Okay.
So this is everybody. You have on the right side 3 small icons on the top where you can see the active speaker. If you click, or you can see everybody. So you have to click on the first icon which says active speaker video view, and then you see Sandra big on the big screen. And then if you want to go back to see everybody, you can click. There are 2 more icons where you can see then the other speakers in small, or you can see everybody in a mosaic. So now for seeing what Sandra is doing, I recommend that you choose the option active speaker video view.
Thank you so much, Michel. I actually am trying to do that as well, so I can see what I'm doing, but for some reason it's not. I cannot. Let me just check 1 second. I see myself in small size.
Yes, that's the problem. You see yourself in a small window on the right bottom. But we see you big, so all other people see you in a full screen if you choose active speaker video view.
Okay. Yeah, orador activo. Okay, perfect. Okay. Well, then let's go. Let's go for the experiment. As I told you before, I have 3 different impactors. I'm gonna choose a height of 40 centimeters. And let's go there. I will do it myself, and then I will bring the camera so you can actually see the different impacts, okay? So this is a lot of fun. I get nervous when I do this, I don't know why. Okay, let's do 1. Wow, that was a nice crater. This is the wood ball. And this is the lighter ball, okay? So I don't know if you saw it, but this actually didn't penetrate much into the soil. Okay, so another important thing is try to destroy as less of the crater as possible when you actually take out the different objects, which is actually quite tricky when the ball is heavy and it's really deep. Actually here, I think I'm gonna leave it like that. Okay, so now let me show you what was the result. Just 1 minute. Okay, can you see the packet?
Yes.
Great, so you see the craters that I just made, okay? And probably just with a visual inspection, we can already know which one, of course, had a higher density. I didn't touch it actually because I didn't want it to destroy the crater. But you see here, this ball penetrated really a lot, and it created many different rays of ejecta. So it actually excavated a lot inside the surface, and all the white material actually came out and formed the different rays. On the contrary, for example, here you see the crater that the ping pong ball created. So really, it didn't penetrate it much. You can actually not see most of the white surface. You still see the cocoa, okay? So the depth is not very high, and the wood crater is somehow an intermediate between the 2 of them, okay? So I'm gonna do now same exercise from this point of view. For example, with a bigger projectile, with a tennis ball from 30 centimeters, more or less, okay? So here we go. Okay, nice. So you see, it also is not as deep as, for example, the marble one, but of course it's bigger because you have a bigger impactor as well. And you also see some of the ejecta. Okay? So you see how easy it is for the students only on a visual look, in a visual inspection, to already have information about the shape and the characteristics of the craters. So now the students, once they have the different craters created, they can use again the ruler and actually measure the diameters of the different craters and also the depth of the craters. Because then we are gonna, since we are scientists, we are gonna collect all this data and we're gonna use them to make some calculations. I'm gonna put the camera again in his place. 1 second. So here I am again. So as you saw, very easy to do, something that is really fun and that your students can actually have some practical taste of different measurements that they can actually conduct. I'm gonna share again my screen, just 1 second. Okay. Okay, so this is the type of table that the students can actually now create with the data they have collected. Of course, if you are working with primary students, you may stop here and just have them describe with words what they are seeing and what they think or how they think. For example, the shape of the craters is affected by the different parameters that we have already discussed, like the size of the impactor, the mass, the density, but try to do it in a lighter way so the primary students can also actually have a grasp of what is going on. If you're working with secondary students, you can go a bit further. You can have a table like this one or the one that you actually consider better, where you have the data of all of the impactors that you have to measure before. Okay, you have to calculate the diameter, measure the diameter, and the mass. That's why we need a scale. You remember in the list, in the previous list, we had a scale. So you need to have this data of your impactor. And then you take the time with the stopwatch. You try maybe different drops, okay? Because again, we are scientists, so we are repeating everything several times so then we can have an average estimate of our calculations. This is only a picture, but I put in the presentation a link to a Google spreadsheet that you can actually use for the activity. And you can also, all of you, put your data there so we can also share among us what are the findings that we are finding, the results we are finding. And you can also do cool things like this one. You can, if you have a slow motion camera in your mobile phone, you can actually record it. And this is something that is really cool to see how actually the impact is happening, how the energy here makes all the excavation, all this part of the surface to go actually out. And then you see again the different ejecta. So I really like this type of slow motion, and also the students can actually make them themselves and then bring them home, show them to their families, and it's a lot of fun. Perfect. So then I leave you here some questions, open questions for the students to reflect. So once they have collected all the data, they have to reflect on them and try to understand what is happening, right? So what is happening, how is the shape of the crater related to the size of the different impactors and to the density, also with the height, what is going on with the height. This has to do also with the energy with which the impactor is actually arriving at the surface. So how is this affecting the shape of the crater? And also the ejecta, because the ejecta, as you saw, with this ball that is very light, there is almost no ejecta. But for example, with the tennis ball or with the heavy plastic marble ball, you have a lot of ejecta. So they have to reflect on these kind of parameters. And if you want to go a step further, you can also actually calculate the kinetic energy of each of these impacts, because we have measured the time that it takes for the ball to travel a certain distance. So we can actually calculate the speed, and we can approximate that to the mean velocity, and then we can calculate the kinetic energy of the impact. And maybe you would like to do some scatter plots to demonstrate your results. You can actually correlate all these parameters with each other, but maybe it's interesting, for example, to make a plot of the object density or the diameter versus the diameter of the crater. And of course, the larger the crater, the larger the impactor, you will get a larger crater. Or you can also correlate it with the depth, for example, and also the velocity that you calculate. Right, so this is one of the experiments that I really like a lot. And as I said, I have done this with different educational levels, different ages, and it always works really well. It's in your hands to adapt it as better as possible for the level of your students. If you are not allowed now to have groups because of the situation of the COVID, you can always use an online tool that is really cool. It's called the Impact Calculator, from this amazing project Down to Earth. And I'm actually going to open it very quickly so I can show you how you can actually model the same that we have done here, but you can actually do that online as well. So I'm just going to, share now my browser. 1 second. Here. Okay. So here is the website of the impact calculator. You can actually choose if you are on Earth, on the Moon, Mars, and you can actually model the different craters in those different surfaces. Since we are talking about Mars today, let's go to Mars. Let's start. You can actually choose your language here. Okay, so you have a list of languages. You can select them here. And as you see, you have already in this screen, you can select the projectile diameter. You can also select the angle. I haven't talked about this, but of course, the angle in which the impactor is going to impact the surface. It changes also the amount of energy, and it changes also the shape of the crater. So here is an easy way to model the angle. You can also change the velocity. And the interesting thing here is that you can model, for example, the density of the impactor, which this we can do with our hands-on experiment, but you can also model the target density, so the type of surface in which the crater is going to be printed on, okay? So let's do this. Let's select something like very big, like for example, 15 kilometers, which are actually, these are quite rare, such a big impacts, but we know that from time to time they may happen, and actually it's supposed to have happened 65 million years ago, when the dinosaurs were extinct. So sometimes we know these kind of impacts happen. Let's now, for example, put, I don't know, 50 degrees, for example. And we are going to change the velocity, 40 kilometers per second, which is actually a lot. And now we are going to say that this iron, okay, we wanted to make a big crater, a big impact. And, okay, here we can only select igneous rock. But I have seen other options here as well. Okay, so now we submit. And the program will give us the resulting crater that we will obtain with these initial parameters and initial conditions. Sorry, my connection is a bit slow. So let's hope it doesn't take much time. I'm just gonna use the cable Just 1 second, I'm sorry. Let's try to go back and submit again to see if we can get the result. Okay, submit. Okay, I think I have everything. No. Giving me some errors. I don't know why. Let's try again. Now, it probably works now. Okay, here we are. So here we have our impact values. We have the depth of the crater. You see almost 1 kilometer depth. That's really a lot. The width also really, really big, 54 kilometers. We have other parameters here. And now we can actually place our crater in the surface of Mars. Here we are in Mars. It's the same image that I have here. So here in spherical, and here you can see as a plane. And you see the kind of impact that is actually happening. So here you can also move around the surface and locate it anywhere you want, for example, here. Okay. If you do this on Earth, remember we're now on Mars, if you do that on Earth, you can actually target a city and you can compare how big the crater is with a particular city. For example, I would do that with, I'm from Madrid, I may do that with Barcelona, for example, just for curiosity, So it's fun. You can also do with different cities, so you can actually compare how big your crater will be in comparison with a particular city. And you actually here have also the option of crater depth, where you can actually select, for example, the Eiffel Tower, and then you can see how big your crater is in comparison with some of the...
Was kicked out. Yeah.
Good. I was like, oh my God, was I talking alone?
No. It seems that, it seems that everyone was kicked out. So just wait a little bit. People are coming back.
Sure. Okay, I will just wait.
It happens. It's okay.
No, but it's good that I was afraid I was talking alone for some time and I didn't realize.
No. Great. Maybe one of the hosts or co-hosts just accidentally clicked on the close meeting button. It's okay.
See when I was telling about the impact calculator?
Yes, we did.
Great. Awesome.
Okay, maybe you can continue. I think slowly people are going to come back again.
Okay, perfect. Yes, so I was saying just before we got out from the meeting that there is a lot of things you can add to this activity, to this workshop, that I will not go into details because I want to present the other activity. But there are many different versions online where you can actually use even the materials that are already prepared. For me, a very good repository is Las Cumbres Observatory. They have a lot of activities, and one of them is this one. It's described in full detail. Well, now we are going to go to the second part of the session, to the second activity, and for that I'm going to share again my presentation. Great. Here we go. Because I told you already that craters are very interesting places to look for maybe organic components, organic material. And what is the key of this material, of this organic material? Of course, DNA molecules. Okay? So you can tell your students that we are going to reproduce an experiment that is actually going to be used in future missions on Mars by these rovers that are actually collecting materials there. Of course, we're going to do an analogy. It's not exactly the same experiment, but it's something similar that the rovers are going to be able to do in next missions, for example, the ExoMars in a couple of years. So these rovers will bring inside small laboratories as the one I have here. Of course, they will have sophisticated instruments, but basically they will have some chemicals that will be used to identify organic molecules in the soil they analyze. And the aim, of course, is to detect current probably not current, but especially past biological activity in the soil of Mars. And as I said also, DNA is the king of the molecule, so it's a very complex molecule, has a big size, and is the basis of life as we know it. So it's one of the key molecules to look for. Well, what are we going to do? How are we going to detect DNA? Because as you know, the DNA lives in the nucleus. This is very efficiently packed, very well packed inside the nucleus of the cells. So we are going to use some chemical components as, for example, salt and liquid soap in order to break those cells. I'm just going to put my small laboratory a bit more at hand. Okay. So we are going to use salt and liquid soap in order to break the cells, the external wall, the external membrane, okay, and also the internal membrane of the nucleus, okay? So once these membranes are broken, then we're gonna have the DNA material floating around, and then we need another chemicals in order to preserve it so it will not disintegrate, and isolate it so we can actually see it, okay? And for that, we will use baking soda and alcohol. So as you see, very easy to find components that we all have at home. Here you have the full list of materials. I'm going to do the experiment with tomatoes, but actually you can use any fruit that you want. I have seen experiment done with strawberries, for example. It's important that it's a fruit or a vegetable that is not very hard, so you can actually break the cells easily. The tomatoes are very good for that. And what you need to do before the experiment is to actually mix the tomatoes and strain the resulting juice in order to obtain our tomato extract, which I have already prepared here. Okay, so I have my tomato extract here. What else are we going to need? We're going to need what I just told you, the fat-breaking solution. Why fat-breaking? Because the membranes of the cells and of the nucleus are basically made out of lipids, okay, which is basically fat. And that's why we are using actually the soap, because it's attacking the lipids. Okay, so for that, for the fat-breaking solution, we're going to use water, liquid soap, soap, salt, and the baking soda. I have already prepared it here as well, okay? But in the next slide, you have the quantities that you need to make this solution, okay? So we need basically 200 milliliters of water or less. Here I have only 300 milliliters. It's more than enough. And then you will need to add 2 small tablespoons of salt, okay? And 6 small tablespoons of the baking soda, okay? So the baking soda and the salt. And then you need to pour a little bit of fairy, or the fairy of the liquid soap that you're using, and then mix it together, okay? Great. What else would you need? What other materials would you need? You need the alcohol, I already mentioned. And then in order to actually have our sample, we're gonna need some glasses, ideally transparent plastic glasses. We are gonna need 1 test tube that you may find maybe in your school's laboratory. We're gonna need pipettes, something you can find in a pharmacy. A graduated plastic tube with thread, like this one here. So you have here the scale, okay? And gloves. It's very important that we actually use gloves for this experiment. So I'm already going to put them on, because we don't want to contaminate the sample with our own DNA material, of course. So let's do this. Of course, you can imagine the emotion in the students when they are actually becoming chemists and biologists, and they are using the gloves and doing this in a small laboratory. Great, so I'm gonna stop sharing again so I can actually let you see better. Great, Let me just take my notes where I have the different quantities that I need to mix up now. Remember, we have our tomato extract, okay, that is already strained, okay, and we have our fat breaking solution. Yeah, I think you can see it better. Great. Now we are going to take 2 pipettes, okay? One is for the tomato, the other one is for the fat breaking solution. It's very important that we do not mix up both of them. We are going to take a plastic glass, and we are going to pour 3 milliliters of tomato extract into the glass. 1, 2, 3. Okay. Can you all see what I'm doing?
Sorry, Sandra, just to remind the participants that they can change the view to see only you. It's on the top right corner, the second, the inner circle. You have active speaker, and with this we can see you in a bigger window.
Yes, that's important. Yes, thank you very much, Naira. Yeah, it's better if you can see on big screen what I am actually doing. Okay, let's check here. Okay, perfect. So 3 milliliters of our tomato extract and 6 milliliters of our fat breaking solution with the corresponding pipette. So 1, 2, 3, 4, 5, and 6. Perfect. Now we are going to mix it up. So now what is happening here is now that the tomato cells are encountering the solution and all the membranes are breaking. Okay, so now we have a lot of free DNA material here. But of course, we don't see anything. What we need to do now is to use the other components in order to isolate it and actually be able to observe it. So we mix it a little bit, perfect. And now we are gonna use one of the clean test tubes. And from this mixture that we have just prepared, we are gonna take 3 milliliters using the pipette of the tomato. This is very important, okay? And we are gonna put it in the test tube, trying that we don't touch with the liquid the walls or the edges of the test tube, okay? Great, so let's go. 1 milliliter, 2, 'Okay, and 3. Great. Now this is our sample, okay? And now comes the tricky part. We must have prepared the alcohol beforehand in this graduated tube. Now we need to pour the alcohol over on top of our sample, but we need to do that in a very gentle way, okay? So the mixture will not become turbulent. If it happens, no worries, but you will have to wait for 5 minutes approximately in order the turbulence to cease and to be able to actually see the DNA molecules. Okay, so let's see how this comes out. I hope you can actually see it. I'm gonna try to pour it as slowly as possible. Some alcohol may actually come out from the tube. So that's why you always need to protect the surface in which you are working, okay? Great. But now you can see here, we have the sample and we have the alcohol on top. And in a minute, you will see there is some white cloudy stuff forming in the interface between the sample and the alcohol. This is the DNA. And because it's less dense than the alcohol, soon it's going to start going up and it's going to precipitate towards the upper part of the sample. Okay, so those are your DNA change. Of course, it's not only one change. Here we are looking at millions and millions of DNA change. I'm just gonna go closer to the camera. Hopefully you will see. Now you saw that many of these white substance is going up. These are your DNA change. So you can see how easy it is to isolate DNA, and something quite similar is going to be used by these different rovers when they arrive to Mars and they actually examine the soil there. Okay? I have one that I did before, so maybe you can actually now see it a bit better. Here I had many more cells, so you actually see this substance much thicker. Okay? And what you can try to do is actually to fish it up and try maybe to analyze it with a microscope that you have at your school. I've also seen other recipes where they actually freeze the alcohol. So when they pour it into the sample, the viscosity is going to change and it's going to be less liquid and a bit more solid. So actually it's easier to take it out and maybe put it into a microscope, okay? But there are different recipes that you can use. In the internet, there are also many different examples, but I like this one because it's really easy. You don't need to do anything, just have your components ready. And then you can see it actually very, very clear, the DNA material. Great, so just to finalize, I'm going back to the presentation just to share with you a couple of things. Here we are. Again, here you have the step-by-step. You can check it out later. If you didn't have the components to do it right now, maybe you try at home during the week and then maybe take a picture and we can maybe put it in the social media if you like, of course. So here you have, again, pictures of what you are supposed to be looking at once you pour the alcohol. Okay, so all these material are your DNA change. Okay, also here. Great. Of course, you can also do this, I already mentioned, with other fruits, or you can even use your own saliva, for example. You can use soil from your garden, anything that may have organic material. And I like very much this experiment for the reason that it's very easy to do, that you are talking also about different areas in astrophysics that I really like a lot. I like that astrophysics, astronomy is very multidisciplinary. So we have now also biologists coming to work with us in order to be able to assess something so important as if there is life in other places in the solar system. So I really like this activity because you can talk about a variety of things. And you can also talk about one of the greatest minds of the past century, which was actually Rosalind Franklin. And she is not really well known by the scientific community. She was actually the person that discovered the structure, the double helix structure of the DNA molecule. She was a British biochemistry and she was a specialist on a technique that is called X-ray diffraction, which is the technique that crystallographers use actually to understand the structure of the atoms. And she was really good at this technique, and she was analyzing different components, one of them the DNA molecules. She actually discovered there were different types of molecules, type A, type B, and she studied for many years their composition and their ordination inside the molecules, so how they are actually ordered. And what happened to her is probably one of the most controversial episodes in history of science, because she took this famous picture, the 51 photo, where you can actually clearly see the double helix structure of the DNA molecule. She didn't publish it right away because she was working on the theoretical model in order to be able to provide a full explanation of the molecule. But she actually was writing some stuff on the experimental work that she was actually conducting. What happened is that Watson and Crick, two famous renowned physicists or chemists, I don't remember exactly, but scientists in any case, took this picture without her knowing and actually included it in their well-known paper about the structure of the DNA. And of course, Rosalind was not properly credited for this job, for this work, which was so important. Later, they won the Nobel Prize for this discovery, and Rosalind was also excluded from the prize. So this is one of the greatest injustices in science. And it was basically because she was a woman at the time, was not well seen that women will actually do science. But the incredible thing about Rosalind is that she was not only the discoverer of the DNA structure, but she also worked a lot with other molecules, like, for example, RNA, and most importantly, viruses. So she was the pioneer scientist that worked in the structure of viruses, that we now this year know a lot about viruses, but she started this work, this leading work, that was really groundbreaking. And in fact, some other colleagues that worked with her in the structure of viruses won the Nobel Prize also later, when she had already passed. But in any case, so she was a really bright scientist, accomplished really incredible things. And I think it's very interesting to use this activity also to talk about her. And especially because we were talking about rovers on Mars, and I just discovered that actually the ExoMars rover that will be on Martian soil in 2 years is being called Rosalind Franklin, as a way to thank her for all the discoveries and efforts that she did. So I think this is a very beautiful way to remember her. And she probably had never imagined that she would have a footprint in the solar Mars, in the soil of Mars. So I think it's a very nice story. And with this, I leave you. And if you have any questions, of course, I'm here to answer now or through the afternoon in the chat. So thank you very much.
Yeah, so many thanks, Sandra. Very nice experiments. Always liked us very much. Questions for Sandra in the chat, please.
So we had one from the previous connection, and it's about the globe, the Mars globe that is next to Sandra. And maybe you can, yes, I told her that I think, okay, I don't remember the name exactly, but I told her that they can buy them in the internet, but I don't know if you remember the website. If not, maybe we can send them we can post it on Grasp once we have the name of the website.
Yes, I don't remember the company because it was our colleague Alfred who actually arranged for the purchase of all of them. We have several here at the office. But yeah, for sure, we look it up. And if anyone is interested, we just share the details. I really like this one. It's really cool. And we have the same for the moon as well. And we have also a normal Mars. I'm just going to take it. I cannot resist to show you. So this is a typical Mars, also in a spherical shape. And it's interesting because it tells you where all the different rovers were landed. Okay, not where are located, of course, currently, but where they landed. So it's really an amazing tool to have also at your school in case you are talking about planets, about the solar system. They're really cool. Also, I didn't mention it, but the rock that I showed at the beginning is an actual meteorite, we think, actually. We haven't analyzed it yet, but a teacher brought it to me that they found it in a beach here in Tenerife. And I talked to one of the experts in the house, to Julia de Leon, an expert on asteroids. And just by visual inspection, she told me that it seemed to be a real meteorite. But of course, then a proper analysis would be needed. But maybe you can also try to have access to a meteorite and you can also show them your students.
So there are no questions. Many thanks.
Thank you.
And
Thank you all.
one comment of one of the teachers saying that I think, she did the activity last year. Yes, from Daniela, I think. Gerasim Daniela, that she did it, and it was really successful. So we already have. If you have photos or something that you can share.
Yes, share all your picture if you want to do it during the week. That would be amazing. We can have a warm-up to see you all, your pictures, trying to repeat the experiments. That would be awesome.
Okay, Michelle and Rosa, I don't know if you want.
Yes, many thanks then. So I think then we finish for this morning. Rosa, unless you want to announce something.
Yeah, I just want to say that I'll be staying here behind a little bit in case someone has a problem in the installation of SalsaJ to help.
And we start the session as planned at 14:30 Central European Summertime.
Yeah.
Paella time.
So also, I would like to inform the participants that for the breaks, not now, but for the following breaks, the coffee breaks and the lunch break, we are going to be randomly distributing you through breakout rooms so that you can get to know each other. So it's 5 people at a time. We're going to drop you in a room. Actually, the system is selecting who is going to meet with whom. And you have the opportunity to talk as if you were live face to face with the other people. Okay, so when you come out or and back again, don't worry if you find yourself just with 5 people. That will be the normal thing for all the breaks. Okay, not now for the lunch. Or maybe if you don't have many questions for me, or if you don't have trouble in the installation of SalsaJ, then we can do that right away also for this group of people. And I guess that it's Sandra, just to remind you, please unhide the space on the campus for the participants related to your session. It's still hidden, but I'm sure they are eager to get their hands on the instructions and further information.
Of course. Yes, I will do that.
Okay. So does anyone here have problems with SalsaJ? Let me know now. I don't see anything here on the chat, so it seems that everybody has SalsaJ. Okay, that's great. Oh, there is one person with a problem. Okay. I don't know, David, if you were here, if you can be here to help me a little bit. Can you please use your microphone?
Yes.
Just someone that said that they have problem with SalsaJ, please turn on your camera and microphone and talk to me and tell me what the problem is.
Hello, I tried to salsa, but when I unzip, do you hear me?
Yes, perfectly.
Okay, when I unzip, it does show the files. You see, you told us you are showing us it, and I don't find the executable file.
Okay.
It only has a salsa file that I can't open.
So you're probably looking for the wrong address. Did you go to European Hands-on Universe website where you find the different links to download the software?
No, I did all the steps. I did all the steps.
Okay. Can I share my screen, please?
Yes, you can.
Okay. Let me open here. Let me open the page of share. Okay, so you should have gone to this page and then you click on software.
Yes.
Which operational system do you have? You have
Windows
10.
Yes.
Exactly. Okay. So you can come to this link here.
Yes, yes.
Right.
I even okay.
It will save the file. Okay.
Yes. I downloaded Java.
And you have to have Java installed on your computer. That is the first thing. Okay.
Yes, I did that.
You save this, and we'll open it. It won't. I don't have a Windows. I have a Mac. So for me, it's opening again what I have. But you should find the executable file. So can you try and do it with me? Can you share your screen and do it with me? I will stop sharing my screen. And if you can share your screen, I will help you do it with me, okay? Gustavo, if you can please stay behind, we might need. You don't have a PC also.
I'm here, but I have an idea of what is the problem. But if she can share the screen, it's easier that we can see what's happening.
I'm trying. Wait a minute.
Okay, start sharing. We can see. Yes. Now go to the folder that you have the files.
My files. Wait a minute. Oh, I see you. Wait. I see you and not my. Wait a minute. Okay. Okay. This is Salsa. Wait a minute. To remember where I put it. Okay. Okay. Can you see?
No, you have to share again because you have stopped sharing.
Share again. Yes. Okay. Can you see now?
Yes.
Yes.
Yes. I have these files.
Okay. So can you click on
this?
No,
this
no.
can't open.
The one below.
No, top.
Data.
No, Gustavo, that is not it. This is the icon. No, it's not this one. This is not an executable.
Oh, okay, so yes. So it's the second file.
The one above, the one below this one.
This?
This, yeah. Try to click on this. Click, double click.
Yes, this.
Just click twice.
I opened it.
But we can see because we only see the folder. We do not see the other screen.
It should share the complete.
The new yes. Okay, wait a minute. Stop sharing.
Just stop sharing and share the
yes,
folder.
And share. Yes.
Share everything, the whole desktop.
Okay.
Okay, now open the folder again and click again.
You can't see that.
No, we cannot see anything.
No.
We won't share. Now you can see.
No, you're only sharing the window where you have WebEx. You're not sharing your full screen.
You're sharing an application. Try to share the desktop full screen or something like that.
You will see.
I think I do it.
Select something different than what you did so far.
I'm
No.
sad that I'm delaying you. I'm sorry.
Not a problem. We're here for that.
Yes, you don't see anything. What do you see?
We just see the window for a WebEx, nothing else. You're sharing the wrong
Nothing
window.
else.
Stop sharing
No.
and try sharing something else, different than what you're doing so far.
Okay, different. Okay, I'm sharing it.
No, you're sharing the same thing again.
Yes.
When you click share, choose the first
What-
option. That's screen.
What do you see now? Now
we see
you
only
see the
You see the
file.
folder, the files, yeah. But we need to see the whole,
To open this.
Yeah, but we can't see the output.
So
Click share and then choose the first option, which is share screen or desktop. Do not choose a specific application. Choose the first option when you click share.
The first option. Okay.
Yeah, the first
This
one. Yeah. No, that's not it. Because you only see the files window. Anyway, can you click, the second SalsaJ, which is the jar file? Can you click it with your right mouse button? Yes, this one. Click with your right mouse button and let's see what.
Yes.
The right button of your mouse. The right button of your mouse. You're not doing that. You have to use the right button of your mouse, not the left.
Yeah.
I click. Yes, I click
But
it.
you were too quick. You have to wait.
Yeah. Rosa,
Yes.
may I suggest something?
Yes.
Because
yesterday
we cannot see the whole screen.
Wait a moment, please.
Yeah, because we are not managing to see the whole screen here in WebEx. Can I call Anastasia and ask her to? I can assist her in Zoom. So
That's great. Yes, Gustavo, please do that.
Yes.
That's a bit better. It's okay for you, Anastasia, that we
Yes.
we go for a
Okay.
Zoom session. That's much easier. Okay,
Yes, of
I'll send
course.
you stay here because I'll send you the link. Okay, and then you meet in Zoom. I'm sorry, but
Okay.
WebEx
Thank
has
you.
some issues here. Okay, no problem.
Okay, in the chat. Okay, I'm waiting. Thank you.
Okay, and now
Thanks a
Rosa can
lot.
help
Yeah,
parents.
I will be here for other people that might need. Is there anybody else in need of help? Just turn on your microphone and let me know. Any other participant that might need some help? No?
Yes, Rosa, it's Marina, and I need some help.
Marina, go ahead.
I'm ashamed.
No, don't be ashamed. Don't be ashamed. I mean, these things are never
Because
easy.
this is not the first time.
No, that's fine. Perfectly fine. Go ahead, please.
I installed the SalsaJ and the Java, but
Marina, you can speak Portuguese.
Ok.
If you prefer.
Obrigada. Já instalei o Java e o SalsaJ, mas eu agora carreguei nos ícones e ele não me abre. Eu também tenho um Mac.
Podes partilhar o teu ecrã?
Não, porque eu estou com a sessão no telemóvel.
No telemóvel não funciona.
Não, eu tenho o computador aberto.
Então não podes, podes partilhar, tu consegues partilhar. Pois, eu não sei o que te dizer, eu tenho que ver, Marina, preciso ver o que é que se passa para poder te ajudar.
Eu estou a filmar o meu ecrã. Portanto, quando eu carrego, aparece esta imagem.
Mas não estás a partilhar a imagem comigo?
Não? Iniciar, já está. Pronto.
Não é possível deixar ver porque provém de um programador não identificado. Ok. Faz ok. E agora clica com o lado direito do rato. Mas eu acho que não é esse. É esse, isso. Clica com o lado direito do rato e clica e abrir. Não, o primeiro, abrir, isso. Abrir, clique em abrir. Lá embaixo tem o abrir. Isso.
Já está.
Já está, pronto. That was easy.
Obrigada.
Nada. Anybody else with a problem that that need help? Okay, Marina doesn't solve her problem. Anybody else with a problem?
Hello.
Yeah.
My name is Takis. Hello. I will turn on the video. I have installed Salsa, but and I installed also Java, but it doesn't run.
Did you install Java first and then SalsaJ, or did the opposite?
The opposite. So
now
I will uninstall.
Well, you don't have to uninstall. Just click SalsaJ to install again. I will wait. That is quick. I will wait.
Okay, thank you.
Maybe you can also share your screen.
Give me 1 minute, and I will do it if I have a problem with that. Yes, thank you.
Anastasia is telling for you to wait just a little bit longer. It seems that Gustavo's computer crashed. So just wait a little bit longer.
I installed it again, Salsa, but still it looks for Java.
But then I know what the problem is. Can you please just share your screen with me? This is a problem that SalsaJ is older than Windows 10, and they changed the path on Windows, and now the program cannot find it. So actually, there is a fix to that. When Panagiotis, what I wanted to do is the following. Just forget that. Go to the page of European Hands-on Universe, please. Just leave it like this and go to just kill it. Go to European Hands-on Universe webpage.
Excuse me?
Go to European Hands-on Universe webpage, the page where you downloaded the software. Yeah, that one.
Okay.
And now you're going to...
I have Windows.
Yeah, go to the top where you see the February 2003 corrected version. Click on that.
Here.
Yes.
Okay. And then I will do...
Just wait, I will walk you through. Download it.
Okay.
And now you're going to unzip it. And you will have to take the files that you unzip and copy them to the folder of SalsaJ in the program files. So just unzip it and leave it there. Extract.
Okay. So I will extract them.
Just extract them
somewhere.
You can go to program files. I cannot read Greek, but inside Windows you have program files. You have two program files. I think it's the one that says 86, something like that.
So it must be in the other. It's all Greek to me.
Yeah, it is.
Okay, here we are.
Okay, open it. And extract there.
And I will replace everything.
Yes to all.
And
now go back to where, forget the icon that was created in your desktop because that will not work. go to the place, to the program, and create a new icon for your desktop. So go back to the program file where you have SalsaJ.
Blah, 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 blah. Check. And which is the...
Just a second. Anastasia, Gustavo is telling me that you can go to the Zoom link that he sent you on the chat.
Okay, thank you.
Now you have SalsaJ jar. Click on that.
This?
No, below.
Ah.
Yeah, click on that. What is this message?
Give me 1 minute to see it again. No message. No message, but nothing happens.
Wait a moment. Check back your desktop.
Nothing.
Nothing.
Magic.
Try again. Click on it again.
Okay.
It should have worked. So let's put this. Maybe
should I uninstall Salsa and Java?
No, you don't have to. Just do the following. Let's do the following steps, because you replaced everything. Maybe you shouldn't have replaced everything. Install again SalsaJ as you did before.
Should I first uninstall it just to be?
No, you don't have. You don't have to do it. It's SalsaJ is very user friendly in that sense. It's old, but it's very user friendly. Just install, not that one, the older one.
The older?
Yeah. We're going to do the process again.
Okay. Should I install this with the images or that?
Yeah, it doesn't matter. It doesn't matter. I'm giving you the images anyway, so you can do it with the images. It's fine.
So, I already have that, but okay, let's do it again. Okay.
Install.
We're ready.
Close. Good. Now go to the place where you have extracted the files from from the new version that you downloaded. Open that folder. No, this is the program file. Okay. Go to the zip file and zip it again.
I didn't understand that. Sorry.
So you have brought a file from European Hands-on Universe, the corrected version, and you have extracted it.
Yes, but we extracted it here.
Yeah, so we are going to extract it somewhere else. Instead of extracting it here, you're going to extract it somewhere else.
Okay.
Just on your, create a new file on your desktop and extract it there. Create a new folder. Sorry.
Yes, give me. It was
on the top, when it says February 2018 corrected version.
Here. You mean I download that again? Okay.
Yes.
And I will save it here, for example. Okay.
And now, when you extract to some other place, maybe on your desktop.
Yes.
Or in a different folder, so it's easy for us to find.
Okay, so extract the desktop.
Create a new folder, for instance.
I didn't make a new folder. This is a house.
So it's difficult for me to see where it is with so many things.
Yes, it is. So
apologize for that.
No, it's my fault that this havoc, not your. So
just create a folder. When you say extract, select new folder.
Yes, I will put it somewhere safely.
Yeah, you see, you have the new folder to the right.
I will put it here where, okay. And the new folder,
somewhere you know where to find it.
yes. Okay.
Okay, and subtract.
Nice. So
now you go to leave it open another window. Just go back to where you were, because you will need that window open. You will need
in the zip.
No, throw away all the zip files.
Okay. So this is
the new one, right?
Yes, and we know, and we
now leave this open as it is,
and we go to the old one.
Open another one in parallel to this one.
A new one, a completely new one.
A new exploded window. A new a new exploded window.
Okay. Explorer.
No, close that. It's not there. Yeah, this one, the yellow folder down there. Click with the right side of your mouse. The right side. No, yeah, exactly. Open a new one.
We need a new.
Two windows like this, one beside the other, because you're going to drag and drop one folder there.
Okay. So.
I want one explorer. Just open another explorer, just like this one that you have open. Open another one like this. If you go down there where you have the folder.
Okay.
Yeah, that's it.
Okay.
Now go to where you have SalsaJ.
Okay. Here we are. Okay.
Now drag and drop just the salsa jar. Yeah.
What?
What happened?
Wait. Okay.
Yeah.
Okay. So I replaced.
Yes.
Okay. It's done.
Okay. Now click on salsa jar.
And pray.
Still not working. I don't really understand why.
Okay. I will try. First of all, I think you helped me, because I mean, I know what to do. I will try with another computer I have here.
Okay. Maybe it's a problem with Java, because the problem is, okay, in the older jar, it will look for a folder called Java W. Actually, let me show you where that is. So
it is in the bin. It is in the bin, I think.
No. If you go to program files, and find me the folder where Java is. No.
Yes, of course. Java, okay. It
Java.
is in the...
Open Java. Yeah, open the one on the top. Yeah, in the bin.
In the bin.
Yes.
Oh.
Don't have it there. There is nothing. So go back to the other folder. Maybe it's in the other folder. Yeah. No. You have a problem with Java. You have to reinstall Java.
Okay.
You don't have the files that are necessary. Okay. Install Java again. It's Java.
Let me see if it is here. In the it's here.
There is a Java W over there. Yeah.
Here it is.
Java W, yes. So the old installation without correction, it's looking for that file. If you just say, okay, it's here, it will open SalsaJ. The problem is that every time you launch SalsaJ, it will do the same thing.
I did it before I was sent you the message. I did that, and I told. Yes.
So uninstall Java, uninstall SalsaJ, install Java first, and then SalsaJ.
Okay, I will do that. but I will let you know.
Okay.
Okay.
All
Thank
right.
you for your time. Thank you very much.
Very welcome. Very welcome. Okay. Next in line. Who else needs help? Can you stop sharing your screen, please, Panagiotis?
Yes. Give me 1 minute.
Thank you.
Why?
You have to find a red bar where it says stop sharing.
Yes, it has been minimized. So
yeah, so if you put your mouse over it, the stop sharing will appear.
I don't believe that.
That's okay.
Okay.
It
So
happens all the time.
I will do something else. Okay.
Maybe you have to leave WebEx and come in again. Okay, anybody else has a problem?
Olá, Rosa.
Quem fala?
Sou Natividade. Já instalei o SalsaJ, agora estou a tentar colocar na mesma pasta para ver se funciona. Segui a explicação que deu, mas ainda não sei se está a funcionar.
Eu preciso que partilhe o seu ecrã. David, are you around?
Só
um pouquinho. David, are you around?
Yes, I'm here.
Can you please stop the Panagiotis screen sharing?
I don't know if I can. Este video is the webcam. No, maybe I can share and. So you can share and then share again.
Perfect. Yeah, great. Ok, Natividade, por favor, partilhe o seu ecrã para eu ver o que se passa. Natividade, está por aí? I think Natividade is having some problem. I don't see her microphone anymore, David. Do you know what's going on? Maybe you should make me co-host so I can see what's going on. Now I don't hear anybody.
Yeah, I'll host now.
Okay. Natividade, are you still here with us? I don't hear her. Okay. While she's coming back, anybody else with problems with SalsaJ? You see the chat. Oh, Fraser's been helping. Thank you so much, Fraser. Okay, anybody else with a problem?
Natividad is there, but it's muted. She can't nothing.
Natividade, if you're trying to speak, Natividade, está a tentar falar, o seu microfone está desligado, está em modo mudo.
Sim. Já.
Ok. Partilhe o seu ecrã comigo, por favor. E se calhar é melhor desligar a sua câmera porque a sua ligação não tem boa resolução.
Está bem.
Isso, e agora partilhe o seu ecrã, escolha logo a primeira opção que é para partilhar tudo, assim não tem dificuldade, tá bem? Quando clicar aqui no Share, escolha logo a primeira opção.
Em cima, não é?
Exato.
Ora, o que é que está a ver agora?
Ainda não estou a ver, ainda está a vir.
Está a ver. Pronto. Eu tenho aqui estes ficheiros. Portanto, vou selecioná-los, extrair.
Não, pera. Não é nada disso. Isto foi... isso é o download do primeiro SalsaJ, certo?
É. Eu fiz, sim, o que está lá em cima. Eu fiz o download da versão com as imagens.
Certo.
Instalei.
Certo, mas não é esse que foi buscar agora. Não, eu não estou a ver aí. Eu não estou a ver aí o que é preciso. Olha, na atividade, se não se importa, cancele.
Sim,
vai de novo à página para eu ter a certeza que está a fazer download do ficheiro correto.
Aqui. Eu fiz download deste.
Não, sim, mas agora vai fazer. Já instalou.
Já instalei. Só que
Pronto,
eu estava à procura dele, está aqui, estava à procura e não o vejo nos programas. Estava a ver se o encontrava nos programas.
Mas já instalou, já extraiu, já instalou.
Fiz assim, fiz save file, fiz isto aqui.
Ele está a salvar ainda não veio completo.
Sim,
mas ali embaixo já está completo, eu estou a ver.
Já está, mas lá está, disse failed. Agora que eu estou a ver. Aqui mas pronto, estou a fazer o passo novamente, tudo direitinho.
Ok.
Mas eu sei que fiz isso e foi até ao fim, deu concluído.
Então agora abre uma janelinha dessas amarelas do Explorer.
Sim.
Isso.
E vou
E agora vai ao
PC.
Não, geralmente é lá para baixo onde tem o disco C.
É o C.
Exato, é o C.
Vou a programas.
Programas. Agora eu nunca sei se é no... Está aí, vai mais para baixo um pouquinho.
Eu tenho aqui várias versões de Java que eu já uso.
Ok, vai mais para baixo um pouquinho.
Mas não me aparece, já instalei o salário.
Então, mas não é aí. Saia daí, vá ao outro programa, o programa vezes 86.
Sim.
Tem dois, eu de baixo, o programa tem um X86 à frente. Aqui do lado direito,
Sim,
tem este programa, isso, abra esse, para ver se está aí.
O outro está.
Ande para baixo um pouquinho, até chegar à letra S.
Salsa, está aqui.
SalsaJ. Abra lá. Muito bem, deixa essa janela aberta. Coloque a menor, faça menor um pouquinho, para depois poder ter duas lado ao lado.
Sim.
Isso, deixa ela quietinha aí. E agora, vai fazer download do outro ficheiro.
Deste aqui.
Isso mesmo.
Faço save file?
Isso, save.
Isto para mim é tudo muito novo, porque eu não sou desta área, sou professora de francês.
Isto é ótimo estar a fazer, isso a gente aprende, a gente só aprende fazendo.
Sim. Estou a adorar.
Já fez o download? Já conseguiu?
Este, não é?
Pois eu não faço a mínima ideia.
Então eu volto a fazer.
Pois, é melhor fechar todos. Vá lá ao essa set zip que tem aí embaixo, fecha essas janelas todas.
Sim.
Isso está bem,
ok.
Certo, é esse mesmo.
E está aqui.
E agora vai extraí-lo para um sítio que saiba onde está, certo?
Sim.
Vai clicar e agora vai clicar em...
Seleciono tudo, extrair.
Exatamente, ok. E diga, clique no desktop, vá até o desktop.
Eu vou colocá-lo no sítio onde ele está, nos programas.
Não faça isso, porque esse é o truque para não nos perdermos. Vai até o desktop, selecione mesmo o desktop.
Criar uma pasta.
Trabalho, chame de salsa novo, por exemplo.
Salsa novo. Pronto.
E faça ok.
Pronto,
agora ok. Pronto, agora feche essa janela, feche isso. Isso já fez.
Sim.
E agora, abra um outro, tem um Internet Explorer aberto, agora abra outro, vá lá embaixo com o lado direito do rato, lá em cima da pastinha amarela, e abra mais um. Não, lá embaixo mesmo.
Sim, sim, sim.
Isso. E agora...
É este?
Não, não é isso, não é isso. Não sei como é que se abre uma nova. Clique em explorador.
Mas é para colocar aquela pasta dentro daquela...
Não é a pasta, não é isso, não é isso. Feche esse ficheiro que tem aí aberto, por favor. Feche isso, que isso só está a atrapalhar. Isso. O Windows não consegue localizar. Ok, faça o quê? Ok. Feche esse que está aberto agora.
Sim.
Ok, pronto. Minimize isso tudo, que é para não fazer confusão. Só ter aberto aquilo que a gente quer. Minimize também. Minimize também.
Sim.
Pronto. Agora vai clicar na pasta amarela.
Já estou a clicar.
Ótimo, ela já vai abrir. E agora abra. Muito bem. Agora vá lá embaixo e clique na coisa amarela para abrir, que ele vai abrir uma outra pasta. Espero eu.
Para que descarregar alguma coisa?
Não, mas não é isso que é fazer.
Era outro.
Isso.
Aqui.
E do lado direito do rato, explorador de ficheiros. Ótimo. Agora vai procurar a pasta onde está o SalsaJ, portanto é no C.
No C.
No programa 86, não é?
Sim, sim.
Isso. Procura aí o SalsaJ. Já passou.
Tá. Abrir?
Abre. E
Sim.
agora deixa essa pasta quietinha e abra a outra. Deixa essa no cantinho e abra a outra. Isso. Arrasta ela para o lado um bocadinho. Isso. E agora vai... Ups, o que aconteceu aí? Agora põe o rato em cima do sal. Pega o SalsaJ.jar e arraste para outra. Isso mesmo.
É para substituir o ficheiro.
Exato.
Substituir o ficheiro no destino.
Sim, isso. Para remover essa pasta. Ok. Agora faça clique nesse SalsaJ e veja se funciona.
Já fiz duplo clique. Vamos lá ver se está dentro. Já está. Fantástico.
Pronto.
Já está. Obrigada.
Nada.
Obrigada.
Okay, anybody else with any problem? If not, I'm going to have lunch before we have to restart. Natividade, eu peço que pare de partilhar, por favor, o seu ecrã.
Sim, sim.
Ora... Tem que encontrar a barrinha vermelha que está por aí.
Não estou a encontrar,
Onde é que ela está, não é? Aqui do lado direito não tem uma janelinha onde me vê? Deve ser por aí alguns. Aliás...
Aqui, em cima... Ou só se eu fechar. Se calhar mais vale fechar, então.
Pronto, saia do programa e depois volta a entrar. Vai lá almoçar e depois volta a entrar.
Exato. Ora, onde é que se fecha aqui? Tenho que aumentar isto. É que isto ficou pequenino e não estou a ver.
Eu também não consigo ver isso, mas se passar o seu rato aí por cima, algures há de aparecer a opção de parar de partilhar.
É o que eu ando à procura. Que eu não estou habituada a outras.
Sim. Deixa eu ver se eu consigo resolver isso. Espera lá um minuto. Eu talvez consiga isso. Espera lá. Ok, problema resolvido.
Obrigada.
Nada.
Do you listen to me if I try?
Okay, everyone, any other problem? Anybody with a problem? No? Okay. So have a good lunch. Yes, I can there.
Okay, thank you. Didn't before. Thank you very much.
Okay. Going for lunch then.
Have a good lunch. Yeah.
Thank you.
Roberto, hello. Good afternoon. At least good afternoon in Europe, depending on where you are and where you participate. Rosa?
I'm here.
Very good. So essentially, this afternoon is, well, at least the beginning of the afternoon is yours. Yeah, I hand it over to you. You can explain much better than me what you will do.
Okay, thank you, Michael. So I won't be paying attention to our WhatsApp group, Michael. So if there's anything that I need to know, please be kind to tell me. Also, if you can help me with the chat, it would be very nice. Thank you for that. So I will be sharing my screen. Let's see if it works well. Okay, can you see my screen?
Yes.
Okay, good. So I'm going back to the activity, to the nice activity that Bea introduced yesterday. And I'm going to show you, this is just the warm-up part. We are just waking up. I guess everybody had lunch. David is probably sleepy because he had paella. Paella? How do you say that, Michel? Or David, how do you say that? Paella?
Paella.
Paella. So, David, you are not allowed to sleep because you made us all envy of you. So I hope you had a nice lunch, and now it's time to wake up. And by the way, some of the activities that we are doing here with you guys is what we call, warm-ups or ice breaking or whatever. They're very important for students as well. So when students come back from lunch or even in the morning when they get to school, they sleep, their brains are not awake yet. So it's very good to do something fun to wake up. So if you go to Google and you search for ice breaking, team building, warm up, there are tons of very fun activities that you can do with the students to wake them up. So you should do it every day. And at some point, you can ask the students to invent their own, to come up with their own ideas for energizers, which is also another word, energizers. They can come up with their own. So Bea had this very nice idea using Google Earth. And I hope that, well, I don't think that everyone have put a link. Let me check here. Oh, guys, shame on you. Only a few of you have included your pins on the Google map, and it's so easy to do. So can I ask someone, I don't know if Gustavo is already here or, well, anyone, please put the link on the chat, or maybe I can. I can. Okay, here's the chat. Let me copy this and put it here. Okay, so I will not be paying attention to the chat, as I might be distracted from what I have to do, but at least I can do this. And you guys can go there. Please go there, put a pin on your location or whichever location you prefer. Hopefully you will be sharing your location with us. And what I want you to do today is something very interesting. I want to know if there's one food or sweet that you really like, that you would ask for us to bring to you, if we could deliver it in a digital message, what would it be? So I did it, and I will show you how I did it. I clicked here on the pin that I have created. Okay, and I created a chocolate. See, it's Rosa Doran. I live in São Domingos de Rana in Portugal, and this is my favorite energizer. So I would like you to do the same. And so when I click in other pins, I will find what is your favorite food. So if you want to edit what you've done, I am not an expert on this platform or on this tool, but okay, let me click here again. I'm sure I can edit it. Yeah, I can click on edit, and this will appear. And now I'm not going to change that because I just did it. So I had the possibility to have a small info box. So if you click here, you will see no info box. Then I changed that to small info box. and I wrote my favorite energizer. And then I clicked here to put an image, and I asked Google to find an image of my favorite chocolate, which is dark chocolate with marzipan inside, my absolute favorite. Yeah, it's very caloric. I know I shouldn't be eating it, but actually I don't often, but that's my favorite one. And you can change it. You can change the color of your pin, and you can do all sorts of things to make this space fun. So today, your assignment for an energizer, and I'll give you like 7 minutes to do that, is to tell us what is your favorite energizer. And if you do that, just put your name here so that I can go and check. Or not your name, the name of your pin, so I can go there and check what is your favorite energizer. So let's see. I know that Michal the other day created.
Yes, if you look for the CESA ESAC Solar Observatory, I've put 3 pictures there.
But did you ask? Okay. But did you put your favorite energizer, Michel?
No. I would have to practice.
Now you have this on assignment. Okay, I see the observatory. It's very nice. I know where it is. And I do want to go there personally. But wow, I have a question. You can add more than one image. So now we see the observatory. That's pretty cool. I see the observatory. I see an image taken with that observatory. That's very, very good. Very, very nice. Very nice. Michel, can you send me that picture, please? If it was taken from the observatory, I would like to use it in SalsaJ today. We're going to make some fun. If you can put it on the chat, I don't know if you can share it on the chat. If you can, just put it on the folder where I have image processing with SalsaJ, and everyone can go get it.
Okay, I can put it in the grasp folder. Yeah.
Yeah. Oh, and it's here. I think David just shared this with us. Let's see.
If we have it in our CESA database, it might be.
Aha. But it's just a little piece of the sun. It's not the full image, right?
That's only but we have also full discs of the sun also, right?
Yeah. Okay. I would prefer the full disk of the sun if you can.
Yes,
okay, but for now, your assignment is not that. I will come back to this. Your assignment is something that you really appreciate as an energizer. So this and this. I don't need this anymore, and I go back. Okay. So the image that you put, don't delete any image. Just keep putting and adding things there. Today in the afternoon, I have been receiving messages on my phone saying, stay at home, the storm is coming. So that's a little bit frightening, but that's okay. We will survive. And we are back here. Let me see now. Did anyone update the image with their favorite energizer on their pin? Let me know. Put the name of your pin here so we can search for it. You can even speak if you want. Everybody's so quiet. This is annoying. I don't like quiet rooms. Okay. Let me see if I find that one. There is one that is in Greek. Oh, I don't find that one here. Let me refresh. Maybe this needs refreshing. It does, but I'm refreshing my Google Earth to see if I maybe missed some of your pins. Maybe I shouldn't have that. Now it's taking forever. I have 1,001 different things open in my computer, which is never wise to do, never advisable. Okay. A beautiful planet. I know that we can also actually see the weather here. I don't know. Is Bea around, Michal? I cannot see the participants now.
Yes, I'm here.
Bea, can I turn on the weather here? Or this is only if I have a different pro account, or it requires a different plugin? Do you know that?
The weather, I don't know that, sorry.
You don't know that. I know that I saw once someone saying, oh, you can even see the weather. Okay, this is Bea's assignment to find out how we can put the weather here. Okay.
We'll try.
Sarah put one in, okay, I guess this would be in Ghana Planetarium. Ghana, I haven't been there yet, Sarah. We have to solve this. When COVID is gone, I need to visit your planetarium. Okay. And let me, here it is. But this is not the image, Sarah. I don't see the image of your favorite energizer. How do I change? Now, in order to change, you have probably an edit button that you have to use. Okay. And then you can, so I'll show again on mine. Oh, look, if I just put the mouse over mine, I click here on the edit feature, and I can add whatever I want. Okay, now Google is taking me to that pin. Okay, so it's mine. We have another one in Oedos. Who might that be? I think I know who it is. Back here, I'm going to click here. We have Oeiras Portugal, but we don't know who it is, and we don't know what's the favorite energizer of that person. Sally, I put a pin of the food I'm craving, but it is in Japan. Oh, okay. But Sally, if I click on your name, Sally, maybe it will show me what you did. Let's see. Guys, you can turn on your microphone, you can talk to me. No, this is Sally with the students. Sally is hungry. But Sally, I cannot see the pin that you have posted there. I don't see Japan here. Okay, let me zoom out a little bit. We have 1 more minute to go. That's Fraser there. Let's see if Fraser is here and if he's a good student and have updated his image. Boring, nothing there. No.
Rosa, if you go to the left, to the next icon below the one you have, here you can animate clouds there. Yeah.
This?
Yes, if you go there, you have at the bottom part 3D building.
Yes.
And then the following one, if you scroll down, you should have this turn on animated clouds.
Okay.
So it's like 24 hours cloud coverage. Whether it's real or not, that I don't know.
It's coming. It says from Landsat. Oh, look at that. It's coming. 74%. This is from Landsat and Copernicus data. That's very nice. Thank you so much, Bea. You're very good at this.
Welcome.
I will never use any other energizer than this. This is absolutely brilliant. That is really very good. Come on, guys. Who did add something to their pin? So you have to give me the name of the pin, otherwise I cannot find it. Oops, now I lost everything. So how do I do it now? Where is it? No. Bea, help me. How do I find again the list of pins? Maybe the search? No. The navigation? No. This is a voyage. I don't want to travel, or maybe if I click on one of the links. No, I just lost it. Okay, I click on one. This is a school in Bilbao, and someone likes to eat Mars. I'm joking, of course. Okay, that's not it. Projects. Okay, I'm here again. This one. Okay, so name of the pin Vasiliki. Okay, let's go and see if I can see Vasiliki. It's the last one, then we don't have more time. Oh, I don't see Vasiliki here. Maybe it's in Greek and I don't see it because of that. Aha, okay. Vasiliki, turn on your microphone. Tell us how we pronounce this.
It's Komotini and it's in northern Greece. It's the purple or the purple. Yes, that's one.
Okay, but
I have changed the name in English, both the name of the city and my name. So I don't know why. I have to refresh the map in order to take the new one.
I don't know. I don't think that.
I did that again.
You do have to save. If you edit something, I think you have to save. Let me try it in mine, so I don't have. You see, guys, this is how we learn. We have the teacher around, but we are doing it ourselves. This is the best way to learn. So I'm checking mine, and if I click on edit, and I change something, for instance, I'm going to change the color of my pen to blue, and no, I just come out and it's done. Yeah, it works. We don't have to save anything. Okay, so our mission towards a nice Google Earth is to have it for today in the afternoon, for the next coffee break. I will check what is your favorite energizer as a food, and we will check it out. Okay, time's up. Let's go for serious business here. Not that this is not serious, because it is. Okay. And we are going to start. Did everyone manage to download SalsaJ and the images? If you didn't, if you have any problem, maybe today at the end of the day, I can stay behind and help you out with that. For the time being, I want you all to launch the software, and you should see a yellow bar like this one, okay? So I see that Panajati said, "Dear Rosa, I tried really everything in both computers doing restaurant. No salsa for me." Okay, so Panajati, please watch, and by the end of the day, I might have to escape a little bit before the very end, but then please stay behind. And what we will do is I will ask Gustavo, if you don't mind, Gustavo, helping Panagiotis in the end. He will create a Zoom room as he did for Anastasia. Actually, you know, this is the best, yes, Gustavo. Maybe you can create, and I will join you in that room, and we can solve all the issues for people that have problems with SalsaJ. So I can also learn with you the things that I don't know how to solve.
After the today's session, right?
Exactly, at the end.
At the end, okay.
Yes. Okay. I might be out for half an hour, but after that I am around. Okay. So it's okay if you just watch, because then you learn the tricks and things that you can do. There is a PowerPoint in the. Okay, let me open here again. Here in our campus, which you see like this. By the way, this is using a tool called Graph. This is the back office of the teacher. This is where we are creating this. This that you see here is created in a very modern environment where that is various purposes, in particular the purpose of creating inquiry-based learning sessions. So, for instance, each element like this program is something that we have added one by one, and this is done here with simple drag and drop. Okay, if you are interested on that, you tell me, and I promise you that we will run if there is interest once the particular training session just for inquiry-based learning, and another one for Go Lab that uses this authoring tool that is called Grasp. So on Grasp, in the space that is a shared space, you find the link to install SalsaJ, as I told you. You find the instructions on how to install it. And you find a link to a Dropbox folder or file folder where I have all the images that I'm using today and tomorrow. You don't have to download it right now, but it's all here. You have all the collection that I am using, except from a few that Manuel Castillo shared with me that I don't know if I can share with you or not. If you give us permission, I will also share them. And you have this SalsaJ English. This is your manual. And what you have there, again, like this, that is a step-by-step instructions on how to replicate exactly what I'm doing here with you today. Okay, so if you are feeling lost, like I don't know where to click, I didn't launch, I don't know, I don't have the images, and you're wasting your time now trying to install everything, just stop doing that, because everything that I'm showing to you is in this PowerPoint. I prefer that you look at what I'm doing because we don't have a lot of time. We have 1 hour together, actually less than 1 hour now. And I prefer that you look at what we are doing. Okay, so I will have this PowerPoint open outside of your view so I can follow the order. And in the folder where you have all the images, you have you will find an image that is called F and Y feeds. For that, let me show you something that is important that you know. This is a CCD camera, and basically our mobile phones have a CCD camera inside, and it's a CCD camera. What they do is they convert the light into into electrons, creating one electric current. So they're all made of silicon, and each square, so this thing here, if you zoom in, you'll find a collection of squares that collect light, collect photons. And each of these elements is called a pixel. Okay? And they collect photons and convert into electrons that will be transformed into a number in a matrix. So astronomical images are just matrix full of numbers. This is what they are. Okay, this is how the information comes to us and how we can analyze it. And the astronomical image, I have my images here, and I can either go to File and open them, go to the place where they are and open, or if I have it open like this, I can just drag and drop. SalsaJ. One important piece of advice: do not click on the image to open it, because if you do click on the image to open it, what will happen is the following. I will click, and I shouldn't have done that. Now I made a big mistake. It will open my favorite software to see images, which is GIMP, and that doesn't work because GIMP does not know fits. It's a specific type of code that preserves the information that is brought to you with the image, okay? So don't click. You have to either go to File and Open or drag and drop the image to SalsaJ, which is just what I did, okay? So I selected this image, and the idea here, there are other windows that appear. Don't close them. You can minimize them. Just don't close it. Leave them open because you might need them, okay? Now, what we are going to learn here, and to some of you, this image is appearing very black, as you can see here in the PowerPoint. You see here, the image is completely black. And I'm going to click in this button here. That is the button to adjust. This is the button to adjust the brightness. If you click on auto, it will reveal the image to you. And of course, if you are patient enough, you can play with this, play with that, or you can just auto. When you are playing with this image contrast, brightness, and everything, you are not changing the image. You are changing the way that we see the image. So the computer, or sorry, the software is trying to show you the best possible image for that particular, the best possible contrast and brightness for that particular image that you have at hand, okay? So you adjust it until you see the image. You can also play by coloring it. For instance, if I go to image and I select lookup tables, I can paint it green. Or image, lookup tables, I can paint it red. But that doesn't mean that the galaxy is green or red or blue. In astronomy, all the images come in black and white, and the color is assigned by the software or by the astronomer that is working with it. Usually, we assign the color of the filter if it is in the optical. And because this is a fit file, I can go to Image, Show Info, and this will give me information about the image. The name of the object, I don't have, there was no filter, so it's something that has, it's not filtering the light that is coming, so it's probably a beautiful color image that I cannot produce a color image because I don't have it in the different filters. So it's something that was automatically done. So there's no coloring to it. But I have all sorts of information. The right ascension and declination, I don't have here, probably because they didn't turn this specific feature on the telescope the day this image was acquired. But other information that are very relevant, especially if I'm doing science, because if that is the case and I am doing a scientific experiment, that means that if I discover something, I have to share this with other scientists. So the scientists can verify the discovery that I made. This is how science is done. Okay. So this is just was just to show you how to play. Oops, I didn't want to maximize this. So this was just to show you how to play with the colors and contrast of a specific image, okay? Now, okay, let me open again this image. I shouldn't have closed it. So that you see, this is not the one, yeah, this one, the fit file. And I'm going to drop again here, open it again, and I'm going to do something that is pretty cool. You see here, I'm going to click on the magnifying glass. I'm going to zoom it a little bit. It's a very nice image of a galaxy. I can use the hand to drag. Oops. Oh, I don't need to do it because I have the full image here. Okay. So now I'm going to go to Analyze, and I'm going to select First, I need the straight line selection, and I'll try to put a line crossing these 3 bright spots here. Okay, I know that one of them at least is a supernova. To be honest, I don't know which one it is, but one of them I think I have in the PowerPoint somewhere saying which one it is. But what I'm going to do this is make a profile. So plot profile. Math teachers love it. And now if I scroll through the picture, if I scroll through the graph, you see here, if you look at the picture, take a look, put your eyes on the picture. You will see as I'm moving, it is showing me what I'm seeing on the graph. Okay, this is a plot profile. And I can measure this. I can measure the brightness and I can compare to other images. So imagine that I have an image of the same galaxy in 3 different nights. And maybe this one is a supernova and its brightness will fall down. So I know that this other 2 peaks will remain the same and this will faint. So I know that I have seen something there that is something that is not always there in this galaxy. It was a feature, a phenomena that came and went away. And by the shape of this phenomena, scientists try to understand what is it that they are seeing. This is something that Fraser and Ira are going to share with you later on this week. Okay, so this was just one teaser. Now, we're going to open another image.
Just very briefly,
yes.
I put your 3 sun images in graph in your session.
Okay, thank you very much. We're going to go there, maybe not today, maybe tomorrow, or maybe later today. Thank you very much for that, Michal. Okay, now let's open another image, and this image is called, actually, I need to see this better. This is the image called moon.fits. Okay, so I'm going to look for this image here. It is here, .fits. And I'm going to drag it, drop it here. And here is my very tiny picture. And I'm going to zoom in a little bit. Okay. And one thing that I can do, and that is very interesting, you know that Sandra has talked to us today about craters. So you can see here the crater. And one thing that you can see is also, you can make like a profile here as well. And you can analyze and make a plot profile again of this. This is the plot of the moon. And you can see the different shadows, the sun illuminating the several parts, right? And if you can find a collection of images of the moon across one week, for instance, you can see how the illumination of the sun is changing because it's illuminating different parts of these craters that are featured. This is one image, one specific image only, okay? So you can zoom and play with that. Okay, another one that I have from the moon here is this one that is called craters. Now to open this one. Okay, and what I'm going to do now is something that I'm going to try and do again with Michal's images, but actually I will give you that as an assignment later today if we have time. But what we can do here is, first of all, I can zoom in to such an extent that I can see the individual pixels. Can you see the squares? You can type on the chat, can you see the squares? Or the image is not good enough for you to see the squares? Everybody's very silent. Yes, you can see, great. So with the right side of my mouse, I'm zooming out, okay, to have the picture again in the same size. Let me just change something here so I don't get lost in the sequence of things that I want to do, right? Okay, better. So now what I'm going to do is the following. I want to measure one of these craters. Let me close this. Sorry, a little bit, organize myself. I don't need the brightness and contrast. And I'm going to, okay. So what is your guess? I'm going to measure, okay, let's try and measure this crater over here. How big do you think it is, this crater in meters or kilometers? Just a guess. Tell me on the chat. How big do you think it is? Come on, any guess will do? Be brave. 25 kilometers. 5 kilometers. Okay. Any idea on how I can do that? To know what is the amount of kilometers there? In a very easy way. The answer is, there is no easy way here because I don't know the scale of this image. Unless I know the pixel scale, which in this case we do, and in the astronomer who produced it, because it was produced for Global Hands-on Universe as a pedagogical image, the astronomer, the following. In the information about the image, you see the object, the telescope that was used to take this image, what was the instrument, what was the name of the observers, the date it was observed, the time, how high, where on the sky was the moon, right? But in the end, there's also many things different about the equipment and everything else. But here, towards the end of this image, the astronomer did us a favor. This is a text file, the fit file here, this information, I can edit if I want to. And he did. And what he told us is that each pixel is equivalent to 1.1 kilometers. Okay? So what I have to do now is go here, go to image, and click on another feature, which is, sorry, not that's what I want. What I want to do is analyze and measure. Okay. So I know that this specific line has a length of 102.5 pixels. So I can turn on my calculator, which appeared here, and I put 102.5 times 1.1, and there you go. This crater has 112.75 kilometers. Okay, I will show you later on how we know, how can we do it in a simpler way if we have the full image, and then if we know the diameter of the object from other sources, of course, then you can guess the size of this crater. This is very good exercise to give a sense of perspective to students of what they see on the sky. You know, when we look at the moon and we see these different parts of the moon, how big they are. This is a very nice activity to do with your students, okay? Okay, now, another thing that I can do, okay, this one is done. Another thing that we can do is do a surface plot. This, and another important information is the following. If something doesn't work on SalsaJ, there is always one simple way to solve it, is close SalsaJ and open it again, okay? That's usually solves all the major issues that might appear. So now I have opened another file that is called N51. I'm going to drag and drop it. Here we are. Let me play a little bit with the brightness, contrast, auto, beautiful galaxies here. A little bit. Yeah, not really. Okay. But what I want to do now is, instead of doing a plot profile, so remember I have used the straight line, I can make it like this. Oops, very bad. I failed miserably here. No, let me do the opposite. Like this. Okay. And I can do analyze plot profile. Okay, and this is what I see. No, I don't really like it. I prefer to do the following. I click here on this square. I select this area and I do analyze surface plot. And a completely different reality appears. Okay, I can select, instead of lines, I can select the field one, and I see the profile here, much better. There's a lot that I can analyze. You see, this is my image exactly. Remember, this is not height, this is brightness that I'm analyzing here, okay? And I can play with the Z axis, the maximum and the minimum. I can play with lots of things. I have never had time to explore all the features that are enabled here on this surface plot. You can do this for anything you want, even you know, the ears of your cat. So you can do this for various things with various different purposes. So this is another feature that I wanted to show you, okay? As I said, this is all in the PowerPoint. Don't freak out. You will be able to work and train a little bit on this, okay? Now, I'm going to open another one. Close this one. I'm going to do another thing. This is my favorite one. You also in the Dropbox. You guys following me? Anybody's panicking? Anybody in panicking mode? Okay. I'm going to open Jupyter 1, 5, 6, 7, 8, 9. And I'm going to drag and drop it to SalsaJ. The thing is that I have opened SalsaJ in the other window, so it is playing tricks for me because I have to drag and drop everything here. I don't have to do the sharing of the other screen very soon. Okay, so I have here my pictures of Jupyter, and actually in this particular one, take a look at this. I will zoom in. Can you see the red dot, the spot, the red spot in Jupyter? I guess you can see it, right? This is a storm that is going on for over 300 years. And people think it's a hurricane that doesn't disappear because there is no surface for it to hit. Okay, now I'm going to do some magic, huh? Nothing this hand, nothing this one as well. And I'm going to click on auto. Oh, what are those things near Jupyter? Can you tell me? I now see things that I was not seeing before. The moons, right? The 4 Galilean moons. This is what I see here. Okay, so I'm going to do something that is pretty neat, which is the following. I'm going to click here. Just do the following. Image process. Okay, I go here to process image calculator. And what I'm going to do is I'm going to add Jupyter 1. No, sorry. I'm going to add Jupyter 5 to Jupyter 6 and create a new window. Well, not much to see yet, but if I click on contrast and I adjust, can you tell me what I see here then? Can someone say, what is it that I'm seeing here in this picture now? Someone, the motion, nice. Are they going up or down? Related to the picture, are they going up or down? Could Galileo use this image to prove that the moons are orbiting Jupiter? What do you think? Don't be afraid, answer. You can turn on your microphone or write on the chat. Up and down. How do you know, Francis? once Natividad set up. You should see more pictures. Okay. So I'll try something that I haven't done before. Process image calculator. Let's see something here. Result of chapter 5 and 6, and now I'm going to add 7. Okay. What do I have here? I might fail miserably, but I don't care. It's okay. Oh, now we have 3 images. That's pretty cool. I have never done this before. That's awesome. Can you see the 3 moons? So now we have 3 images, up or down. And can we confirm that they are orbiting Jupiter? So Diego, I have more pictures. It didn't solve the issue. Okay, because we don't have much time, if I was in the classroom with students and I had time, this would be a perfect inquiry-based exercise, okay? So what I'm going to do now is process image calculator, and I'm going to do something absolutely awesome, which is I'm going to put here chapter 5 again, and I'm going to subtract from chapter 6. Check it out. Okay, some inquiry now, guys. Can you tell me from this picture what you see? Okay, wait a bit. Salvador said some goes down and others go up. Okay, Salvador, how do you know that from this picture that I'm showing? Can you tell me, just looking at this picture, which ones are going up and which ones are going down? I would like to hear your brain. This is the part that I hate about being online. I don't see your faces. Lucky guess. Well, if Galileo would have claimed that it was a lucky guess, he would have died earlier, I think. No, it's not a lucky guess. And actually, if Galileo Galilei had SalsaJ, he would just love it so much. The answer is here. Can you tell me how we know? I will leave it here and I will try again my luck. Now I don't know which one is this one. Let me just add this result. Okay, I will put this one. I created the program. This thing is not disappearing. Okay. The result of chapter 5, and I will subtract from chapter 7. Let's see what we get. I don't think that works very well. That's pretty interesting. I love this one. Look at this. Is it making sense to you? This thing won't go away. Some dots are white, other black, and they are interchanged depending on the moon. Yeah, the thing is, when you're adding and subtracting, it's assigning colors to one picture and the other. But if you take a look at this too, this is giving the answer to you. There's something going on here. Can anyone tell me what it is? Why I can say that this is good evidence that some of these objects are orbiting Jupiter? It's not the fact that some are black and others are white. Let me see here. It's not from the different intensity. It's from the shadows, but not just because of the shadow. It's comparing the black dots and white dots, but what? In some cases, the black dot is down, but in others, it's up. Okay, so take a look here. Black, white, black, white, white. Oh, wait a moment. White, white, black. So this is going the opposite direction, right? Okay, so this moon is going this way or this way. I don't know which way because I haven't been careful to study this. But we see those two coming down. Yes, Jupiter did move, but only a little bit. You can see that Jupiter is elongated here because it is moving, right? But the moons are orbiting, and especially Io, because it's closer to Jupiter. In one night of observation, you can see it orbiting. You can see it going around the planet. Okay. Of course, you need more study. You need more evidence, but you are on the footsteps of Galileo Galilei. Okay. Okay. So I'm going to close all these images now, and I'm going to go back. I'm going to close everything not to make a mess, and I cannot get rid of this, but I don't want to kill SalsaJ, so you will forgive me for this thing that is now remaining on my screen. I'm going to open all the Jupiter images again. Oh, actually, no, I will not do this with Jupiter images. I will do this in the front. Okay, so we've worked with Jupiter. We are done with it now. Now I'm going to do the one that students really totally adore, which is I'm going to make a colored picture of a planetary nebula. So I have here these 3 images, which you also have, from a planetary nebula called M27. And I'm opening it here. Okay, what you see here is all black and white, right? Okay, and I'm going to click on this one. And auto. Do all these images seem similar to you? Do you think they are the same images, the same object, or do you find something different between the images? Let me zoom in a little bit. Now go away. My computer is almost about to crash. If I disappear, you know what happened. So they are not equal, right? There are differences between them. And if I move the hand here, I can move it around, okay? You're right. So the thing is that they've been taken with different filters. And as we've heard briefly this yesterday, the colors or the filters are bringing different features. It's different physics, it's different chemistry of the specific element. So I'm looking to different phenomena of the same object. That's why it seems different. So in order to allow us to see better, having it in a color image, it makes it easier to understand what's going on. So in this specific case here, the observer put the name of the filter on the title of the image. But if I didn't know, I go to image, show info, and here I can see the filter is green, okay? So what I'm going to do now is I'm going to assign the color according to the name of the image. So I go to image, sorry, let's close something here because this is interfering with my computer. Okay, I go to image and I go to color and RGB merge. And I'm going to tell the software is asking me which image is red. I'm going to click here and say this one. Which image is green? This one. And which image is blue? This one. And now I'm going to keep the source images so I can play with it again. And ta-da! This is a very nice color image of a planetary nebula. And as Fraser and Ida will show you, there is a large database of objects like this. This one in particular is called the Dumbbell Nebula that you can download and play with it with your students. You can have them make their own collection. Now you can ask me, what if I made a mistake and I don't use the colors as you said? Well, nothing will happen because, again, remember, you are not changing the original images. You're not changing anything. You're just changing the way we see it, okay? So if I go here, colors, RGB merge, and I don't change anything, well, I'm going to have something that has a different color. Of course, that in this particular case, the red features are the ones that were taken with the red filter on. In this particular case, that will appear in violet or something like that. Okay, so there is no problem in doing that, no problem at all. Okay. Okay, so this was the part about the color image, and now I'm going to dazzle you with making some movies of the sun. Let me just close this. Okay. And what I will do now is I will stop sharing for a moment because I need to move to my other screen. So give me just one moment. I'm going to switch things around here a little bit. SalsaJ down here. And my images are down here. And now I'm sharing. That I'm going to be looking down at you because I'm looking at my other screen. And there's going to. Okay, can you please? No, this is not what I want. Sorry. Stop sharing. Let me share again. Share. And I want this one. Okay. You are seeing my screen. You see SalsaJ? Can anyone speak with voice? Because now I don't even have the chat anymore.
Yes, we see it.
Okay, great, great. So now I'm going to choose. I have a images from Soho, but actually I'm going to use this one. These are images from Soho. What I will do here, I can do because my computer is very patient with me and cope with me with this many images. Your computer is probably won't be happy if you do what I'm going to do now. I'm going to drag and drop all the images here that I can. No, I'm not. So yeah, okay, it's opening. It will in this computer, but well, it's an old computer. It has 6 years old computer, but it puts up with me. Not every computer puts up with me. I have 1,000 different things open all the time in my computer. In this particular case, I'm opening too many images. In the case of less powerful computers, especially in schools, what you do is instead of opening all these images, you select one and then keep 4 or 5 and open another one and another one. You just select the images that you're going to open, okay? But I am selecting a sequence of images that we're taking with the Soho satellite. And I'm going to make a movie with it, okay? So I go again here. I can just close something else here. This is, I have to open my computer is complaining. And so now I'm going to make a movie. So I go here to image. And that's not what I want to do. Sorry, just give me one moment here. I go to image, stock, and start animation. Sorry. I need sleep. Okay. Image, stack. And I'm going to select images to stack. And what the software is doing is compiling all the images together so that all the images will be the same size. Now I'm in trouble. Let me see, what is it that I have here? Okay, I have one image up here, another one. It doesn't like when you have other images open. Okay, now I should be okay. Image, stack, images to stack. You have to have only the images of the same collection. The software doesn't like if you have Jupyter open or if you have the Nebula open or something else. The software doesn't appreciate that and it really doesn't work, okay? So what the program is doing now is compiling, putting all the images together, and with that, I will be able to create a movie. So I have just compiled here, as you can see. And now I can go to image, stack, and start animation. And voila, I have the image of the sun rotating. And this is something that we're going to play a little bit with, which is trying to understand the difference between the sunspots, which is something that Galileo discovered, and a planet passing in front of the sun. And while you are dazzled with this, I'm going to go to the folder where probably now we have the images that Michal kindly gave to us. Let me see if I can see it. Beautiful. Okay, 3 beautiful, beautiful images. Okay, so I'm going to save this image. I'm saving one of the images that Michal gave to us. Yeah. Okay. And so I'm going to stop this. Image, stack, stop animation. And I'm going to open the image that Michal gave us, taken with their observatory. Let's see where I can find it. Just a second. Here. It worked. Okay. F. Okay. I just put it in the wrong folder. Okay. That's not what I got. SalsaJ. Here, SalsaJ. Okay, now I have saved where I want it to be. And hopefully, I will be able to see it here. Let me open my file again. Michal gave us a very, very, very nice image of the sun. Michal, while I'm looking for it, can you explain which is the filter that you use to make such a nice image?
Sorry, which is the?
The filter, which kind of equipment you use to make this image?
The equipment is the Solar Observatory. These are two telescopes. One is a normal telescope, but this is not these images. What you see is the H-alpha image, which is a special filter. So it's a special telescope which is just serving for observing the sun in this wavelength. So what you see here, as Rosa said before, you see this nice orange yellow color, but the picture originally is black and white or grayscale. And afterwards, just to make it nice again, so we convert the contrast again back more or less in this visible with the colors so that you have the same impression if you look at it. But for the real scientific work, you don't need the colors. So you work just on grayscales.
So you see here, there's something going on here on the surface of the sun, right? So
yes.
How yeah, go ahead, Michal.
Just for the explanation, what you think is this image is optimized for the solar disk. So the protuberances that you see at the edge, you see they have such a kind of shape around. So this is the processing of the image that was done. It was not optimized for the limb, for the border. It was optimized for the disk, and that is why you have this strange shape around the sun.
Okay, so how big do you guys think these protuberances are? Can you tell me? Right here on the chat. I have opened the chat again. 3 times the size of the Earth, Diego said. Okay, so we're going to do a trick here. I'm going to make it smaller again, the sun. This is not scientific measurement, it's just more or less, okay? And I'm going to try and measure the diameter of the sun, just roughly. Analyze, measure, and, oh, I might have closed now, it's here. Okay, so the sun in this specific image has a length of 844.152 pixels, okay? Now, I'm going to zoom in. I have to drag the sun a little bit. Drag again. And let's measure one of these protuberances here. Okay? Okay, perfect. Analyze, measure. Oh, this one has 17 pixels, okay? So if we want to know what is the size, let me just pull here. Just a sec, let me pull my calculator here. Okay, so I know that the sun has approximately 1,392,000 kilometers, 1,392 kilometers. If I divide it by the number of pixels, I know that each pixel has 1,000, approximately, oh, you don't see the, sorry, you don't see it, approximately 1,648 kilometers. This is the scale that is, well, more or less because the sun is not flat, right? But just for understanding the size, how big things are, it already helps. So if I multiply this by 17.3, tells me that the height is 28,527 kilometers. So it's roughly 2-point-something times of the size of the Earth. So 2 Earths and a little bit more can fit in here, okay? So it's, although it appears like a tiny little thing, it's pretty small, actually. This tiny thing is small, but the Earth can fit 2 times here. So just to give you a sense of how big the sun is, right? Okay, I don't have much time. I wanted to do something else with you, but I think I will leave it for tomorrow, where we will continue exploring the sun with transits, occultations, and things like that. Is there any question, anybody that completely lost or panicked? As I told you, I have a PowerPoint. Again, the PowerPoint is already shared with you on the link that you have in the folder. I'm going to close this so I can bring out another thing here, just a sec, because I'm switching. And now I crashed my computer. I didn't. Oof, lucky me. So if you go to the campus, there is one session that is called image processing with SalsaJ, and the images that were given by Michal can be found down here. You see this image that I have just used, this other one, which is really amazing, amazing, amazing image, and this other one. But these are JPEGs, so you have no information. You can possibly calculate the pixel scale, but you can ask for the original fit file to Michal. I'm sure he will be delighted to give this to you.
Yes, and I also put you a link in the same folder, and where you can go directly to our page of the SESA Solar Observatory, and there you have all the data. So you just have to look a little bit. Unfortunately, we stopped observing every day when the COVID situation started, because our solar telescope is not yet completely automatic. So we need somebody really to be there to start it up and to close it down. And since we were not allowed to go to work for several months, and now it's still quite restricted. So unfortunately, we have the images are all mostly from last year or the years before. But I put the link there. I hope it's
not here, the link, Michal. But we'll check. I'll check once we finish. I will check. I see here the Caesar name, but I don't see any link.
I made a mistake. It's a link. It says Solar Observatory. If I look at the image processing, I see a link just before the images.
Image processing, just before the images.
Here, there, Solar Observatory.
Ah, it should work. Okay, well, I will check what's
yeah,
on.
This is it. This is it.
Yeah, I will check, but I did it from the back office and not from the page of the students. From the page of the students, I have to check. Maybe we have to delete and do it again, because it appears here. It seems that it's trying to bring. I know what it is. Why it is. It's because it's not a safe page. You don't have HTTPS,
yes.
So it will not allow it to appear here. You have to enter it as a document and put the link there for people to click, and they can open it outside Graph. It will not open it, because the way you did it, it would open inside Graph.
Okay.
Okay. Okay. So I will stop sharing. And go back here to see if you have any questions. I think this is my time. I love it. Very good. Very, very good. So my time's up.
Yes.
I'll be here. Tomorrow we have more SalsaJ, but I'm very glad to have, very happy to receive your questions or anything that you might want to share with me. So I guess, Michal, that I give them back to you, right?
Yes, many thanks, Rosa. In principle, now we have Jorge.
I am here.
Jorge is here. Very good. So, Jorge Hernandez Bernal, he's working at the University of the Basque Country, and he's working with us in the Mars Express team now since quite some years on a very interesting instrument. When we launched Mars Express, it had, if I remember correctly, 7 scientific instruments. And after, I think, 12 years of operations, we managed to get a new scientific instrument on board, which normally you cannot do because the satellite is far away, so you cannot just go there and put a new instrument. And what we did essentially was, there was a small webcam, and Jorge will tell you a little bit now more about it, that we converted from a purely PR instrument for nice, taking just some nice PR pictures for the press into a real scientific instrument. And Jorge has become, working on his thesis, the expert of this camera. And he will tell you now a little bit about what you can do with it and where you can also find the data. So Jorge.
Thank you. Can you see my screen?
Yes, we can see it.
Okay, great. As Michael was saying, this is about the vision monitoring camera, also known as SalsaJ, which is a camera that is part of the Mars Express mission. I'm going to start by presenting the camera briefly. It's this little camera, which is much little than any other instrument, and it's located more or less in this part of the spacecraft. This camera was launched to Mars as a monitoring instrument to monitor the separation of the Vegel-2. The Vegel-2 was a little lander that was sent to Mars together with Mars Express and was intended to land there, but it didn't success to Mars with the mission. But well, the camera, the DMC, was expected to monitor the separation of the Vegel-2 from the spacecraft. This was in 2003, and few years later, the camera was switched on again for outreach purposes. For example, here we see a very nice animation made from BMC images. These are real images of Mars. And more recently, 2 years ago, we started the project to make the BMC camera into a science instrument, and that's where the University of the base country started the collaboration of the European Space Agency for the project. So I work in the University of the base country, where I am performing my PhD thesis. The special thing about this BMC camera is that it has a very wide field of view, and this allows us to take full disk images. Taking into account that here we have the full disk of Mars also here, and this maybe it's not, we would not expect that, but most instruments in space missions are more or less like telescopes, and they are not designed to see the full disk of planets. But with this camera we can see the full disk, and that's something very special. So in this speech, I am going to, actually I am going to, I want some participation because this is a hands-on. Well, this is related to the speech by Patrice this morning because she was speaking also with this camera, and she presented some activities that we have developed around Mars and Mars seasons. And also this relates to the last activity from Rosa, because I am going to propose some activities that you may be able to perform using SalsaJ. I am not going to present very specific activities, but in general I'm going to present ideas and things that are related to this camera, and I think that you can use to animate your students and also to design your own activities adapted to the circumstances of your classes. In general, I follow this personal philosophy when it's about educational activity and planetary sizing. And what I think is that when we look at our planet, we can learn about what actually matters, and that's the Earth and its inhabitants, that's us and all the other life in our planet. And what can we learn? Mostly we can learn two very important things, that we are alone and on our own responsibility in a planet that is very special, and it's our responsibility. That even if we usually try to look for things on other places, and we think that other places are much more fascinating than our planet, the fact is that our planet and life in our planet is the most fascinating and special thing in the universe, and this deserves to be taught. So I'm going to, I animate you to compare the DMC images to other images of the year. For example, here in this link, I am going to send you this link now. Okay, I'm going to copy that to the chat so everyone can have it. Anyway, I will post this presentation later. I am going to compare images of the year with images of Mars. For the year we have this mission, where you have here images from, for example, like 2 days ago. Always you will find recent images of the year in this link. And here you have images from BMC. And I am going to show you how to find the BMC images also. The thing with these images is that, as I see it, looking at our planet is kind of looking at ourselves in a mirror. By looking at other planets, it's a bit like relation, like social relations with other people. Those things are very important to know more about ourselves, to meet ourselves. And that's the important thing of education, to know ourselves and to know others. That helps to take care of our planet, of ourselves, and everything. So now I'm going to speak briefly about the climate of Mars as an introduction. And first I want to speak about the ingredients. What are the ingredients in the Martian atmosphere? In the first place, I have to say, this has also been told before by Alex, and I think that also by Beatriz, that the Martian atmosphere is very thin. It's mostly made of CO2, carbon dioxide. You can see here the composition of the Martian atmosphere and the composition and the Earth atmosphere. It's very different. And also we have to take into account that the Earth atmosphere is much more denser than that of Mars. The water of Mars. Maybe someone can say something about this in the chat if you want. Like the water of Mars because there's a lot of news every year about this. Well, in summary, yes, there is water of Mars. There's actually a lot of water free mostly in the polar regions. Also, there are layers of water ice in the ground, and there is also vapor water vapor in the atmosphere. But the thing is that liquid water cannot exist on Mars. This was told by Alex this morning, by Alejandro Cardesim, and that's because there is not enough pressure in the atmosphere of Mars. He explained it in a lot of detail. I'm not going to explain it in so much detail, but if you are curious, I can tell more about this. So there is water that it's not in liquid state. And in fact, there are clouds, and some clouds, for example, these clouds here, are made of water ice. Sometimes these clouds are also made of carbon dioxide. This might be the case of these clouds. And sometimes there is also dust in the atmosphere. There are a lot of dust in Mars. And this has also been told before. Alejandro Cardesim showed this photo this morning. And also you can see here an image of the Curiosity rover with a lot of dust. This has also been told by Beatriz. Due to the orbital tilt of the Earth and Mars, it's the same effect. We have also in Mars heat zones like those on the Earth. But there is a difference in the orbit of the Earth and Mars, which is that the orbit of Mars is more eccentric than that of the Earth. This means that the Earth, its orbit around the Sun is not exactly circular. It's always more, sometimes it's more near the Sun, and sometimes it's further. But in the case of the Earth, this effect is not very important. In the case of Mars, this effect is important because, as I say, the orbit is more eccentric, and this affects the climate. Also, important thing, the Martian year lasts around 2 years, under 2 years, which is around 23 months in the year. And also told this morning, the Martian sol is a bit longer than that of the Earth. So I'm going to introduce a new concept that has not heard before by Alejandro or Beatriz, which is the Martian year and the solar longitude, which is the way we made a Martian calendar. For example, currently we are, well, Martian year is MY, okay? So the current Martian year is 25. And the solar longitude is basically the position around the sun. For example, the solar longitude here is 1, here is another solar longitude, and so on, so on. So the solar longitude relates to the part of the year. So the 20 October, the year 2020, on Earth is the Martian year 25, solar longitude 300. Here we have some summary of all this. Here we see the two planets. The year here is like 12 months, and the Martian year is like 23 months. And around the year we have the different moments of the year. The 20 of March, which corresponds to an equinox. The 20 June, which corresponds to the north solstice, the moment of the year when the sun is moving to south, and so on. And this also corresponds to the different seasons. In Mars we have the same, but instead of having months and days of the months, we have the solar longitude, which is LS. Okay, and here we have the aphelion and the perihelion. Aphelion is the moment of the year when the planet is farthest from the sun, and perihelion is the moment of the year when the planet is more near to the sun. And this is more important in Mars than it's on the Earth. And let's remember, of course, that while the Earth year is 12 months, the Martian year is 23 months. This means that there is no correspondence between these two bars. Again, here we are in the 20th October in the Earth, and in Mars we are in 300 solar longitude. And here, but next year, the 20th October will not correspond to the solar longitude 300. Here we have a brief calendar of Mars. We will come back to this later. Well, now we come to a little practice that I'm going to make with you, because this is kind of basic for the next of the activity. I'm going to share with you these links, because these are an application to convert between the year calendar and the Mars calendar. And we are going to calculate our Martian birthday, okay? And I want you to show the Martian birthday, your Martian birthday in the chat. So we go to the first link that I sent, and this application converts a Martian time, a year time to a Martian time. Okay, I'm going to do it. For example, I was born in the 1994 in January, the day 30. And that is why I was born at the 5 in the morning, but it's not very important. We are going to ignore the time. We push this button, and we see that I was born in the Martian year 21, in the solar longitude 210. So try yourself and tell in the chat when is your Martian birthday. If you need some kind of help or anything. But I don't know if anyone is fine. Now, the other application makes the opposite thing. If I introduce the Martian year and the solar longitude, I can obtain the year time. Okay? Very good. Diego said that his Martian year is in, he was born in the Martian year 17, and Silas says that he was born in Martian year 18. Okay, but you are saying the month, and I would prefer you to use the solar longitude because it's like more common, the solar longitude. Now you can introduce the Martian year and the solar longitude in the other application, and you will find, of course, the time you were born in the year calendar. Now, when is going to be my next Martian? Very good, Diego. When is going to be my next Martian birthday? Well, my Martian birthday usually is in 211 LS. So taking into account that currently we are in the Martian year 55 and LS 300, my next Martian birthday is going to be in the Martian year 36 and in the solar longitude 211. And that's going to be in the 2022 in the 18 April. You can also make this exercise yourself. And well, I think that this is an introduction because it's important for what I want to explain today. But I think that this is also something funny that you can do with your students, and that it's also good for them to learn about the planet. And of course, I'm 14 years old. You will see that in general you have less. Always you have less years in Martian on the articles. Of course, the Martian year is longer. Now, let's go to the BMC thing. How can we access the BMC images? There are different ways. As I told before, the BMC camera was used for a lot of time for outreach, so it has brighter and it has flicker. And the images, when they arrive, are upgraded to brighter and flicker. But recently, we have started to use the Planetary Science Archive from ESA, and that's a very nice way to access images. So I'm going to send you the link to it. There you have the link. I'm also going to access okay, so this is not the right link, but okay, that was not the right link, but this one will work. Now, in the PSA, if we introduce BMC, we see two different instruments, BMC over Mars Express and BMC over Venus Express, and of course we want Mars Express. So we press Mars Express and search for images. And here we have a lot of images. There are tens of thousands because there are a lot of tiers of images. If we push here, this button, we can see them more properly. And also I suggest always to select processing level and check level to be calibrated. Because, for example, this image is not calibrated, and you can see that it's a bit dirty. But the calibrated images, they are much nicer. So we check levels recalibrated and we check here again. And now we have only the nice images. And we can search by time. For example, I am going, let's search for images in my last Martian birthday. My last Martian birthday was on Martian year 35 in solar latitude 211, which is 31 May 2020. So here, so this is going to show me an image taken in the 2020 May day 31, which is the my last Martian birthday. But oops, there are no images for this date. So this is happens often because DMC is not imaging all the time. Sometimes it kind of takes a rest. So I have changed it, the time interval. I have made it a bit wider. And this is more or less how Mars looks like during my last birthday. Okay. And again, this is something that you can do. You can do it now to check the test that I'm showing you. And also this is something that you can do with your students, so they can see how Mars looks like in their last Martian birthday. Well, here, I am going to send you this, and here you have the whole instructions on how to access the data. Well, in my case, as I told you, my last Martian birthday, there are no images in the archive. So what are the common features that we can find on the BMC images? One of the most common features and more clear are the polar caps, because they are clearly white over the rate of the planet. But also we have the target volcanoes, which are these 4 volcanoes, 1, 2, 3, 4, 1, 2, 3, 4, and they are also very clear in the images. Also we have Valles Marineris, which is a very important valley that they are Mars. I think that this morning Alejandro also spoke about it. There are other features, but I just make it quickly. Those are the most common ones. Now, I am going to speak now about some objects or some meteorological events that we have sometimes seen in DMC are interesting and are mostly part of our studies with the Macrocam. Again, I am going to show you these images, but also I am going to show you how to search for them in the archive. So this way you can use these events, these meteorological events, as part of some kind of activities for your students. The most striking phenomenon in the Martian atmosphere are the global dust storms. And the last one was just 2 years ago, 2 years ago. For example, here we can see 2 similar images. This one is taken 1 year before the dust storm, and this one is taken during the dust storm. This dust storm only takes place some Martian years, not always. So it's like they are not very predictable, and they are a very common topic of study. This global dust storm happened on Martian year 34 in levels from 184 to 214, which is more or less on June, August in 2018. Of course, we can use the applications I have told you to make these conversions, but let's make this search for June and August 2018 in the archive. from the 1st of June to the 1st of September. Yeah. But in 2000, okay, I did it wrong because it's from June to September, not from September to June, obviously. And here we have a lot of images from the season, but I'm going to constrain it from June to August because of. And here we see those images from the dust storm. And basically you can see that the contrast of the Martian features is lower than usual. And you can explore these images and see different features of the dust storm. And you can also search for images of the same season in the previous year, and you can compare the images with and without global data storm. Just as curiosity, the Opportunity rover, which you might know, died in this data storm. So these data storms are not like a very comfortable time, but they are a real problem. Of course, there's a problem for our mission, so now they are just something that happened. Well, these are the global dust storms, but also there are regional dust storms and local dust storms. These are storms that are more little, and these do happen all the years. Like 2 or 3 times there are regional dust storms all the years. While the global dust storms only happen like every 5 years, 7 years, something like that. But it's kind of random. There is no known way to predict when a global dust storm will happen. In this case, in this animation, we see this is an animation DMC image, where we can see the dust storm movement. You can see here that the dust storm is moving. Maybe you cannot see it very clear because I am not sharing in video mode, so I'm going to copy it here, copy for you. In case you want to check animation. But anyway, I will send you this presentation later. Well, what can we as humans learn from this dust storm on Mars? Because, of course, sometimes this is amazing that there are these huge dust storms on Mars, and we can see amazing images of them. But can we learn from something from them and something that helps us as humanity? Yeah, the answer is here. In the first time, the nuclear winter, which is basically a climate effect that will happen in a case of nuclear war. Basically, it will cause a kind of winter, and that will produce problems with food supply, and among other many things. This nuclear winter was in fact investigated based on the Martian dust storms. The same people who were modeling the dust storms on Mars had to make models for the nuclear winter on Earth, and that was in part one of the reasons why the new politics of limitation of nuclear arms was why they limited the amount of nuclear weapons that each country could have. And also, we can learn from Martian dust storms to prevent dust storms on the Earth, or to understand our dust storms, because these dust storms on the Earth are something that really affect people here. There are real threats here. I am not going to enter now, but you can search and you can check the screen, and you will see some examples of how the data storm ideas are an actual pair here. And here you can see a data storm entering the ocean from the Sahara and the Sahel. And this image is from the satellite I have told you before, the instrument that takes full image, full disk image here. Another thing that we can see in DMC images from time to time is gravity waves. Don't forget that gravity waves are not the same thing as gravitational waves. And gravity waves are like oscillation in a fluid, for example, in a glass of water or in a swimming pool. In the moment when you put a finger inside a bit of water, you produce a kind of wave that moves in the water. And this is also important for planetary atmospheres. And in the year, we usually see clouds like this one with parallel patterns with lines. Here we have a more rare example, but this is a very common image. Probably all of you have seen this kind of clouds, and these are gravity waves in the atmosphere. Well, in Mars, using the DMC camera, we see them from time to time, so you can see an example, and here you can see another example. With your students, you can use this idea to call their attention to clouds on here and how they make this wave pattern, also maybe as a way to introduce the physics of waves, which are amazing physics. And well, I'm sure that there are a lot of things that can be introduced or written in these images, or maybe these images can lead to reflections about a lot of things. A very important phenomenon that we have received with the DMC camera is the double cyclone that sometimes appears in the northern hemisphere of Mars. You can check in June and July in 2012, which is the Martian year 31 solar longitude from 120 to 140. I think that probably we can try to search for it in the previous slide. Yeah. So I introduced the time range that I was telling before. If we look at these images, this is the north polar cap of Mars.
Jorge?
Yes?
No, just since I didn't hear you talk. So all the images that are in the Planetary Science Archive, the images that are already calibrated, run through the pipeline, or are these the raw images?
Yes, these are calibrated images. As I told before, I have selected processing level only pre-calibrated, because if I don't, there will be also non-calibrated images, which are not so nice. And this is important. I'm trying to search for the vortex. Okay, this was easier when I did at home. From maybe because there are some clouds, but these are not which I am looking for. But anyway, let's see this one, for example. Okay, I'm not sure if this is the double icon. I will need to check in detail. But anyway, here we have a huge thing. As I told you before, I propose you also the possibility to use SalsaJ, which has been presented by Rosa, to measure some of these images. And how we will do that? Here we can see, we can click the C-label file, and the label file contains a lot of information, and most of this information is basically unuseful for you, but there are some interesting things. For example, we have the solar longitude, which is the part of the year. Also, we have the Martian year, and this is something interesting. We have the resolution of the image, and we have two resolutions. This with the nadir resolution, which is basically the maximum resolution, and we have the link resolution, which is basically the minimum resolution. At any part of the image, the resolution is between these two values. So we can use these two values. For example, let's say that the mean resolution of the image is like 12 kilometers per pixel. So important, this is in unit of kilometers per pixel. So we could download this image. Important thing, never press here. You can press here, of course, to download the product, but if you do, you will download a lot of products that are not what you actually want to use your students. The easiest way is to download this image here. For example, like saving the image or just copying it directly to a file. And then you can use SalsaJ and these two resolutions to measure things. This is just an approximation, of course, because this is a sphere, and measuring a real sphere is not straightforward, but well, you can make some approximations to measurement. And again, you can use this to introduce the topic of cyclones on Earth and how they also happen in particular regions and particular seasons, because this is something common on Mars in part of the year and in these latitudes. And on the Earth, as I was telling, it's also common in particular regions and moments. We have also the AMEC, the Archean Monocean Elongated Cloud, which was also presented this morning by Alejandro Cardesin. This is a very amazing cloud that we discovered using the visual monitoring camera, the EMC camera. And well, it's really special, I should say, because well, it's special for a lot of things. But one of them is that it's really long compared to its width. It's very elongated. And such elongated clouds are not so common in the atmosphere, at least not in here or in Mars. Some people were wondering if maybe it was like a volcano, a volcano. This is the Alcamons volcano because this is the area of Tarsus, about which I spoke before. But Martian volcanoes are there. There is not more volcanic activity in Mars now. So this is not like a volcanic plume, even if it might look like a volcanic plume, but it's just what we call an orographic cloud. This is a motorized cloud which forms in the slope of the volcano. This is a very particular cloud, a very special cloud, and we are investigating it a lot. Of course, you can again use this to present other things on the Earth. For example, this elongated orographic cloud on the Earth, because orographic clouds are also very common on the Earth, and they are also common on Mars, not like this, but other moderate little orographic clouds on Mars are very common. You can check this link to learn more about this Archean elongated cloud. Again, you can use the PSA to search for images of the cloud. For example, in the drive. I hope you have more more at this time. So this is in October in 2018. I think that we will see very fast some notes of the action using the good flag. For example, here it is. Here we have, this is early in the morning, that's why it's not even representative. But if we look for Messi, we can find it's very common here, but you will need some patterns to look for images here. But in the end, you find things like this. Here we have another image. And again, you can use SalsaJ to measure this cloud to find what's the longitude of the cloud. And also another option to measure the longitude of the cloud is to use Marstrek, which is a very nice tool. I have just sent the link in the chat, but let's open it here. The idea is that if we want to measure this cloud, we can use okay, there's a question from Diego. To be honest, I'm not sure if this is the Monte Fuji. I just searched for the clouds on here, but very probably it's Monte Fuji, but I'm not sure. And yes, I mean, in volcanic areas on the Earth, and if you have an active volcano, you can have a volcanic plume, but a volcano is also a kind of mountain, and in a mountain, in every mountain there can be geographic clouds. Geographic clouds happen because there's a mass of fire with of wet type that rises over the slope of the volcano, and when it rises, its temperature goes lower, and then the water that it contains lowers its temperature and condensates into a water cloud. Okay, and this happens both on Earth and on Mars. You can search for this, for example, it's a very common thing. And if you search for it, you will find a lot of examples, and also you can, for example, in Wikipedia, find information about it. It's not a word thing. Well, I'm not sure if it's the same or not. Well, going back to what I was saying, if we want to measure this, we can do it by taking into account the pixel size that, as I have told you before, it's in the information, in the PSA, in the information for the lead. But we could also, for example, do it by comparison. For example, what's the distance from this volcano to this volcano? And then compare it to the longitude of the cloud in the image. But how can we know the distance from this volcano to this volcano? Well, that's why we have Marstrek. Marstrek is this, and here we have a kind of map. And this is a very nice application where we can calculate the distance to between different points. For example, I'm going to measure the distance from the two volcanoes, which is around 800 kilometers. And from that, we could say that the length of this cloud will be around 100 and 500 kilometers. Okay, just to make clear, this is not a volcanic plume. This is an orographic cloud. So it has nothing to do with volcanic eruption. Okay. Another possible activity around DMC is around the polar caps that we presented this morning, an application for this. But you can kind of make your own activities using again the PSA, the archive of images of DMC, and search for suitable images of the polar caps. The subpolar cap is a kind of more complex because there are areas on the polar cap that also become kind of white, and then this can produce this can be confusing. So I would recommend in most cases using the North Polar Cap for this kind of activities. And here you can see that in different solar longitudes, for example, these solar longitudes correspond to the equinox. This is basically the starting of the spring in the area, in the northern hemisphere of Mars. And in solar longitude 90 is the north solstice. This is the moment of the year when the north is most to when the sun is most to the north. So basically it means that this is the early spring, and here we are advancing from left to the right to the summer. And that means that the polar cap is slowly melting, and you can see if you look at this feature, this feature, you can see that it's here, and it's here, and it's here, and you can compare it to the bottom of the polar cap and see that the polar cap is receding. As time advances, it's being more level. So you can use this to see the advance of the time of the climb of the year of the seasons on Mars. But it's a activity because the fact that sometimes we can see the polar cap during this season, and this makes things a bit complicated. And again, you can use this to compare the year, because there's something interesting, which is that we saw Mars from above before we saw Earth from above. I mean, we could saw kind of this with telescopes centuries ago, already. William Herschel, another astronomer, were able to distinguish the polar caps on Mars, but on Earth, the polar caps were barely known until very recently. So just sort of think about how we have kind of known more Mars from above before than we knew the Earth from above, because it was not possible to know the Earth from above until we had satellites. And this is in connection with what I told in the starting, that looking at the Earth is like looking at ourselves in a mirror, and looking at other planets is like meeting new people, and we need meeting people to know more about ourselves and know more about the others. So, as some final comments, can we escape from the Earth to Mars? Maybe someone wants to give some opinion on this in the chat. And yes, responding to Adriana and Ari, yes, I will give you a presentation.
Yeah, many thanks, Jorge. Just looking through the questions.
No, I have not finished, but I am finished. I mean, I am finishing now, but okay. I have still some comments. So can we escape from the Earth to Mars? Maybe people would think that that's an option, but actually it's not very probably an option, because actually Mars is not a comfortable place taking into account that the atmosphere is very thin, it's basically carbon dioxide. There's a lot of that storms, and definitely it's not a comfortable place. And even in the worst scenario of the radiation of the year, it will be easier to live on the year than will be to live in the Mars. So forget about this idea that maybe we can escape to Mars. So please, let's live here for exploration and common growth as humanity, and not for surviving or for private interest, which is basically what some companies are saying that they might want to do. And also, it's a very important thing. We need, in this context of first travels into solar system, we are in a critical moment of history, and we need slow reflection, and we need a different kind of thinking. We need big picture, collective thinking, and long-term thinking. And I am sure that we need much more than STEM, that science and technology, to drive our future as humanity, because science and technology are not enough to understand our real problems. The fact is that, for example, I am a scientist and I want to end with hunger in the world. Maybe I develop some kind of technology to improve the productivity and have more food. But that is not going to solve the problem with hunger in the world, because I was not going to the root of the problem. The root of the problems, for example, in the case of hunger in the world, is not that we don't produce enough food, we produce more than enough food for everyone on this planet. The problem is a way of organization, a kind of economy, a kind of politics, and in definitive, the selfish of humanity. And what we need, again, is much more than science and technology. We need reflection, we need philosophy to be able to go to the root of the problems and then use science to solve these problems. We are facing an ecological crisis that we have made ourselves, and we only were able to change our planet into this ecological crisis thanks to the aid of science and technology. Science and technology is great, but it gives us a lot of power, and we need more responsibility to be able to use this power in a proper way. Because if we use this huge power in a responsible way, in a selfish way, as we are doing, we only make problems on this planet. We are powerful than ever before, and we need to be more responsible, and science and technology cannot give us this. We need to educate our children in a way that the scientists know about philosophy and art, and in a way that artists and philosophers know about science. In general, we need, as I say, more than STEM, much more than science and technology, and slow reflection, big picture thinking, realistic thinking, and long-term thinking, and being honest to ourselves with the fact that we are producing these problems, and we are producing this because we are using science and technology in a responsible way, and we need to use reflection to do it in a proper way. So in summary, don't occupy Mars, forget about going there to save our asses, but make Earth great again. This is a very important message that I think that scientists and more people working on Mars who need to give to people, because some people are trying to say that there is something different, some kind of solution to this problem that doesn't involve a change in what we are, and it's false. We can't save our asses going to Mars. We need to get it and save this planet. So thank you a lot.
Yeah, many thanks, Jorge. I think this was a very good end statement, because you're absolutely right. We're always confronted with those comments that when we will go to Mars and when we will colonize Mars. I think from a scientific point of view, as you said very well, there's not much sense colonizing Mars, having this wonderful Earth, and I absolutely agree with that. So also it's very interesting from a scientific point of view, but for living I think I would never like to go to Mars. So questions for Jorge? Just read through the text. People are quite happy. So I think one of the major things that you can take away from this nice overview is that Jorge showed you the access to the ESA Planetary Science Archive. And this is really impressive. I think it's absolutely impressive. When I was a student and I studied at the University of Vienna, I still had to go to the library for everything I needed. This is, of course, is more than 30 years ago. So everything had to go to the library and then take a paper copy on the copy machine. So now you have practically all the data accessible online. So this is really amazing. You can go to our archive. You can download all the Mars Express images from VMC, which is, I think are the nicest images because they're very simple to understand. But yet you have also all the other data also there. You have the high resolution stereoscopic camera images. You have all the spectroscopy data. So in principle, you can be a scientist without needing anybody or asking anybody for permission. You just go there, you download the images, you learn which software tools to use, and you can do your own science with the images. This is not only true for the planetary observation, it's also true for everything the astronomical missions of the European Space Agency have ever observed. This includes all the images from the Hubble Space Telescope. This is a collaboration with NASA, so we have the complete archive there. So I can only invite you, please go there, connect to it, and play with it. We will have another session also this week from Beatrice about the ESA Sky, which is also a very nice interface to those type of data. So we will also learn how to do that. But if you have a question to Jorge now, because then if you don't have any question, please share the link. Yes.
I will ask Michael. I will ask you how to share the presentation with them, because right now I'm not sure, and so I can make the presentation available for them. Yes, presentation includes how to access that and everything.
Yeah, I will take care of that. Jorge, I will tell you a directory where you should just upload it, the presentation, and then I put it on the Grasp system so that everybody can have it. Okay, very good. David says that, we have to take care of the Earth, but in some million years we will need to be an interplanetary civilization. Yeah, I don't know if we need to be. It would be nice if we make it to some million of years. I doubt it personally, but somebody has to be more optimistic.
I think that in the future it makes sense to colonize other planets and to expand, because in the end of the day, we are not going to. The Earth is not going to be infinite in the future. Someday the sun will explode, but we need to do things properly, not because of private interest. That's it.
Yes, I think that the difficult thing will be that humanity survives the next 100 years. If we manage that, then there's a chance that we might colonize Mars at some point. Okay.
If there are life in life, if there is life in Mars, maybe this is not. Okay.
So we have again the clock. Many thanks, Jorge. So we have a short break now. I think we have a 15 minutes break. Let me just check. Yes, until 5 o'clock. And then please at 5 o'clock, we all come back for a hands-on session with Bear, where you can see a little what you can do with your classroom. Is a nice exercise, Mission to Mars. So to give the young people, the students, a vision. So if we want to go to Mars, what should we prepare for that? So let's come back in at 5 o'clock, please. Yeah, hello.
Hello.
So good afternoon, but good afternoon for Europe. I always forget about this. We have a lot of people also from all over the world. So we are coming to the last session for today, and it is a hands-on session where we have Beatrice again, and she will show you a little exercise that you can do in your classroom with your schools, and it's called Mission to Mars. Where?
Yeah. Super. I am hiding the grass for you to follow some things here. I don't know, but do you listen to me well?
Yes.
Okay, super.
It's a little low.
It's a little low. Okay, thank you very much. Okay, so I'm going to share my screen. Share screen too, and I will use, I think I will use image until we go for some video or something like that. So I'm sharing using, where do I see the mode, David? I'm sharing using, you're seeing the screen. I'm sharing.
Yeah, only when you start sharing is that you can decide if you're using one mode or the other. So if you decide to have video, you just stop sharing and share the other mode.
Okay, so I will start for images because we saw, otherwise it didn't have good resolution. And then if it's not well seen, then I will switch to the motion. Thank you. So I'm sharing now screen 2, okay? And the activity that I'm going to present to you now, it is called Landing on Mars or Mission to Mars. We have given it several names because we have several activities within this scientific challenge, and depending the ones that you are selecting, you may call it Are We Martians, Mission to Mars. Always is where to land, depending on the objectives that you have, whether it is for searching life or, but we are going to call it Landing on Mars or Mission to Mars. And it indeed is exploring Mars with Mars Express and ExoMars. And also for you to better understand how the different teams, the operational teams work in ESA. So we are going through Mars, the different teams, and then where to land depending on the subject or on the goal that you want to achieve. So for example, if we go to Mars for looking for life, we can say that a Greek philosopher, Anaxagoras, in the century 16 before Christ, before Jesus, raised a theory not yet demonstrated. It was called panspermia. Pan, all, and sperma, seed. It is the hypothesis, not proof, that life could have been originated somewhere in the universe and reached Earth, embedded in the remains of comets and meteorites. This is a challenge for you students. So would you like to travel with us to Mars and search for life traits? Do you dare to do it? So as we were saying, we are presenting this to students as a challenge, again, for solving or trying to improve the skills for 2020 and with different phases. They will work in teams. We recommend they to do that, each one with a role. And this activity is for the age range from 14 to 17. It is a practice, medium, a complexity, and it will take 2 hours, 4 hours, depending how much you prepare and how many activities within this challenge you do. And also for the teacher, preparation, depending as well of how many activities you want to run. This is one of the activities that we have for Space Science Experience Online. And both guides are given to you through the online Space Science Experience that will be explained tomorrow, as I said. And thanks for joining for the teachers to our community already, so you can follow it better tomorrow. So it's an indoor activity, and you need computers, internet, and Google Earth Pro. The curriculum relevance is physics and chemistry. So again, the scientific method, it's a laboratory work, heat and its temperature. You will see later that depending on the place that we decide to land, we will have to take some decisions based on some requirements. Mathematics, technology for learning process, geography and history. We again use Google Earth, but in this case with Mars. So we also consider our physical environment of movements of planets, in this case of Mars, so Earth and Mars, because we are going to launch our satellite from Earth to Mars. And biology and geology, there are several topics that I'm not going to talk in this presentation, but they are in the document that is attached in the grasp area, where you can see what is the origin of life, what molecules can be found and not to identify that it is life, or we think it is life based on those type of molecules or habitable zones. So you have a lot of activities that you can use in class, but today I'm not going to go through those. So the students should already know physical maps. I'm going to use again topographic maps, distinguish between latitude and longitude, basic concept of biology, what is life, if you pick up this activity, and understand graphical representations, okay? And then they will learn the most important factors of life, importance of working with a multidisciplinary team. This is because we are going to divide them in groups, and each group will be assigned a challenge. Let's say they will be given one task. They are going to be the flight dynamics team, the one that takes care of where to land, only thinking about the safeness of the satellite, or where to land depending on the scientific that you are going to obtain. So it's the scientific team, it's the flight dynamics team. So we will divide them in different teams, and they will see how at the end they need to work together and arrive to a conclusion. That's why we say multidisciplinary team. Analyze the importance of studying all this data and it's useful for the society, okay? And then again, the strategies and the skills that are expected for the 2020. So what did you know? I'm going to come back to the previous search that we were doing, that because I was showing you the questions, we couldn't see the answer ourselves. And just to refresh and go through those, is one of the questions is how big is Mars in comparison to Earth, because we're going to Mars, so we need to understand a bit how is the planet where we're landing. And most of you said half size, what is correct. Then how far is Mars from the sun? And then the correct answer is 1.5 times the distance from the sun to the Earth, that is 1 astronomical unit. So these two were correct. And you could vote several times. Mars is red because it has a lot of saffron, the iron oxide on its surface, and it's an optical effect. So you all agree, and we're right, the iron. How much would I weigh on Mars if I am 50 kilos mass? So most of you identify that it is 1/3 of the gravity on Mars because of its size, and it's the same mass, not half of the mass, it's the same mass, but less weight in the sense of mass multiplied by the gravity. The atmosphere of Mars in comparison to the Earth is, you thought it was 10 times, today, this morning we were told that it was 100 times less dense than the one on Earth. So it's quite thin, and also Jorge just told us about the composition as well. Does Mars have magnetic fields? Yes, but weaker than those on Earth. No, but it had in the past. No, and never had. Yes, the reason to be losing its atmosphere. So it's no, but it had in the past, and also this was correct. I didn't type it properly, but it's correct as well. No, and this may be the reason that we are missing the atmosphere. It's been removed with the solar wind. How many missions did fail to arrive to Mars? This morning, Alejandro told us that more than half. So this is the most popular answer. Which of these missions to Mars are led or have a strong collaboration with the European Space Agency? And most of you, ExoMars, we have already ExoMars TGO, Trace Gas Orbiter, sent launch in 2016 to Mars, and Mars Express that is already working perfectly, and also VMC is on board since 2003, observing Mars and orbiting it, taking a lot of images and data. So these two are correct. And have water been detected on Mars? Yes, as liquid water on its surface. Yes, as liquid water under the surface of the southern pole. Yes, as ice in the polar caps. No, never. Yes, as water vapor in its surface. So you see here that Mars Express detected a possible lake of liquid water under the southern pole. And yes, we can detect it as ice in polar caps and craters as well, and also vapor on the surface. Because of the pressure of the planet, we were saying this surface pressure, it cannot be liquid on the surface, but it is water there. And what are the reasons for the seasons on Earth? Okay. The inclination of the axis with respect to the orbital plane, and also because it's moving around the Earth, just the two of them. But inclination is the key. Do you think that Mars has seasons like those on Earth? We saw that it has seasons, but they are more mild because they are farther and also more eccentric, the orbit. Jorge was mentioning this before. When it is summer in Spain, in the northern hemisphere of Mars, we were saying that is one ahead, no? So it's, excuse me, so correct. So it is fall. So it's one farther. But Jorge also told us that it didn't fit as well, no? It's because it's different length, but more or less it's one ahead. How would you study the variation of seasons in Mars? And yes, we all use the variation in the polar caps in this case. There are other ways. This apparently is applicable for summer only, but okay. But we, with the VMC camera that has the whole picture of Mars, is observing the variation of the polar caps. Okay, and the VMC camera is a web camera on board Mars Express. Mars Express is the right answer. Okay, how long do you think that a Mars year lasts? So 2 years. So you already know that it's almost 2 years. Okay, so I'm coming back then to the presentation. This is what we know, what we need, and we knew, and now we better know from Mars. And also, as we are going to land on Mars, here I have an image of how was the trip for Mars Express and how much did it take when it was launched in 2003. So let's start the challenge. As I said, I wanted to talk to you that missions, ESA missions, and also, or especially those related to Mars, but in general, are divided in several areas and several tasks. Each one has a role. So we have the Science Operations Center, SOC, that for the Mars mission is mainly here at ESAC, the European Space and Astronomy Center, where there are scientists and engineers that are doing the planning of what all the instruments on board the Mars missions, Mars Express and ExoMars, are going to observe. They are in contact with the MOC. MOC is the Mission Operations Center, and this is in Darmstadt, in Germany. And they take care of the orbit of the satellite and the different maneuvers that the spacecraft need to do. They are also, apart from engineers, they are also operators that are continuously checking the information from the spacecraft. They are called SPACON, spacecraft controllers. So any alert on the instruments, on the platform, the position is triggered there with a software called SCORS, doesn't matter. And this is, they react immediately. So it's all the satellites are well cared 24/7. And they are continuously in contact with SOC. So, and apart from that, before the launch, we need to test all the integration and that all the instruments are going to survive the launch. and they don't interact badly with each other with some interferences or whatever. And the test, the integration tests, are done at STEC, the European Space Research and Technology Center, that is in the Netherlands. So they are mainly engineers. So I want you to do a quick Mentimeter again. This is going to be very fast. We're going to do it together. And it's menti.com, as Rosa said, not Mentimeter straight away. So just because most probably you're already a bit tired, there are only 6 quick questions, and it's related to role models. So I'm going to do this with you here. And I'm going to show you some pictures, and we are going to decide together which is the role. I mean, in what team are they working? These are dedicated to Mars. In what team are they working? Of the 3 that we mentioned, or others? So I don't know whether you are accessing through your tablet or through your computer. I don't see the chat at the moment. I don't know whether you feel like doing that or not. So chat, please. What is the number? Okay, this is a very good question. Yes. The number is 51. I'm going to edit 5131907. It's very quick. So it's just for we to wake up a bit after all this interesting science today, but I know it's a long day. And tell me if you're ready. And we can do it together. So the first one is easy because we had him this morning. And I don't know whether... Okay, ready. You're ready? Okay. It's very simple. So all of you have a computer, I suppose, because we are following this and the Mentimeter. So I'm going to show you the Mentimeter, how it works. Most probably you do know how it works, but sometimes you may choose different options. At the moment it's designed. This is the Mentimeter. This is your presentation. And I have selected show image. If I select show image, you can see the image, but you cannot see the answer. This would happen before. And if you say configure audience pace, here is where you can see everything. So the questions and the figure as a student that are answering. So you're answering now all these questions, and I'm going to the presenter page, and we will go together through this. So you won't see the questions, but the question is about what of these 4 teams are people working. Is the scientific team, the integration team, the flight dynamics team, or other? So this is one of the questions for Alex. Press enter. Okay, next one. In what team does she work? In what team do they work? In what team does he work? We will see the answers at the end. This is arrival of Rosetta to the Churyumov Gerasimenko. In what team does she work? In what team does she work? Okay, that's all related to your question. So we are going to see together the Mentimeter. And as I said, you need to come to the presentation. I need to come, okay, I'm going to show it here again. You need to come here to the presentation. Because it's already, okay, excuse me, it's already in the presenting mode. So I cannot leave it. Okay, I can, okay. So, and if you want afterwards to see together the answers, you need to remove the show image so we can see the answers together. This is what happened to me before. So I'm just showing this, that is a very easy application, but sometimes you need to know also all the details. We are using this in our Space and Experience Online, but you only see as you are seeing now. Your students will only see these questions. And later on, you can send to yourself the answers on an email, so it will a PDF. So he works in a scientific operations team. Yes, we met him this morning. Height correct, okay. What team does she work? Flight dynamics team. Yes, it was the woman with all the computers at ISAC. Super, very good at it. In what team do they work? They were in the integration. It was very obvious. Yes. In what team does he work? And it was in the flight dynamics team. I mean, I'm talking about him, the guy that was jumping, because it was arriving, Rosetta was landing and Churyumov Gerasimenko, but in reality, if you look at the picture, there is a group of men, women, different ages. In what team does she work? Test integration, yes, it was a woman with the solar panels testing at STEC. And in what team does she work? This is our colleague, Julia. And she is working here at ISAC in Science Operation Team for Mars Express. Okay, so that was all in terms of role models and waking up a bit. And the idea is that your students get to know that we have several roles and the teams work together, different skills, and we have men and women working together for Mars missions and all missions at ESA. So now we're going to take care for the ExoMars launch, and then we're going to be the flight dynamics team. First, we have to decide where are going to launch the satellite from Earth, because we need to put it out from our planet first. And I would like that you answer in the chat in what latitude, at what latitude do you think the Guiana, okay, this is super specific, super, for ESA. But more or less, I mean, it's enough if you say more or less a range of degrees in latitude. Or whatever, close to the poles, close to the equator, 0.5. Good for Diego. What about the rest? What do they think? They don't know. Okay, I'm not going to take more time. Close to the equator. Okay, you all see it very obvious. Yes, super. So it is close to the equator because the velocity is here higher. So we are using close to the equator. We are using the area on Earth where the velocity is higher to send satellites outside. Yes, close to 0. Perfect. Okay, getting to Mars, we want to get it in the shortest possible time because we want to be safe in terms of cosmic rays, also to do not use a lot of fuel on it, and for in general for safety reasons, we do it as fast as possible within some limits. Let's say we are also using. We're also taking care. We need to send some elliptic orbits from the Earth, an elliptic orbit, sorry, from the Earth to Mars for that. And first of all, I want you to see this video about it. It's a minute. And is this the video? Yeah. And for this, maybe I need to. Wait. What happened? Okay. But it is, there are 1 minute videos, and it is another one before. Tac. How do you land on Mars? Is no. Mars in a minute. How hard is to land curiosity? Okay. There are a series of videos that are very nice to see what is difficult and how you should do it, how you should land, or what do you need to take into account when you launch a mission to Mars or any planet that does not have the same atmosphere as Earth. Apart from that, we also have a simulator from Universidad de País Vasco, and I'm going to show you this, and I'm going to put here also the link. It's in Spanish, but it doesn't matter because for what you need to do is not you don't need more than time in days, position of Earth, velocity of Earth, position of Mars, velocity of Mars. So it's really no. And how does it work? So you reset it and then you say play, and then the two planets, this is Earth and this is Mars, start moving, and you need to launch something, the satellite or the satellite to Mars when you think is the right position. We were saying that more or less each 2 years they get closer. Okay, now it's too late, so we need to wait again for Mars and Earth be close, but they need to go from Earth to Mars with an elliptical orbit. So not all the time is possible to launch. And now I'm going to try. We'll see what happened. Blah. No, it was late. Okay, you can reset it here and then again. So this is a easy and fun way where you students, okay, I already, for speaking, I already missed the launch, launch window. So they understand why you cannot launch at any moment a rocket or a mission to Mars. Going to launch now and we'll see. No, it was closed, but no. Okay, so you know how is it? I don't want to spend the whole afternoon here, even if it's fun, but I don't want to do that. So you also have the simulator to see how flight dynamics and need to define the orbit and the time that they launch, how difficult it is to land and those things. So you can develop this with your students and you can ask them questions and they can answer. Or, as I said, all this information very well explained is in our teacher's guide and students guide for them to follow that. And as we were seeing, Mars and Earth has different speeds. Approximately every 2 years, they get closer. In order to get to Mars, we have to make sure that we point out our spacecraft well, as we were seeing before. Also here we have the simulation for Kepler, but this is mainly to see how the different planets, the orbits of the different planets and how do they work. I have it here. Yeah. So you can explain different things from the curricula if you want with this scientific challenge of landing on Mars. So here we are going to start animation. And here we have Mars. And we start sweeping. So we see the areas that are swept at the same period of time, taking the same period of time. And if we pause it and we change this to Earth, you see that it's the eccentricity is lower, is close to 0, but when you select Mars, is 009, so 0.1, close to 0.1. And you can, Earth, again, okay? You can again start the animation and see how they move. This case is the Earth is faster. Okay, pause animation. So all this activity, as I said, give you some, as the other day Michael was saying, astronomy and space missions are very attractive. So it's a good way for them to pay attention to curricular activities. And this is what we were saying before. From Mark's experience, we see that it was almost 7 months to arrive from Earth to Mars using this trajectory, even if here they were the closest, and the difference in season. So where to land on Mars? We propose you to work with your students, as we were saying, in teams. Each one of them will have a task or a mission to do. So to land on a planet, we need to be flight dynamics team for sure, but in some missions, we also need scientists to decide what is the best place in terms of data return, scientific data return, or if you send a manner crew, no? So as a mission that has people, that have people inside, no? So it's they're going to colonize, or they're going to stay there, not for the reason of colonizing, because we are approaching this activity as we really want to know from where we come from, and maybe we come from comets, or we come from Mars, so that's the reason why we want to go there. We don't want to invade it without any reason, but to better know about ourselves. So this is team 1, and it's, we call it here an expert team that is in charge of the flight of the ship, so the safeties of the ship. So what do they need to do? They need to decide where they're going to land in latitude, longitude, and altitude. And they only need to think about the safetiness of the spacecraft. As we saw on the video, when you land on Mars, because you have already some velocity, you come from some velocity, and the atmosphere is thick, it's not as on Earth, so you need to brake to slow down your satellite and also to land safely. Okay, so this is the mission of this team. So we asked you several questions the team 1, to help him a bit. We tell them, where do you think that the difference in velocity between the satellite and the planet would be lower? I mean, we're coming very fast from Earth, and we said before on Earth, and it's similar on Mars, that close to the equator, the velocity is higher. And another thing is, do you see any difference between the 2 hemispheres of Mars? For this, they are going to use Google Earth Pro observing Mars, so they can well inspect the planet. And we will go later to this. Is the Martian atmosphere as thick as the one from Earth? They may know from what they have prepared before, or you have prepared with them before about Mars, or they know in advance. So the way that we ask you to do it is with some preparation. So these questions they already know. So they need to think about this parachute, or some thrusters, or some extra, but the atmosphere to slow down. So this is team 1. Then we have team 2. It's an expert team in charge of Martian rover, car efficiency, or safety. What does it mean? So from the point of view of the landing, we need to find a place on Mars where the rover can drive properly. So in terms of, it's not only important that you already land well, but that you don't fall on a crater, or any place that is not walkable later on. So they need to observe with Google Earth the different areas of Mars and identify regions that should not be are not possible for landing, and others that could be possible for landing. As we saw yesterday, you can define your path on Google Earth, and then define areas. You can decide red for do not use this area, and green for yes, is a possible area for landing. So each team is working separately. They don't know about what they are doing. The others are doing. They only care about their task, their mission. So we have a team 3 that the mission is, from a scientific point of view, where would it be more interesting to land? This presentation in full screen, I am asked. Presentation view, full screen mode. No, it was not, sorry. Now it is. Okay. So from another mission that is for the team 3. So we have 5, 4, 6 people. Oh, you're welcome. Sorry, I didn't read it before. So from there are 4 or 5 people working together in a team that has this mission. From a scientific point of view, where would it be more interesting to land? So we saw this morning that there are regions where there is water or methane, or there are different molecules that we associate with life. So if we are looking for possible past life or present life, but anyway, in principle, we look for possible past life. We will look for areas where is liquid water or where is water. No, it can be in terms of ice, or because if we base the life on water, around that area would it be? Okay. And the geological history, we are going to take it into account, because also we are going to see the 3 epochs, the 3 periods of geologically for Mars. And we will know which is we tell all these tips to the students. They need to do this mission, and they would know that the eldest area is the one where there are more impacts. So they are going to look at the surface of Mars, as this morning it was done by Sandra, looking for craters, different type of craters. So, and then we have 2 more teams, and they are going to land. They're going to land in terms of not only safetiness or science, but also they need to take care of a non-tripulated mission that has a rover, and not only taking care about that is a flat or a dryable area, but also that they will need energy. They will need energy to move around. If it doesn't have a crew, it will not need water in principle, but this is team 5, the one that will need water because it has a crew. But team 4 wouldn't need water, but would need enough sun for the rover to move if they were solar panels. It can go with another energy, but we are thinking in principle with solar panels. So we need a lot of sun, a lot of solar radiation. Okay, so as I said, we are going to do this in Google Earth. And I'm going to show it to you now. I'm going to put here Google Earth from scratch. So I'm going to Isaac here. So I'm going to Earth. Boop. Okay, coming here now. And I'm going to change it to I'm going to share as a motion. I'm not going to do, okay, I will continue like this. If the video worked, this wouldn't be worst. So we are here with Google Earth Pro. Again, this software installed is free software. And to go to Mars, we go here and we select Mars. We can also select the moon. But in this case, we are going to select Mars. Okay. Here we have different ways to see Mars. Usually by default, you have this visible imagery. These are images from NASA in this case, processed by ESA, DLR. And it's similar as we were doing the other day with the Earth. You can turn this way, then you can go to north, you can go to south. So you can do the same. You don't have this little person that you can step on the planet, but you can go, you can turn around. Or again, you have the information here. You have the information here about the coordinates. So I don't know whether you see it well, but if I come here, I have 13 degrees, 10 minutes, 34.50 seconds. North, this is the latitude of my position. And 86 degrees, 11 minutes, 45.53 seconds with east. This is the longitude. And then we have also the altitude. And in this case, the altitude is 14,616 kilometers. Okay. So what we are going to decide where to land or not is going to pay attention to this area, to the coordinates. So we are going to use this colorized terrain. And we also take some time in the activity to explain the students that blue is not because it is water, but it's a fake color. It is a scale. And the lowest part, that are the darker ones, are -9 kilometers. deep, and the highest one is 21 kilometers deep. So if we come here, for example, we can do similar to what we were doing yesterday. We can define a path. I'm going to move this here. We can define a path, and then here you have this open, so it's just my route if I were one day to Mars. So you click here, and then you do OK. So you already have the route. And if you come here, show elevation profile, so you can see how is this area. If you see, maybe it's not a good place to land. Most probably not, because you may fail here and you cannot move. So you can go through Mars. The route is here, and you can remove it here and not have it contaminated anymore. And also you can look for places here, for example, Valles Marineris. We all know some nice places or famous places on Mars. And we click on search, and it's not moving, maybe because now I need to change the share to motion, or I don't know. Okay, I'm going to stop sharing, and I will select the motion. I don't know whether this is a thing. Optimize for video. Okay, screen 2. Screen 2, okay. I don't know, we will see. I was selecting Valles Marineris. No, it's because I wrote it Bali. It's because I wrote it Bali Marineris with 2 L's. Search. For some reason it's not searching here. Olympus Mons. Okay, I wrote it wrongly, so we will see later. And you go straight to there, too close, indeed. So you can zoom out also using this, as you do in standard Google, with your mouse, with the wheel. And here is Olympus Mons. And show view. Your workplace is too low. Okay, cancel. Okay, you get some information about the Olympus Mons here. Okay, this is a general use, but we were on an activity and we wanted to decide. So it's quite nice because they can inspect Mars with real images taken by NASA, processed by ESA about the surface of Mars. You can see all these craters here. And you also can see here different landers. What it is display is also here. You can see rovers. It tells you what all the information that you have on the map. But we come back to the presentation. And then, as I said, you run Google Earth Pro. And here you select the planet. You change for Mars. Usually this is the standard image, but you can change it to the color. You can change here the color to the one that you better prefer. It's quite visible, these different colors with altitude, which may take it difficult for users to read text. Based on your current hardware, your content is being shared at a lower resolution, which may be difficult for read. Tell me whether you read it. I mean, I can repeat how I did it, so you can do it yourself. Yeah, it's amazing. It's amazing, Google Earth, what it's doing. But as I said, you can edit here, or you just can scroll out, and then move around. Move around with this. You can turn around. If you see the north is moving because it's moving. You can put it again, the north above, and explore the planet. It's amazing, yes. So we come back to our activity, and then we were saying we are going to also define the grid. So we come here to tools, add, view grid. In view you have grid option here. Click. So you can see also now it's much easier if you are defining the latitude and the longitude. You see now that the north was not at the north part. Okay. And then now you are more or less looking in front of the planet. And then you can move it again around and you can see the coordinates. Okay. So as I was doing, you can search for some known places, but also you need to know well the name, because Valles, I thought I wrote it correctly, but I didn't. So if we come again to the Olympus Mons, well, let's stop. No, not to the Olympus Mons. Let's create a path here. The path is let's call it, I don't know.
Yeah.
Yeah, sorry.
Can you share again with for text and image?
Yes, sorry. Yes, I'm doing that. Stop sharing. Share. Okay, optimize text. Okay, because I'm not moving much, so perfect. I can do this. Okay. I was just adding, thank you, David. I was just going to add here like a mountain or hiking route on Mars, no? On Mars, my hiking route on Mars. So you decide the color again, and then you click OK, but you don't close this. And we are going to say that we're going to spend a lot of time doing this path. So they can, again, they can see how is the elevation profile. And they also can compare to -3 kilometers. They can compare to areas on Earth. Okay, but as I was saying, we are coming back to our activities. And this is something on Valles Marineris that I also did. And Marineris Valles. Okay, you have to write it the opposite way. And then you can define more or less the area of your path. No, in latitude, longitude, and altitude. It's quite long, but you can more or less define a region. Eos Chasma, Aeolis Menside, so there are different areas that you have on Mars, well known. But now we are going to solve the different activities that the teams do need to solve. So the first one was to take care about the spacecraft and about landing safely without taking care whether it was on a crater or on a flat area. So similar to Earth, as we were saying, close to the equator, the velocity of the planet is higher, so it would be less impacting, no, or it would be easier for the satellite to fly around the equator, where the velocity is higher also on Mars. Okay. We also see, we ask whether you see any difference between the two hemispheres. That is called the dichotomy. And you see that if looking at the altitudes, that the southern hemisphere has higher latitudes in general. No, here we have some mountains, but the southern hemisphere has compared to the northern that is mainly blue. Blue because it's the lower altitude and not the water. So we can see a difference, and it's when you move it, it is for some reason it is also spinning a bit. Okay, so we can say that if we wanted to land and the atmosphere is very thin and we want to use as much as atmosphere as possible, we will try to land on the lowest place. So with the parachute, apart that we need also some thrusters and other pyrotechnics or whatever, the landing will be safer. So the lower part would be better for the satellite to land, closer to the equator. So this would be the solution of team 1. So we can mark this path here and there using our Google Maps. And as we were doing, you just turn around and define the northern limit and the southern limit. So this is a solution for the first team. The second team. The second team is they need to avoid craters, rocks, and even terrain. So most probably they will go to the northern parts, as we were saying, because it's flatter. It's flatter here. They can also land here but they could say this crater Elas crater, or they most probably will say the north. Wait, sorry, to close. They most probably would say the north, where there are more regions, because you can also think that when you land, maybe you are not very precise. I mean, even if it's quite big, but you may not be very precise, and it's, I mean, in adding errors, most probably you will better land here, but also at the southern part, the Elas crater. So this could be the answer of the second team. They are not fixed answers. So the idea is that they get to know Mars, they play with Google Earth and define areas, and they think a bit about the difficulties to land on a planet or when they don't have the same atmosphere as the Earth, etc. So as I said, you can mark with the path, also with polygons, as we were seeing yesterday. You can come here also, and then here you can define your polygon. So you define the color, okay, and also the inside color, and you just need to mark areas where you wouldn't land. For example, around here, I wouldn't land myself, even if it's very interesting, most probably. So I say, okay. And one of the things is that here, when you do the polygon, you need to define the altitude. So sometimes it's crammed to the sea floor, relative to the sea floor. Okay, now you see it here. Because sometimes, depending where you selected it, you can only see when you are far or when you're very close. So I would select myself relative to seafloor so you can see it. What else do we have? This is a topographic map of Mars. It's a real one. And you can see also here what we already see in Google Earth, and the names of the places. So you may say that you want to land on Amazonias Planitia here, or Acidalia Planitia here, or Utopia Planitia here, because these are places where they are very flat. In this case, we would also agree with the safetiness of launching the satellite or landing the satellite at a lower part, not only because it's flat. So these two things are met, these two requirements. Now the team 3 goes to the expert team in charge of science data return. So we're going to look for liquid water or remainers of having had liquid water, or place where it could be ice. I mean, we were saying that mainly the ice is around the craters or on the poles. But I mean, this team had not already talked or didn't have an interaction yet, but it will have at the end with the other teams. So they may decide that they are going to land on the poles, because they are not having yet the restrictions about the landing close to the equator. No, so they already may arrive to that conclusion. So we're going to look for areas, old areas, because we know that at the Noachian period, that it was the eldest period for Mars known, it was hotter and wetter. And so it may be that there may be trails of dry rivers. And also Hesperian, it has sulfate, so you need water to dilute this, but it didn't have magnetic field, so maybe it didn't have water. So we're going to look for, identify in reality the different areas. And we know that the eldest one will be the one, or the older one is the one where there are more craters. So we are again go through Google Earth, close, okay. We're going through Google Earth, and we're going to look for areas where there are craters, and we are going to identify which, to what period do they belong to. Here as a teacher, you have the answer, as I was saying. So the Noachian is the oldest period, and is distributed along here. The Hesperian is the green one, distributed along here, and the Amazonian is this one. You can develop this as much as you want. You can compare with Earth, the different ages, and you can develop this depending on your time or your subject, or as much as you want. And the solutions would be, again, for example, Elas Planitia here, because you have here some remainders of rivers, so valles marineris, where you have also some reminders here for this team, for looking for science, no, for scientific return based on water in this case. Then we have the generation period. Then we have the other two teams that are interested on colonizing or living for long, not only landing on Mars. That's why they will need for sure energy, some radiation, and they would need, if it is a crew, they also would need water for living there. And then we come back to this, that it's based on a game that we did for an open day here at ISAC. And we basically consider that close to the equator is where we have more solar energy. And farther, so more or less, from 0 to 45 degrees, we have more energy, more sun radiation. And from 30 to 90 is where we may have more water also, because it's less evaporated now. So they should arrive, and it's very easy, to areas where the two conditions are met, having this map. Also, they can come back again to the Google Earth, and then it would be from 30 to 45, where this team most probably will decide to land. So they already have this topographic map, and they will decide one place or another where to land. So we are taking care of the two things, because we are thinking of a crew that is going to stay for long to really search for past life or present life there. If we only take care of the rover, we don't need the water. I mean, close to the water, most probably there are also some scientific reminders, but this team alone should not take it. Team 4 should not take areas with water. But at the end, what do we tell them is, okay, now that you have been working in teams, you are 5 teams, each member of a team, let's go to make a new team. So there will be a team of experts, because each one of them know about requirements and positions that can be where to land on Mars or not. And they will define which is the objective of the mission. So depending on the objective, they will bring to the group the skills, and they will decide one of them. So just very quickly, we don't have yet an activity on this, but as I said, the idea of going to Mars in our scientific case, scientific challenge, is to look for life, not only for colonizing. And we know that it is water, the comets that are at the Kuiper Belt and the Oort Belt. We had the successful mission Rosetta with Philae landing on a comet. We have here some videos that are very nice for you to see later. This is the flight dynamics team that made possible to land on a 4 kilometers by 4 rock of dust of how you call it, of dirty ice. Also the DLR team, that is the one that we saw in Google Earth. They process the data, and they make the nice pictures apart from doing the scientific analysis. And that Rosetta identify water vapor to have significantly differentiated composition to Earth ocean. So the ESA, the European Space Agency, flew to a comet, and it was the first one arriving there in order to see whether the water that we have on Earth, that we have a lot of water, comes from those comets. And it does not come from this comet apparently, but it may come from another comets, or other families of comets. And also it was the mission that first detected nitrogen at a comet. And in general, what it is called, they are called the ingredients for life, that are glycine and phosphorus. So the clock is there. Okay, and then yeah, that was all. I just take this image from Alex this morning. The activity that you have on our website, and we have put also on GRASP, and we will explain tomorrow how to do online, is having a lot of information also about habitable zone, not only depending on the star, but also the atmosphere, as Alex was saying this morning. And that was for me today. Thanks a lot. Yes, I will upload the presentation to the corner.
Many thanks, Bea. Yeah, I like this clock. Which clock is this? Is this clock?
It looks like Alex clocks.
But Alex is muted.
He's not in, no.
This is probably David that found some way to include this.
I'm very happy to be on time.
I will send you.
So, Rosa, is this your clock? It is always nicely at the full hour. No?
So I'm going to upload, and just to finish in 1 single minute, is that, as I said, I'm going to upload this to Grasp. And if you access to it, I'm going to share this with you here. When you access to it, you will see this mission to Mars. And here you have the Mentimeters. I will upload here the presentation. Here you have the quiz that is linked to our website. And is Are We Martians? As I said, this scientific challenge, you can call it many ways, and you can solve it through it. And also here you have the document that I was telling you that we have been working, and we presented to you now a brand new document about what I was explaining and much more. So that I was not sharing my screen, no? So you didn't see what I was saying?
No.
No, okay, I will share in 1 minute, so they understand what I say. It's only 1 minute, promise. So I just want to share with them where they can find what I was explaining. So I'm going to move this here. And it is here at our virtual campus. You have here the Mars seasons. Here you have, no, these are not updated, sorry. Okay, this was before. We also have here Nairas and Rosas. So here you have the Mentimeters, the quiz, and the link to our website, and the document. This is the student guide where you can follow all what I was saying and much, much more. So, and if you attend tomorrow to our presentation, you will also know how to access to the teacher's guide. Okay, so that was all.
Okay, many thanks, Bea. And with this, we come to the last point. And now you can relax because it's just a walk a little bit through ESAC. And in the end, I show you a little bit the tools which we plan, or what is our work really in a mission like Mars Express, for example. But yeah, this is just now to relax and finalize this day in an easy way. So I will just share my screen, and I will swap also the video to the other camera. So because I do this on the other computer, so the rest should be okay. So we share the screen. Let's just see how I can get this working. So share screen. So can you see this?
Yes, perfectly.
Okay, so let's just do a little bit of walkthrough, because normally what we do in the teachers courses, as I told you, is that we show the participants around. So we have normally reserved half an hour or 45 minutes even to walk through different areas and rooms. So this is you have seen in Google Maps. You can go back there and look at it again. You can see all the European Space Astronomy Center from above. So this is the entrance. There's a big roundabout in the entrance. So this is where you go into the parking place. And here on the right side, there's a nice castle, which we can see later also a little bit better. Is it more or less going smoothly if I move? Yeah.
Yes.
Okay. So, and then so I have to again to say many thanks to our colleague David Cabezas, who has done this in a record time. So it's still quite a little bit experimental. So we will redo some of the pictures. And the other thing is also, normally the weather here is really good, and just on that day it was quite cloudy. So this is not the normal weather here. So then you come into our center, and on the right side, you have already the first satellite model. This is a one-to-one model of Gaia, a very interesting mission. Probably scientifically the most important mission of the last decade, because it really made already the second release of a catalog. It is the most complete catalog of stars ever done. It consists of 1.7 billion stars. And so for science, you can imagine how important this is. All astronomers that are working on stars or dynamics of the galaxy, distribution of spectral types. So all this is really an enormous project. It is even more challenging from the IT, from the informatics point of view than from the satellite point of view, because you have to deal with enormous amount of data. So it's a really, really amazing project. And the publications are, per month, there are more publications than with any other satellite project ever, the Hubble Space Telescope included. So then you see here two buildings. You see here, ESA, ESAC. So on the left side here, this is the canteen. And on the right side here, this is the oldest building that we have. If we go in this direction, you can see you here again here on the right side you have the satellite. Which what you see very nicely, so they've put it transparent so that you can see some of the structure of the internal structure. So these are leftover parts from the engineering models that were not used in the end. And so instead of just scrapping them, they were putting them here into this nice satellite model. So by the way, those are the mirrors here, what you see here, these rectangular things. There's one mirror, and here in the back you see a second one, also rectangular mirror. And the interesting part is this is a space telescope and it doesn't look like a telescope, no? Because if you want to make a catalog with 1.7 billion stars, what you need to do is you cannot just go one by one looking at the stars separately. So what you do is the whole spacecraft is rotating over this axis, you can see. And while it's slowly rotating here in this sense, all the stars pass by this mirror and are reflected to an area where you have more than 100 CCDs, one after the other. They're just observing the stars while they're just gliding over them slowly. So that is why the satellite has this shape. And also very important, since it's an astronomical telescope, what you have to do is you have to protect it from the sunlight. So what you see here on the bottom is the solar shield, which so the satellite makes its own shadow, and on the other side of the solar sheet are the solar panels to get the energy for the satellite. And then you can see here the A building, so we can just go in there for a moment. And then you see this is our lecture room where normally have our courses. You can see here we have a nice illuminated globe, because you can project with a computer all types of planets here on this globe from inside. So that we took the maps and arranged them in a way so that we can produce the complete solar system here on this globe. And you have also a model of the Ariane 5 rocket. Yeah, and then here in the back is we're looking here from the speaker's view, and you can see here on the left side, so we have the school classes here. So we have here topographic models. So they made the topography exercise yesterday. And so here we can have a sandbox and you can project the colors of that onto the sand, which is really nice. This was also developed by David. Yeah, and then if we go back and we go along the road here, so you can see on the left side, you see a canteen. Very nice, with nice weather. You can even sit outside. It's really, really nice. And then on the right side, we have another satellite model. So this is Rosetta. This is the famous satellite that flew to the comet Churyumov-Gerasimenko. And this is a model which is 1:4, so it's quite small in comparison to the real spacecraft. The real spacecraft is 4 times bigger. So you can imagine the solar panels here of the real spacecraft were about 35 meters span. And here you see a small lander, Philae, which in reality is about the size of a washing machine. And here you see it's really small because it's 4 times smaller than the real one. And if we continue, yeah, so here we come, so you see on the left side, what you see here, these are some cabins, which are essentially containers because we have too many people and not enough office space. So since, I think 15 years or more, we have here these cabins, which are supposed to be temporary, but we still have them. So, and you hear in the background, what you see is this MOS antenna. You remember a talk yesterday from Jorge Tauste. He also showed this antenna close up. So this is the 3.5 meter diameter antenna of SMOS. And then we see there's some other satellite models later on. And here on the right side, we have what we call the B building. So here the oldest building here on the right side is the A building. Here. This was the oldest model building. And then here this was the second big building, the B building. It was constructed in 1994. And when I started to work in Spain, so this building was done for the Infrared Space Observatory project. So here you have some artwork, which is called Orbitas. So it is a little bit about orbits. And on the left side is something relatively new. So this is a nice panel. And normally, if you have a big conference or something, then they swap that and put something else in there. And so this is the entrance now. So we're just now in front of the, you can look around. This is, yeah, we will enter now. And so now we're in the hall of the B building, which is normally very nice. So you have here the satellite models. Those models change normally after several months. And if there was exhibition, then they swap those, the communications people normally. So here we have ExoMars, a model of ExoMars. I can show the picture a little bit closer. So this is ExoMars. And here this, you should all know what it is in principle. I cannot see the chat window now, but I suppose that you all know what this is. And just a little bit. Yeah, and then we have here a model of XMM Newton, but since Maria Santos, the operations manager, will talk about this on Thursday, so I will not go into this for the moment. Yeah, we are just inside the building here at XMM. We are here 2 big meeting rooms. And then we go into the restricted areas in some years. It's not like before. Now you cannot enter the buildings anymore if you don't have an electronic badge. So you see, this is the entrance, and we are going in this direction here. And this is a very nice room. It's a video conferencing room, or also a meeting room. But the interesting thing is what you see here on the roof. So it's a retro-illuminated picture from the Herschel spacecraft, which shows you the sky in sub-millimeter wavelength. It's really very nice. It's very impressive if you're in it. So it's covering the whole ceiling. And yeah, it's very nice. So it's a room. So here we have David taking the picture. No, the picture was taken by our trainee Diego. So here in this room, we have what is called, we call it the Mars room, because it has on the ceiling a big Mars. So really very, very nice. Also retro-illuminated. You can see it's really very nice. So normally when we have courses for university students or schools, also teachers, then normally I give here a small presentation about Mars Express, ExoMars, and explain them. We will not do this today because Alejandro did in the morning a very good overview of the Mars missions and also Mars Express and ExoMars. What you also see here, unfortunately, is that all the screens are here black, so we will redo these pictures. This was because with the confinement, so nobody's working on site anymore. We're all working, practically all of us are teleworking. I think there are only about 25% of people that go in from time to time. And so all the computers were switched off, and it took me a day to get everything up and running again. And there was no time anymore to take the pictures, so we have to redo those. And another nice thing that I wanted to show you is here what we call the Hall of Fame, which we have since a little bit more than a year now, where you have all the ESA science missions, or where ESA at least was participating, which started with the very old missions. If you go here to IAE, so the first mission, you cannot very good see the year numbers, but so the gray missions are those that were flying or still flying. So if you see one number only, like here for the Hubble Space Telescope, means this is just the launch date, and for the rest, it's still working. If you see two numbers, means it's the like here, for example, for ISO. So this is for the Infrared Space Observatory. So this is when it was launched, and then the other thing is when it was finished, when the mission finished. Then you have in orange those that are the missions that are not yet launched. So I see here that they have to change this because Solar Orbiter was already launched. But of course, this changes always. So this is a little bit a small tour to the Mars room from the entrance of ESAC. And so what I wanted to show you now is something else. We'll just stop sharing for a moment and see if I can get to the planning system, because to explain you a little bit, so what does a person do who is working on a satellite project? I mean, there are many things, there are many different jobs. There are software engineers, there are people in the working on the planning, there are other people working on the scientific instruments, calibrating instruments, looking at the data, checking quality of data. I personally have worked all my life in missions as a kind of at what we call the uplink side. So the uplink means everything that has to do with the satellite mission, that you have to give the satellite that the satellite does a good job. So this means, the planning what you want to observe, deal with the scientists, and do what they want to do, and then come up with a plan. So what the satellite does really. And so I want to show a little bit the tool that we have for Mars Express. So what you see here in this main window, perhaps we start from the start so that it's easier to recognize. So you have a map of Mars, and just check. I think I'm missing one thing here. If we can, the control panel is here. Just a moment, just have to switch on one of the visualization options. If you can see better the trajectory of the satellite, which is trail display spacecraft. Yeah, so here it is. So it's a map, and you see here, this is the represents the satellite, and then this is an orbit. I looked for you up the orbit because when we plan 3 months ahead of the actual observation, and what we do is we plan really up to the second of precision, 1 second of precision, what the satellite will do in any second, every moment. So I've looked you up the day of today. So you see here below 20th of October 2020. So what is the satellite doing at that moment? So you have here a representation of the complete orbit of the satellite. So you can see the hour, the time. So you have here, this was in the morning. So you have 4 o'clock, 6 o'clock, 8 o'clock, 10 o'clock. One orbit of Mars Express is about 8 hours, one revolution around the planet. And then what you can see on top of that is the representation of that orbit. So you have in the middle, this line is the closest approach to the planet. Since Mars Express has a very elliptical orbit, you can really see this afterwards in the graphics. And what you see here is a representation of what the satellite does. So it starts on the side and moves, the timeline moves here through the whole orbit. And what you see here is where the satellite is pointing and what the satellite is doing. So so the pointing is here below, and then these are activations of different instruments. What you see here are the different instruments. So this is the when you remember the talk from Alejandro this morning, this is the famous radar, MARSIS, which can look into the ground up to 4 or 5 kilometers depth to see if there is water or ice layers below the surface. This is a high-resolution spectrometer which can see the composition of the atmosphere. The same is true for this spectrometer here, SPICAM. And then we have here our high-resolution stereoscopic camera. And so if we look now on what is a typical orbit of the satellite, so you can see, if I scroll here through the timeline, so you can see the satellite moving. What you also see is, you see the dark part is what is in the dark. The side of the planet is in the dark, and the lighter one is where it's illuminated. And you see that the satellite this is the projection of the satellite directly onto the surface of the planet. What you can see now is the blue circle is the horizon that the satellite sees currently. And so it's going closer and closer to the closest approach. So it approaches the South Pole. Then, what does it do? So it starts to take data. So we switch the view. So we can switch to the south. And if we switch to the south, so we see now Mars from the South Pole here with the polar cap. And so if we continue, then you see that the satellite now is doing something. So you see the small green rectangles means that we are taking now data. And if you look now at this graph on the right side, you see that here the instrument, the radar, is starting to take data. So it's sending out radar waves to the surface and getting the reflections from the satellite. And with this, you can finally find out what the composition or what the density of the subsurface is on the planet. And so if we continue with this slowly, so we now coming really close to the pole now. And then you see there's something else coming up. So there we have now also some yellow rectangles, orange rectangles. So this is now here, this instrument here, the high resolution stereoscopic camera, which takes now images in 3D. You see here the red images also. So this is where we take now images that can then be combined to, in the end, convert them into 3D images. And so now we switch again the view. So we go back to the lateral view. And then you can see, so the satellite is now coming up on the other side of the planet. And now it's going further and further away on this elliptic orbit. And then you see it switches on again once more for the 2 spectrometers. And you see very curiously, so they are not looking down, they're looking to a lateral angle view, because what the spectrometers do is they want to know the composition of the atmosphere. So what they use is they're looking to the limb of the planet and looking at the star while it just comes up or disappears behind the horizon, so that they can look through the atmosphere with back illumination. So it's very interesting to see. So this is the planning tool that we use to plan normally a full month of observations. These are 100 orbits every month. You can see here on the right side, these are the orbit numbers. Although, so these are the orbit numbers. And this was the tool that we were using for most of the mission. And since some years, we have a very nice extension. So we got from our programs, from our software engineers, have a very nice addendum, which is the 3D view, which is much more intuitive. So for you, it's also, not only for you, it's also for us much nicer now to do the planning. So what you can see here, I hope it's visible. You see the stars in the background. So I can switch on now the natural movement. So what you can see is the satellite is moving on his orbit. What you see also is TGO. This is the yellow orbit. You see the orbits are very different. TGO has a circular orbit around the planet, very close to the surface, because what Trace Gas Orbiter is looking for is the composition of the atmosphere, looking especially for methane, while Mars Express is a multi-purpose mission with a lot of different instruments and also has a very elliptical orbit. So you see we are on the night side. So the sun is, if you look at this, you can see this. So the sun is here on the right side, behind the planet. And so what is our main problem here? If you can look at the graphic here, what this is when our satellite is in the shadow of Mars. And this is especially problematic because we have a very old spacecraft, which is now 15 years old, more than 15, 16 years now old. And our batteries are less, a little bit less than 40% of its original capacity now. So when we go into the shadow of the planet, you see now we're entering now the shadow, then we have to run on batteries. And since the batteries are not very good anymore, so we have to switch off and we cannot do science anymore. You see here the sun coming, so it will disappear in a moment. I mean, it's very nice. I really like this 3D view because it gives you a better impression of the geometry of the satellite. So you can see on here, so it's coming close to the shadow, and you see that the sun will disappear behind it, which is also very interesting because this is essentially, these types of occultations you can also use for scientific measurements. So, and it's the same for stars. You can take a bright star, and while it disappears behind the planet, so you can measure the composition of the atmosphere. So what you see now is we are slowly drifting. By the way, we have accelerated the real motion 60 times, so that we're not waiting too long. And so now we are drifting through the shadow where we essentially cannot do anything because we have to save battery power. And then, so you can also see, I hope it's visible on the screen, that you see the planet is getting bigger and bigger, because on our elliptical orbit, we're really coming now really close to the surface. So you have to imagine that on its first point, Mars Express is about 10,000 kilometers. So you see now we have come out of the shadow, so the sun is here again. So we can put our solar panels again into the sun. And then be careful now, the satellite will start to take data. So it's approaching, so it's moving around, orientating the radar, which is this long, long boom here, is orientating the radar where it wants it. Now it's taking data. You can see here the green and yellow now becoming orange. And now you see it has switched off the high resolution camera. It was taking pictures in 3D. It's still working with the radar. I said the graphics is a little bit low resolution for the model. So it's still taking images with the radar. Now it stopped. Then it continues, and it had its closest approach to the planet, which is about 190 kilometers distance. And now it slowly drifts away on this elliptic orbit, and we'll switch on now another instrument. So you can see the satellite. You see the projection of the satellite directly onto the surface here. And now it takes again, you see, so it was looking at the limb and taking images with a star in the background to analyze the spectrum of the Martian atmosphere. So this is the typical, kind of a typical day of Mars Express, or orbit, not day, it's an orbit of Mars Express, which is about 8 hours. And this happens every month 100 times, and this now since 16 years. And this is the work that we do in a small team. So we plan every revolution of the planet up to a precision of 1 second. So if you have some questions to this, I'm happy to answer those. Otherwise, I will just stop sharing so you can see your questions. If you don't have questions, then I just say many thanks. And I see you tomorrow again at 10 Central European Summertime. And tomorrow we will talk about the sun. Many thanks and see you tomorrow.
Thank you, Michael. This was absolutely amazing. What a closure of the day. I think everybody now wants to go to Isaac, so you have to find a way to bring us out there. That was absolutely amazing. Thank you very much.
Yep, you're welcome. So talk to you tomorrow.
Don't forget, everyone, to go to Google Earth and finish your mission there.